Welcome to video number 1 of Data Science Dojo's tutorial on Introduction to Text Analytics with R. I am your host, Dave Langer. As this is the first video in the series, let's start with a quick set of overview slides. So as this is the first video in the series, I figure a brief introduction about myself is in order. So as I mentioned, my name is Dave Langer. Currently, I am the VP of Data Science at Data Science Dojo. I also happen to be one of the lead instructors teaching our mini boot camps in various places around the world. I have a background in technology. I've been in the business for more than 20 years, and in that time I've held various roles. I've been a software engineer, I've been an architect, I've been a manager, but most importantly, I've been a data professional. So I have an extensive background in business intelligence, in data warehousing, and analytics, both traditional analytics, descriptive analytics, as well as predictive. My last job before joining Data Science Dojo was as a senior director of BI and analytics at Microsoft. At my last job, I had a team of technical program managers, and we owned all of the data platforms that ran Microsoft's $10 billion plus supply chain operation. That included everything from BI to data warehousing to analytics, anything, cubes, OLAP, all the way up to R and Spark running on a Hadoop cluster in the cloud, anything and everything in between. But probably most germane to this video series is that text analytics is one of my passions. I firmly believe that text analytics is one of the most useful tools to have in a data scientist's tool belt, or for that matter, any data professional who's interested in doing some advanced analytics in their daily work. Text analytics is a useful skill, and we'll see that as we go through in this video series. So I joined Data Science Dojo to realize the company's vision. The mission statement of Data Science Dojo is data science for everyone. We really do believe that. We believe that you do not need a PhD in statistics, you do not need a PhD in machine learning to learn data science tools and techniques and apply them in your daily work and derive business value. We absolutely believe that. And this video series is proof positive of that. By the end of this video series, you'll have a really firm grounding in the basics of text analytics, and you can apply those skills to your daily work and derive business value. Okay, since this is the first video, let's do a few housekeeping things. First up, there is going to be a GitHub repository for this tutorial. You will be able to get all of the code that you see demonstrated throughout this video series from this GitHub repo, and here's the URL for it. Next up, if you like what we're doing, in this video series, if you like what we're doing on some of the other things that we do on our YouTube channel, please follow us on social media. We actually provide a wealth of content, not only our own, but also hand-curated goodness of data science from a variety of sources across the internet. And we have a presence on all of the social media channels that you would expect. So if Facebook is your choice, you can follow us there. You can follow us on Twitter or LinkedIn or Instagram, Google+, you name it. We're on all of those platforms. In particular, if you like what we're doing here in terms of tutorials, we have more content on our YouTube channel. So if you like, please subscribe to the YouTube channel and you'll get not only the stuff that I'm doing in this particular video series, but you'll get updated when we produce more content and more tutorials as well. And lastly, don't forget about our 5-day bootcamp. If you like what you see here, if you like how I teach, if you like the kind of information that you get, the kind of skills that you build, we do teach a 5-day intensive bootcamp at Data Science Dojo. And of course, you can find more about that at datasciencedojo.com. Okay, another thing I like to do in my video tutorials, as well as my talks that I give, which by the way are recorded on our YouTube channel, is to do some expectation setting. Okay. So I'm going to assume the following of you as the viewer. I'm going to assume that you have coding experience with R. Not that you're an expert, but you can hack. Because we will be using, while not necessarily super advanced aspects of R programming, we will be doing some things like we'll be creating our own functions, and we'll be using the apply function, using those functions. that sort of thing. So I will make a certain amount of assumption around your R skill in general. The focus of this tutorial is not R programming, but how you do text analytics with R programming. So I will make some assumptions about your R skills. If you need to brush up on your R skills, we have some YouTube assets and tutorials on our YouTube channel that can help you with that. Okay, you'll need to have some math background. So to be clear, the focus of this particular tutorial series will be most definitely practice and not theory, but we will have some math. That unfortunately, that's inevitable. We will have to have some math coverage of some kind. Otherwise, for example, TF-IDF, we need to explain the mathematics behind it, because that will also explain the benefit that you get for using it. And that's TF-IDF is mighty. You use it all the time in text analytics, so it's important. But we won't drill. You won't see tons of equations. We'll focus on practice. So, and I need to stress this very much. This is an introduction to text analytics. Text analytics, this subject, this domain is very, very broad, very, very deep, super interesting, right? Text analytics, text mining, natural language processing, they all kind of fall under the same banner, the same umbrella. So there's lots and lots to learn, lots and lots of goodness to be had. But this is going to be very much an introduction. In particular, the focus of this series is going to be on the creation of predictive classification models over textual data. So we're going to have a very narrow focus. But this is a very useful thing to be able to do. We'll talk more about this later on in the video series about the various types of scenarios where this is applicable, and there are many. Not only will we be focusing on creating predictive classification models using textual data as the input, we will also be focusing on the 20% of the tools and techniques that you use to build predictive classification models over textual data that can be used in 80% of your projects, right? So we're really trying to do the 80-20 rule here. Introduce you to the 20% that's 80% useful, but note that this is very much an introduction and it is a broad, broad topic, and there's a lot to learn. And lastly, since this is an introduction, we're going to use decision tree ensembles. The predictive models that we were going to build will be ensembles of decision trees, and in particular, we'll use the mighty random forest algorithm. And the reason for that is that it's relatively simple. There are other models that can be used to support vector machines, for example, or boosted decision trees. But we're going to focus mainly on the mighty random forest because it is a relatively simple model, but it is also relatively powerful. Once again, it's an introduction. What we'll teach is broadly useful. You can always do more research on your own at the end of this video series if you're interested in using support vector machines, for example. As I mentioned earlier, there's going to be a GitHub for this video series, and I wanted just to show it to everyone just to make sure they're familiar with it. So here's the URL. This is the same URL that was in the PowerPoint that we just saw. Now, as you can see right now, there's nothing in it. That is because I haven't uploaded the content yet, but by the time you see this video, this will be fleshed out. You will see a nice introductory README, and there will be an R file corresponding to this first video in the series as well. So you can get all of the code that you'll see in this video series from this GitHub. Next up, I also wanted to introduce the data that we'll be using for this particular series. So it's from Kaggle. So Kaggle now has a curated collection of data sets, and here's the URL for the particular data set that we'll be using. This is originally from the University of California, Irvine Machine Learning Repository of Data Sets. You can see that here, the UCIML. The reason why we're not using the UCIML data sets directly is because the folks that created this version of the data set on Kaggle did some data munging for us and created a nice CSV file. So we want to use that because it makes our lives easier. Now, in particular, this is a classic scenario for text analytics with classification models. In particular, this is spam. We're going to have our data set be composed of SMS messages, texts of various kinds, and we have a label to say whether they're ham, they're legit, or spam, they're bad. Okay, ham versus spam. Now, I will warn you that this is raw text data of actual people sending texts back and forth. So there is some stuff in here that is not G-rated. There is profanity. There is some adult material in here. It's nothing too untoward, but just be aware that this is not a rated G data set by any stretch of the imagination. So just wanted to let you know that, because we're working with real world textual data. It's the best kind to get your feet wet, and unfortunately sometimes when you're working with real world textual data, you get a dose of the real world, as it were. Okay. So be forewarned. But here's the data set. Here's the URL. We will be also including a copy of the CSV in the GitHub, because we want to make sure that we have a snapshot of the CSV file available to you in the GitHub for posterity, so that if somebody comes 2 years from now, this file may have been changed, but the code that we have in the repository will work with the copy of the CSV that's in the repository. Okay, so that's the data. Now we know about the GitHub, where you can get the R code that I'm about ready to go through. You know about the data set that we're going to use. So let's just go ahead and get right into it. Okay, so first up, we're going to be using a collection of packages in this tutorial series. At the time of this recording, this being video 1, I believe this is going to be the full set of packages that we're going to use, but I reserve the right to add more packages later. But we'll start with this collection here. And if you're not familiar with R all that much, never hesitate to use the help system. So for example, if I do $install.packages, I can get the help file. And essentially this is the mechanism by which you can tell R, reach across the internet and please get these packages for me that have good functions that I want to use in my text analytics. And in particular, we're going to be using ggplot2 for some visualizations. We'll be using E1071 via the caret package. Caret depends upon E1071, so we need to have it. We'll be using the quantita package. This will be our main package for actually doing text analytics. It's very, very cool. Has a lot of really good functionality for doing text analytics. We'll be using IRLBA for doing some singular value decomposition, some SVD, some feature extraction, which is really cool. And then lastly, we'll be using the mighty random forest. It's one of my favorite algorithms. It has a lot of power, has a lot of capability. It's very easy to tune. You can get really, really far with random forest if you do good feature engineering, and that's where SVD will come in, as we'll talk about later. Okay, so if I run this line of code, you can see here that R will reach out across the internet, start grabbing these binaries for these packages, and start downloading them, installing them on my machine here. Now, if you already have these packages, or maybe some of them installed on your machine, that's no problem. You can go ahead and use this mechanism, and it'll refresh the packages that you already have installed, which is handy dandy and super nice. Okay, so next up, I've already set my working directory in R to load up the CSV file, but let me just quickly demonstrate that for some folks if they're not used to doing this. So if you go to Session, Set Working Directory, Choose Directory, this is how you tell R where the location of your data files are. This tells R, the RStudio environment, hey, read files from here and write files to here if I so choose. So if I do that, and you'll get a similar experience on Mac, you'll get a Finder window, and you can just navigate using this to the location on disk where you've loaded the spam file, the spam CSV file. Okay. And as always, let's go ahead and take a look at the read.csv function in the help file. I won't drain this. You can take a look at it at your leisure if you're not familiar. But not surprisingly, read.csv says, okay, R, go out to my file system, read in the CSV file, convert it into a data frame, and store it in memory. And in particular, one of the things that we're actually going to tell R to do is, hey, by the way, R, when you read in this CSV file, when you read in string data, when you read in textual data, do not make it a factor. By default, R makes string data into categorical variables, factor variables. And we don't want that because we're doing text analytics. We want the raw text. So we tell R, hey, don't make the strings into categorical variables, into factors. So if we run these 2 lines of code, we get a nice spreadsheet view in R. That's what this view function right here does. Capital V, view, brings up this nice spreadsheet view in R. And we can take a look at the raw data. And a couple things jump out at us right away. First up, these column names aren't particularly useful, and it looks like we've got some funkiness going on here in these 3 columns, because we actually know from the Kaggle website that in fact we only have 2 columns worth of data. We have the SMS text message and we have the label ham or spam. So this is all extraneous. So let's go ahead and clean that up. So first thing that we're going to do is we're going to say, okay, hey, you know what, R, I don't want all of the columns anymore. I just want the first 2 columns. That's the only ones I care about. So this says, hey, R, go to the spam.raw data frame. Go ahead and filter it. I want all the rows and just give me the first 2 columns. Next up, we can overwrite the labels, because if you remember, they were V1 and V2, and that's not particularly useful. So what we'll do is we'll change the names of the columns, the name of the variables on the data frame, and we'll call the first column the label, right? Ham or spam, it's the label. And next up, we'll just call the second column text. Right? We could call it SMS, we could call it whatever we want. I've just decided to call it text. So if I run that line of code, oh, and as always, never hesitate to use the help system here. Names of an object. Excellent. Excellent. Okay, so this is how you can get the names or reset the names of an object. Okay, and lastly, let's go ahead and run the view code again. And you can see here we now have a nice, well-ordered, well-structured data frame where I've got my label column, ham and spam, and I got my text column. Cool. Okay, so next up, we can see here that we have 5,572 observations. We've got 5572. That's the number of rows that we have in our data frame, in our data table. And we have 2 variables. So one of the first things that we want to know before we start any modeling project, any data science project, is do we have any missing data? Because missing data is a problem. So the complete cases function, and as always, don't hesitate, use the help system. The complete cases function helps you find complete cases. Return a logical vector indicating which cases are complete. That is, have no missing values. Okay, cool. So we're going to say, hey, R, return me a logical vector. And if I just run this code snippet, I'm going to get a big dump to the output here. Look at that. And we see a lot of trues, which means these are all of these right here, complete. They're not missing any data. But what I'm interested in is not the number of cases that are complete. What I'm actually interested in is knowing the number of cases that are not complete. And that's what I've got the exclamation point, the bang here, the negation operator, not complete. And then if I use the which function, and as always, don't hesitate, which indices are true, right? So if I negate this, things that are missing will now become true. That's the only thing that I care about, and I can ask for the length. And that'll tell me how many of my cases are in fact not complete, missing data. Okay, so I run this line of code, and voila, 0. Excellent. So the data has the data frame has complete data in it. Sweet, that makes our life a lot easier. Cool. All right, so not surprisingly, the first step is always to explore the data. Always explore the data. Now, one of the things that you're going to find often in text analytics, and especially when you're starting to do anything like classification of text documents, whether that's sentiment analysis or spam, you name it, is that you may have to understand what the class distribution of your labels are. Because, for example, in a ham versus spam scenario, it's not uncommon for spam to be actually relatively rare, thank goodness, compared to legitimate textual documents. Or, for example, in sentiment analysis, you would like to believe, especially if you're doing sentiment analysis, maybe about, for example, tweets about your brand, that negative tweets about your brand are actually relatively rare. You would hope that to be true. So that's one of the first things that we want to do is we want to take a look at the distribution of our labels. Now for us, this is pretty simple. We have a binary classification problem here, right? We already know that a SMS text is either ham, legit, or it's spam, bad, not legit. So it's binary. So what we can do is, oh wait, I'm so sorry. I skipped over a line of code here. My bad. First up, my apologies. We need to take our label here and turn it into a factor. Right? We know it's ham and spam. So that's our two categories. So let's go ahead and make that a factor. My apologies. Okay. So now that we've got our label set up as a factor, let's go ahead and run a table on that. And if I just run this line of code here, this will tell me, okay, look, count up how many hams and how many spams I've got. Now, technically, this code would work even if we hadn't made it a factor, but I tend to like to make my things factors early on because it's useful for things like ggplot2 visualizations, as we'll see in just a bit. Okay, so if we run table on our spam.raw label, we can see here the relative count. And you can see here that, while not astronomically small, the number of spam is actually relatively small. But it's usually more intuitive to actually see this as a percentage. And that's where the prop.table function comes in. And as usual, use the help system. Express table entries as fraction of marginal table. That's not particularly intuitive for a lot of folks. So let's just run the code and you can see what happens, right? So here's the dealio. Table just gave me the raw counts. 4,825 hams, 747 spams. What prop.table was is actually to convert that into the percentages. So our data set is 86.6% ham. It's 86.6% legit. And it's unfortunately 13.4% spam. Now this is, while non-trivial class imbalance, it's not bad, right? It's not like 1% spam and 99% ham. But it may be problematic as we move on when we start building our machine learning models. We may want to try out some techniques to account for this imbalance between the two. 13% is not terrible, but we may actually get better performance out of our model if we do some magic to kind of account for this disparity. So that's just something to keep in the back of your mind. But generally speaking, this is a good practice, especially in text analytics and classification in text analytics. Take a look at your distributions of your labels. It's extremely important. Extremely important. Okay. So next up, let's just get a general feel for some more about our data, right? And in particular, let's take a look at the relative lengths of the texts, right? Because if we go back to the spreadsheet view, we can see that some are short and some are longer. So it may be interesting to just take a look at and say, okay, hey, like, look, this one's spam and it starts with winner, right? Okay, cool. It's a longer one. Maybe there's a propensity for legit texts to be shorter and illegitimate or spam texts to be longer. It's entirely possible. So the easiest way to do that is just to create a new feature on our data frame. I'm just going to call it text length. And we can use the nchar function and nchar. Count the number of characters. Excellent. So go through every SMS text in our data frame one by one and calculate the length in characters and store that for me in a new feature, a new column on our data frame called text length. And then lastly, hey, do a summary, and not surprisingly, object summaries, not particularly useful, but when you see the output of the code, you'll know what it does. Do a summary on text length. And there you have it. We have some summary statistics on the length of texts. And by the way, if we go back up here, you can see now we have a new column added to our data frame called text length. And you can go down here and you can see, there's some variance going on in text, right? 28, 27, 19, 142, 172, 291. And you see that there's a lot of variance in this data. So this could be potentially interesting. So if we look at this, we can see here, well, we've got quite an interesting distribution. I mean, look at this. At the max, we got 910 characters. That's quite a long text message. But we also have a minimum of 2 characters. And probably even more interesting is that our median, the median value, the 50th percentile, the value at which half the texts are shorter than this and the value at which half the texts are longer than this is 61 characters. So that's a pretty big disparity here. Pretty big disparity. And you'll also notice that the mean is, 19 characters? Fully 19 characters higher than the median, which means that there's probably a certain amount of skew here, which is indicative right here of the third quartile. So 75% of the text messages are 121 characters or less, and only 25% are 122 or more. So there may be some skew here to account for these two differences. So let's take a look at the distribution using a histogram using the mighty ggplot2. That's what we'll do next. So we're going to go ahead and load up ggplot2. Oh, and look at that. Stack Overflow is a great place to get help on ggplot2. Absolutely. Okay, so here's ggplot2. Now what we're going to do is we're going to plot a histogram. We're going to visualize this distribution using a histogram, and we're going to segment it. We're actually going to also use the power of ggplot and say, look, you know what? Color code the bars in the histogram. Color code the bars with the label. So that'll give me some sort of graphical understanding of the relative proportion of ham versus spam in the context of text lengths, the lengths of the texts. Right? And this is super useful. The reason why we had to make label a factor earlier was because if it wasn't, this fill wouldn't work and we wouldn't get the awesomeness that we're about ready to see. And you'll notice here I've arbitrarily picked a bin width of 5. And I did that mainly because just taking, just eyeballing this data, 10 seemed like it was probably a little too big of a bin width and 1 was probably way too small, so I just used 5. Okay, so let's go ahead and run this line of code. And here we go. We get this nice handy dandy plot where, as you can see here, the turquoise color is the spam and the orange color is the ham. And notice it's super interesting, right? We had an hypothesis earlier that said, look, you know what? It just eyeballing the data, just pure wild speculation by eyeballing the data. We had an intuition that in general, spam would tend to be probably longer texts, and shorter text would probably tend to be ham. And we see that actually quite clearly. Now, as we move on later in the series, we start talking about feature engineering, we may actually end up creating a few features that aren't actually based on the raw text itself of what was actually typed into the SMS text message, but we will derive some features potentially that may be useful, like this one. This one may actually prove to be quite useful, actually, from a classification perspective, right? And you look at this, I mean, the texts in basically, well, probably all the way up to about maybe here, this range, are overwhelmingly not spam. So this may be a pretty good predictive feature for us, potentially. So this is super useful. Now notice, though, that, check it out, though, the extremely long lengths of text, though, are actually, the vast majority of them are, in fact, ham. They're not spam. So there's this kind of sweet spot, right? So maybe this, working in conjunction with some textual-based features that we'll engineer later on, may actually be pretty powerful in determining ham from spam. Okay, so we're going to try and keep these videos around a half hour or so. So I'm going to go ahead and end this video right now at this point. All of this code through this wonderful ggplot2 visualization will be up on the GitHub by the time you watch this video. Thank you for watching. Like I said earlier, if you like what we're doing here, please subscribe to the Data Science Dojo YouTube channel. Also, if you like what we're doing here in general, go ahead and connect with us on social media. And lastly, I hope to see you in one of our upcoming data science boot camps. So until next time, I wish you very happy data sleuthing. Okay, so what I have here is an RStudio environment where I've ran the code all the way through the end of video 1. And as you recall from video 1, we ended up with this particular graphic, this particular piece of ggplot2 awesomeness, illustrating the propensity of ham and spam, ham being orange and spam being teal, based on a feature that we engineered called text length, and how we talked about specifically that this feature may be helpful for us later on in our classification modeling. Okay, moving on in the text. So here's the thing. In machine learning, we are obsessed with creating models. In data science in general, we're obsessed with creating models that we can put in production and our business constituents can hang their hat on, that they can rely on to produce the business results that are desired. And in machine learning and data science circles, that's known as generalization, right? Can your model actually generalize and perform well on data that is brand new, data that it's never seen before? So we're obsessed about that. So we have to take our data and we have to actually split it and segment it as part of that obsession. To say, okay, look, if I use all of my data all the time to build and tune and improve my models, I never really have a way to check, to give myself a gut check to say, look, I'm pretty confident that this model will perform well in production on brand new data. Because we're obsessed about that, we actually say, okay, look, I can't use all of the data all at once. I need to actually take some of my data and hold it out, split it off, keep it over on the side, and then I can use that as a check. I use that data that I held out, that data that I split off to the side, to simulate, once my model's in production, brand new data that's coming in as a result of the business operation. And that by doing that, this gives me a way to estimate how generalizable my model is. This gives me a way to get a sense of, if I put this model in production, how well will it actually work in the real world? Okay, so we need to split our data to allow us to do that. So the first thing that we're going to do in the code is load up the mighty caret package. The caret package will provide us some functionality for splitting our data in such a way that we can achieve this goal. We can build our models, we can train our models, we can build new features, and we can experiment. And then we can use the data that we split off and hold out to then verify, okay, how good is this model really? This data that I'm holding on the side simulates the real world unseen data. I run it through my trained model and I say, okay, how good is it? Okay. So let's run this code here, and we're going to go ahead and pull up the caret package. And you can see here, caret stands for classification and regression training. Caret is mighty. If you're going to be a data scientist or a machine learning person or just a data professional in general, and you're going to use R as one of your primary tools, you are going to want to learn the caret package. It is wildly, wildly useful. So to show you, go ahead and click on this help description here, and you can pull up the PDF. And what you get here is a document, which is really useful. I'm not going to drain it, but it gives you a brief introduction to the caret package and how to use it. Caret provides a wealth of goodness to you as a data scientist. Not only does it provide functions like we'll see in a second that allow you to split your data in a very robust way, but it also provides an interface to allow you to program against literally more than 200 machine learning algorithms in a common way. So you don't have to go out and learn 200 different APIs. You can just use the caret API and you're off and running. And later in the video series, we'll actually use Caret with the mighty random forest, and I'll show you an example of how you can use Caret to make your work, even with the random forest, much, much more productive. Okay, so we've got the Caret package. So what we're going to do here is a very traditional sort of thing. We're going to go ahead and say, look, I don't get to use all 5,572 pieces of my data all at once here. Right? I don't get to use all of this data at once, because I'm paranoid about building a model that will actually generalize in production. I can deploy the model in production, and I can be reasonably confident that it will work well when brand new data comes in, data that it's never seen before. So a typical split to simulate this is 70-30. I'm going to keep 70% of my data for my training, 70% to build my model, 70% to play around with the data, to experiment, to create features, what have you. And this 30% I'm going to go ahead and hold out. And I'll use it to test my model, to actually test how good it is. This is a gut check. So this is known as a 70-30 split. And typically these splits are known as the training split and the test split, not surprisingly. Now, as a brief aside, I should mention that this is a pretty standard process that we're doing here, but it's also not necessarily the most ideal. What you would probably end up doing in reality, what I would advise doing in reality if you were doing this in a real world project, is you would actually split the data into 3 distinct chunks. And very briefly, what you would do is you would have a training data set, and you have a second data set, typically referred to as your validation data set, and you'd have a third one called test. The difference between that and what I just described is that the very last data set, the third one, the test set that you have at the very end, you only look at that at the very end of your project. The other two you use as part of your normal project process, but that third data set you use as a final gut check at the very end of your project. And that's mainly because you're so paranoid about generalizing your model. But that's relatively advanced topic, so we'll stop there. What we're doing right here is very typical. You'll see it in the literature all over the place. We're going to do a 70-30 training test split. Okay. Now, if I scroll up to some of the code that we ran in video 1, one of the things that we discovered was this right here. We know that we have unequal proportions, right? We have 86.6% ham. We have 86.6% of our text messages are legitimate, and 13.4% of our messages are spam or illegitimate. So here's the thing. If I'm going to split my data into a 70% training set and a 30% testing, if I just did that at random, it's entirely possible, and in fact, maybe even probable, that I wouldn't get these exact proportions, right? It's entirely possible that maybe this 30% test split, just because of the pure random nature of things, maybe had a higher percentage of spam than 13.4%. Maybe it was 20%, let's say. That can be a problem, right? If we split these data like this, we want to make sure that each split, each chunk of this data is as representative of the original data set as possible. We want this 70% to be representative. Therefore, we want this 70% to have the same proportion of ham to spam. We want this 30% for the test set to be representative of the original data set. We want it to be the same proportion of ham versus spam. This is known as a stratified split. Stratified split. So what we need essentially is a function that allows us to do two things. Randomly sample our data, and also ensure that the split is stratified, that these proportions are maintained across all of the splits. And not surprisingly, since Caret is mighty, there is a function that we can use to do exactly that. So if we do the help file and create data partition, you can see here that Caret comes with a collection of data splitting functions, the first of which is the one we're interested in, which is create data partition. So you can go ahead and take a look at the help file at your leisure. I won't drain it. Let's just take a look at the code and I'll explain what's happening here in the code. Okay, so first up, we pass into create data partition our label. which we've made a factor, it's a category, and create data partition can now use this and actually say, oh, okay, you want to create some splits. I can figure out from this piece of data that you give me the proportions that I need to preserve, right? This 86.6 versus 13.4% split. I will make sure that this proportion is constant across all the splits. And you say, okay, great, thank you. Caret, also, I only want one split. I can actually ask for multiple splits. And the reasons why you would do that are beyond the scope of this course, but it shows you the power of Caret, where you can actually ask for multiple splits, multiple iterations of this algorithm. But we're only interested in one split. That's all we care about. So we only want one split. Next up, we can tell Caret, hey, we want 70% of the data. Please give me a random sample of my data frame. Give me a random sample of these 5,572 observations. That is 70% of the size. I only want 70% selected at random. Please also make sure that the label proportions are maintained. And then lastly, by default, create data partition will return you back an R list with a bunch of things in it. Typically, that's not what you want, I would argue. Typically, what you want back essentially is just give me the indexes, the row numbers that I want. Give me back the row numbers that are a 70% random sample of my data where the class label proportions are maintained. Okay, good enough. Next up, I should talk a little bit about this line of code. So right now we're setting the random seed because we want to ensure reproducibility. We want to make sure that what you see on your computer as you run this code is what you see on this video as I'm running it on my computer. So what this does is this tells your computer and my computer to start the random number generation at the same place. So that way we get the same set of random numbers. Your set will be the same as mine, which means that we will get the same 70% split. Okay, so let's go ahead and run these two lines of code. And let's talk about indexes now. So I asked R to run this function and store the results in a variable called indexes. And as you can see over here, it's an integer vector that is 3,901 integers in length. So if we do a quick math calculation here, you can see that 70% of our observation count of our original data set is approximately 3,900. Sweet, sweet. Now let's take a look at the first 20 values here. Okay. As I mentioned earlier, these are actually the row numbers. These are actually the row indices that we want. Notice that they're in ascending order, but there are gaps. 2 and 3 are missing. 7, 8 are missing, so on and so forth. That's because we asked for only 70% of the data. So what this is saying is, hey, look, Dave, if you use this particular variable and you index into the data frame, you will get back 70% of the data frame at random where the proportion of the class labels is maintained. And we can see that right here. I ask R, hey, go to the spam.raw data frame, go ahead and filter it, and filter the rows by the indexes. Give me row 1, row 4, row 10, row 18, 25, so on and so forth. Go ahead and give me all the columns. Run this line of code. Sure enough, I get 3,901 observations of 3 variables. And if I run this line of code, what I get is exactly the opposite. That's what this negation sign does. It says, hey, R, do the opposite of this filter. I don't want the stuff that's in this filter. I want all the stuff that's not in this filter. So I run this line of code. Now I get 1,671 observations of 3 variables. Cool. And now I can once again use prop table to verify that I get the proper splits and the proper proportions. And you can see here, sure enough, 86.6 and 13.4%. So the training has the right proportion and the test has the right proportion, which means that now I have a 70-30 split of my data that is representative of the original data set in terms of ham versus spam. Excellent. So that means I can use this to build and tune and improve my models. And when I'm ready, I can use this data here to verify how well will it actually work in production. Give me some sense of how well will it actually work in production. Sweet. Okay. All right. So we've got our data split up. We've got our training data set. So now we're good to go. Now we can start doing some interesting things. So now is a perfect time for us to actually understand, okay, now that I've got this text data in this column, what do I do with it? How do I transform it from this raw blob of textual goodness into something that R can understand and I can use to actually train an accurate ham-spam classification model? The core idea that we need to get our heads around is this. How do we represent text as a data frame, right? This is a representational question. R only understands data frames, right? We know this as R coders. So how do we get text to look like a data frame? How do we get unstructured data into a structured format? Now, the answer is actually pretty obvious, and I'm sure most of you already know this, which is, okay, fine, Dave, it's pretty simple. If I've got a bunch of textual data, make every word in my text data into a column. That's the easiest way to take this unstructured data and make it structured in a tabular format that R can understand and work with. Okay, so let's see how we actually do that in practice. So let's take this hypothetical document here. And this is what's known as the duck test. If it looks like a duck, swims like a duck, and quacks like a duck, then it probably is a duck. So let's take this very simple example and say, okay, look, let's walk through this conceptually to say, all right, how do I represent this unstructured data in a structured way that R can understand? And the process by which we do that is known as tokenization. So essentially we say, look, let's go ahead and decompose our textual document or our textual documents into distinct pieces or tokens. So if we apply tokenization to the hypothetical document, right, the duck test, this tokenization process could, and I emphasize could, and I'll explain why in a second, could produce the following set of tokens. And nothing surprising here. If you just look at this, you can say, okay, Dave, all you did was essentially say anything that isn't white space is a token, right? First word, even punctuation like commas and periods, everything is a token other than white space because white space isn't anything, so we don't really need to worry about it. So all this is tokens. Now, the reason why I use the word could is because we're going to run through a very simple hypothetical example here in these slides. But as you'll quickly find later on in the series, as we work with quantita, and as you expand your data science skills in the text analytics space on your journey in text analytics, looking at other packages and other functions, what you'll quickly find is tokenization itself is actually a broad subject as well. And there are many, many different ways to tokenize textual data, all with different characteristics and all with different goals in mind. So we're actually going to use the simplest approach because once again, as we talked about in video 1, we're following the 80-20 rule. We're going to use the 20% of stuff that's 80% useful. And this sort of tokenization scheme is broadly applicable across a huge number of problem spaces. Okay, so we could get tokens that look like this. All right, moving on. Okay. Next up, once we have tokenization complete, we can create what is known as a document frequency matrix or a data frame, right? Or a table. They're all essentially synonyms. Data frame, matrix, table, they're all essentially a square data construct. Okay. So we can create this document frequency matrix and it has 3 specific properties that are important. First up, in a document frequency matrix, each row in the data frame, each row in the table, each row in the matrix represents a single document in your collection. In our particular case, with the SMS data, each row will represent a specific SMS text message. Each column in the matrix, in the data frame, in the table, represents a distinct token. And we'll see that in a second here, what that means. And then lastly, each cell, so each intersection of a column and a row, contains the count of that token for a document, for a particular document. As we'll see in a second, this representation is wildly useful. Again, under the 80-20 rule, this document frequency matrix representation gets you very, very far in practice. Now, there are many, many advanced text analytics techniques that do not rely on this necessarily, but you would be surprised at how far you can get in a very, very large number of scenarios using this representation. In many ways, it is the de facto standard if you're doing classification, predictive models on textual data. Okay, so here is our hypothetical DFM for our document. Now notice, first up, we have what are known as the terms. These are the distinct tokens. Now notice that duck actually showed up as a token in our process a total of 4 times. You can see that here, right? If it walks like a duck, so on and so forth. Duck showed up 4 times. However, it doesn't probably make a lot of sense for us to actually have duck as 4 separate columns in our data frame. So the distinct token, the singleton instance of a token across all of our documents is what's known as a term. So if we had 4,000, 5,000 documents, whatever, any of them that had duck would have their duck counts right here in this single column. As we talked about before, the rows are documents. In this particular case, we only have 1 document, so we only have 1 row. In the case of our training data that we just created, we'll have 3,301 rows in that particular DFM for our training set, because that's how many documents we have. And you'll notice the frequencies are here, right? Just the counts. Duck showed up 4 times, like showed up 3 times. We have 3 commas, so on and so forth. Okay. All right, moving on. So here's the thing to remember about this particular representation. Notice that word ordering is not preserved, right? We know that duck actually shows up, if it looks like a duck, swims like a duck, and quacks like a duck, then it probably is a duck, right? Duck shows up like here and here and here positionally. But notice that because we collapse everything down to a singleton instance of a term, that we lose word ordering. And in fact, actually, we could jumble this all up and it wouldn't matter because we lose word ordering anyway. So it doesn't really matter how these columns are actually set up. We could swap them all around and it doesn't matter. What really matters is that we have a single column for a singleton term and then we have the count. That's what really matters. So word ordering is not preserved. So this is super important. This particular setup is what's known as the bag of words model. Because since word ordering isn't preserved, you can just think of it as a big jumble of words in a bag, right? It's just word counts. That's all it is. And some folks, when they initially learn about this, go, oh, wait a second. Hey, look, Dave, wow, how can you just throw out word ordering? That's kind of important. That's how we communicate. And the answer is yes, that's absolutely true. But once again, you'd be surprised at how far you can get, how much power you can get in these models by getting rid of word ordering. It doesn't really matter. We'll see later on when we talk about n-grams that there's a way to actually add back in word ordering into this model. But in the beginning, you'll be surprised at how far you can get by just saying, look, you know what? Just find all of these interesting terms for me and just use the counts. You'll get really, really far, believe it or not. It's actually very, very powerful. So not surprisingly, this bag of words model is a very, very common representation. Again, under the 80-20 rule that we've talked about, this is going to be used in 80% of your projects, especially if you're doing classification models, whether that's what we're doing here, which is spam detection, or if you're doing sentiment analysis, or you're trying to classify legal briefs or loan documents, whatever, right? This is going to be the de facto standard. This is where you're going to start most of the time. The bag of words model is extremely powerful. It's extremely flexible. As I said, we'll add, when we talk about n-grams, we'll add some notion of word order back into the bag of words model to extend its power. and we'll see that it has the possibility of making our models even more accurate. But this BOW model, this bag of words model, is extremely common and is the de facto standard. Okay, so given this hypothetical basis, we've got some considerations that we need to enumerate. And this, and I will admit, this is going to be a bit of a shock and awe slide. We're going to go over a lot of things to consider. We're going to address each in turn in the R code, but I wanted just to put this in the back of your mind. These are all things that you need to consider when you're doing a text analytics project. So first and foremost is, do we want all the tokens to be terms in our DFM, in our document frequency matrix? So for example, we saw that in our hypothetical bag of words model, that the first word in the sentence in our document was if with a capital I. Now, strictly speaking, hypothetically speaking, if the word if showed up somewhere else in the document, it may not be capitalized. So you would have if with a capital I and if not with a capital I. And strictly speaking, most R processing that you would do would actually treat these as two separate terms. You would actually have two separate if columns, one for capital if and one for lowercase if. And the answer is that the question is, generally speaking, do you want that actually in your model? Usually the answer is no. So typically what you end up finding is most of the time you're just going to lowercase all of your textual data. Now, some of you may be screaming at the screen right now going, Dave, whoa, how can you get rid of casing? Casing actually matters. There's signal in that. And that's true. There is. And there are more advanced text analytics techniques that you can use that take advantage of capitalization. But once again, and I know I'm going to sound like a broken record here, you'll be surprised at how far you can get in text analytics with this very simple bag of words approach. And one of the things that you do is you say, look, I don't worry about capitalization. I'll just go ahead and lowercase everything and it'll work itself out in the end. So that's the first thing you need to consider. So next up, you need to consider punctuation. Do I want punctuation in my term frequency matrix? Do I want periods and exclamation points and question marks and double quotes and all that sort of thing, what have you? And the answer typically is no, you don't. Because as we said on the previous slide, the bag of words model doesn't preserve word ordering. Therefore, it does not preserve sentence structure. Therefore, punctuation really doesn't give you anything. So we typically strip that all out. Now again, there are more advanced text analytics techniques that can take advantage of punctuation and sentence structure. But again, you'll find out, you'll be amazed at how far you can get with this simple bag of words model and just ignore sentence structure. Next up, do you want numbers? Do you want the actual digits in your data? Sometimes you do, and most of the time you do not. Now, just to be crystal clear on this point, we're talking about just the digits. The word zero, Z-E-R-O, would stay in. We're talking about the digit zero. Would we strip that out? Most of the time, a lot of the time, you strip out numbers, but not always. It's something you need to consider. Next up is, do you want every word to become a term? Do you want every word, every token, to actually become a term in your DFM? For example, the word the. It's the single most commonly occurring word in the English language. It usually adds no value whatsoever. Collectively, words like the and etc. are known as stop words. Every language has stop words. They're essentially grammatic sugar. It allows the language to flow. But strictly speaking, they don't add any semantics. They don't add any predictive power. So usually we strip stop words out because we don't want them in our DFMs. Next up, we have symbols. Now, this is more important these days than it was in years past because of the advent of social media. So, for example, sentiment analysis of Twitter feeds, very, very popular, very, very useful. You have to worry about things like @ symbols and hashtags. 10 years ago, you'd probably just strip this stuff out because it didn't really matter. But nowadays, depending on what you're doing, there may be signal. So you have to decide what you're going to do with symbols like this. Next up, we have similar words. So in the English language, for example, we have ran, run, runs, and running. This is an example of what we'll come to see as known as stemming, which is, okay, look, is it possible for me to collapse very similar words into a single representation? So instead of having 4 columns in my data frame, one for ran, one for run, one for runs, and one for running, can I collapse all 3 of these down into a single representation? Maybe just the word run. Transform ran to run, runs to run, running to run. And stemming actually does that for us. It allows us to collapse words down into a single representation, because arguably, in one context, these all essentially have the same meaning, which is a human being moving as fast as possible under their own power. I ran all the way home. I'm going to go for a run. Is Dave running? Why is Dave running? Right? Now, some of you are probably jumping to the next idea, which is, okay, Dave, that makes sense, but you know what? These words can actually be used in a different context. So if maybe it's not just about a human being moving as fast as they can under their own power. Maybe this is in the computer domain or the IT domain. Go run the program. Has the batch job ran? Is the job currently running? So on and so forth. So as it turns out, generally speaking, in this simple bag of words model approach, typically we don't have to worry so much about that. What we're mainly concerned with is collapsing these 4 terms into a single term. So we only have one column in our DFM, in our matrix, in our data frame. And we can figure out the other types of contexts based on the word counts that are also in the document. So for example, in the IT domain, you'd probably have things like hard drive or disk or server or CPU or very computer specific, IT specific terms that would show up that would allow you to derive implicitly the context that this is actually used, these words are being used in the context of computer systems and not in the context of human beings moving as fast as they can under their own power. So typically we don't worry so much about that second aspect. We primarily concern ourselves in the bag of words model with collapsing these things down. So what you can garner from all of this, from this shock and awe slide, is that pre-processing of textual data is a major, major part of text analytics. Now, this is true in general for all data science and all machine learning projects, but I would argue it's especially true with text analytics because you're dealing with the dirtiest of dirty data. So you have to spend a lot of time and a lot of care analyzing your data, understanding your data, and making sure you're doing the right thing. Now, in this particular video series, as I said in video 1, for simplicity's sake, I'm just going to wave my hands a little bit in certain cases and say, well, if you did this in the real world, you would actually do this and this and this and the other thing, because this is very much an introductory series. So just want you to keep this in the back of your mind as we're going through the rest of the R code, that you're going to need in a production scenario, as you apply these tools and techniques in your day job, all these considerations you're going to need to keep in the back of your mind. Okay. All right. I will go ahead and stop there since we're a little bit over time right now. Hopefully you're enjoying this video series. I'm having a lot of fun making it. If you like what we're doing here, please subscribe to the Data Science Dojo YouTube channel. We're going to be producing content on a regular basis, and subscribing is the best way to keep abreast of all the things that we do. Next up, if you like what we're doing in general, feel free to follow us on social media. We actually produce a plethora of hand-curated data science goodness. And if you follow us on social media, you can tap into that data feed. And lastly, I hope to see you in one of our upcoming data science boot camps. So until next time, this is Dave Langer, and I'm wishing you very, very happy data sleuthing. Okay, what I've got here is an R environment, and I've ran all of the code through the end of video 2. And you can see here at the end of video 2, we verified that we had the correct proportions in our training set and our test set for our class labels between ham and spam. Okay. We then also talked quite a bit about representation And we're going to continue right on where we left off with those slides, where we're going to start taking a look at a few pieces of selected data out of the training set, so we can get some idea of what these considerations mean in practice. Okay, so here I'm going to go ahead and access the 21st entry in the training data set. And you can see here that it says, I'm back and we're packing the car now. I'll let you know if there's room. But most importantly, notice this right here. So this is an HTML escaped ampersand, right? Essentially these 5 characters should render just that on the screen. Now, this is often the case when you're working with text analytics, is that stuff that you see rendered in a particular way isn't exactly how it will be represented in the raw textual data that you will get. This is a perfect example. This is an escape sequence that actually denotes, hey, place this on the screen, but this is what you'll actually get. So one of the things that you'll need to decide as a data scientist working with text is, how are you going to handle that? So one viable approach is just to do a bulk search and replace. You can literally go through all of your code and say, look, if I see this particular sequence, go ahead and replace it automatically with that. Or alternatively, you could replace this whole escape sequence with the word and. That would work as well. Or you can do some various other types of techniques as well. You could strip off just the ampersand and the semicolon, leave the word amp in there. Now, unfortunately, amp is an actual word, so that your mileage may vary depending on the domain that you're working in, of which strategy is the best. Because this tutorial is very introductory, we're just going to go ahead and blast away these symbols, the ampersand and the semicolon. We'll leave the word amp in here, and we will assume, as we described earlier when we talked about stemming, we will assume that if the word amp, which is left over, shows up in any of the RSMS text messages, we'll be able to actually differentiate between amp as being a proxy for the word and, the ampersand, the symbol ampersand, or the word and, versus an SMS text related to maybe electrical domain, where amp is actually a measurement of the electrical domain. It's extremely unlikely, it's possible, but it's extremely unlikely that our SMS text data would have something from the electrical domain in there. So it may end up being okay for us just to use amp as a proxy for the word and. But like I said, you could certainly just do a wholesale search and replace. And a very viable strategy would be is just take this and replace it with the word and then you'd be good to go. Okay, so that's one example of the considerations that we talked about at the end of video 2. So moving on, we're going to go ahead and also take a look at a next piece of data here. And you can see that right there. A gram usually runs like ampersand LT semicolon hashtag ampersand GT semicolon. So these are essentially the symbols for less than and greater than. And once again, the same idea applies. The same idea applies. How do we actually want to treat this? If we replace these with the actual symbols less than and then greater than, they would likely get stripped out, because as we talked about at the end of video 2, we tend to strip out symbols. We typically only care about words. So we tend to strip out symbols and punctuation and numbers, digits, all that kind of stuff. So you may have to decide what you want to do here. For example, you could just leave LT. That would actually probably work out okay, because LT would be essentially the moral equivalent of you maybe doing a search and replace on this altogether and replacing this with the word less space than, or the 2 words less and than. Same thing here, because eventually what will happen is the machine learning model will pick up, if there's any signal in the textual data, it will pick up that LT essentially is a proxy for the concept of the less than symbol. Now we also need, as we mentioned in video 2, we got hashtags here. Now normally you pull them out. However, in this day and age of social media, you may want to decide, look, you know what, hashtags are actually kind of important, just like @ symbols may be potentially important. The example we used last time, which I'll repeat, is if you were doing sentiment analysis, sentiment classification on Twitter tweets, you would care very much about hashtags and @ symbols. But again, because this is a rather simplistic tutorial, we're going to go ahead and omit symbols. So we'll get rid of this, we'll get rid of this, we'll get rid of the hashtag here, the and all that. And essentially this will boil down to LT and GT. LT and GT. Okay. And lastly, another example to take a look at is a URL. Your credits have been topped up for http www.bubbletext.com. So this is an example of a URL. As you might imagine, URLs are extremely common in textual data these days, and it's something you really need to concern yourself with, because you can essentially decompose this in a number of ways. For example, you could get rid of these two symbols and just have HTTP and then have www.bubbletext.com. You could segment out the .com. You could segment out the bubble text. You could do all kinds of things with URLs. And as we talked about, Quantita as well as other packages and functions give you a wide range of functionality in terms of working with text, and especially things like special characters and hyphens and URLs and Twitter data, you name it. So you'll have to decide. Again, since this is an introductory tutorial, we're going to go ahead and take the tactic of, we'll probably just split this out as HTTP and then probably just use bubbletext.com separately. And what will end up happening if we do this consistently is eventually the machine learning model, if there's signal in the data, eventually the machine learning model will learn that HTTP is the proxy for some sort of website. Because more than likely, given our relatively small sample size, while it's possible, it's probably unlikely that we're going to have a lot of duplicate URLs themselves. So for example, bubbletext.com itself probably won't be highly predictive, but maybe there's a chance that, for example, the machine learning model may learn, hey, generally speaking, 70-80% of texts that have HTTP in them are spam, so that may become a powerful feature for us. So we'll have to take a look and see what happens as we go along in the video series along those lines. Okay, so there you have it. Just a few examples of the considerations that we talked about at end of video 2 regarding what you need to do for pre-processing your text data, the kinds of things you need to be on the lookout for. All right, moving on. Okay, so let's go ahead and actually load up the Quantita package here. And I hope I'm pronouncing that correctly. Maybe it's Quanteta, I'm not sure. But I'll just call it Quantita. Okay, so we're going to load up the library here, and then we'll run the help file on it. And you can see here, you get quantitative analysis of textual data. That's what Quantita is. And as usual, you want to click the second link over here in the help file, and you get this nice getting started guide. If you pull up the HTML, a lot of goodness here. Quantita is a super, super awesome package to work with. It's become my de facto standard package to work with now in R, supplanting some of the ones I used to use, like the TM package, the text mining package, OpenNLP, and things like that. There's a lot of goodness in Quantita, a lot of goodness, as we'll see in a second. Okay. So first up, we're going to go ahead and leverage the Quantita package's tokens function. So as always, tokens, there we go. Tokenize a set of texts. And as you know from video number 2, tokenization is just the process of breaking up a text document into chunks. And I won't drain this help file because, as you can see, there's a lot of goodness involved here. There's a lot of functionality, a lot of parameters, a lot of things that you can do. I'll show you an example here, and this is again under the 80-20 rule. It's 20% that's going to be helpful to you 80% of the time. So first up, we're going to ask Quantita to tokenize our text column on our training data. Hey, Quantita, go through all 3,901 observations, all 3,901, SMS text messages, and tokenize each one. And what I would like you to tokenize are the words. Now, there are different options available to you. For example, you can do individual characters. Super awesome, super interesting, but generally speaking, most of the time you're going to be using words, right? Essentially anything denoted by space in English language, right? So we want you to tokenize all of these texts into words. Now, per our conversation, per our slides in video number 2, we also have the ability to control at the fine-grained level how the tokenization process is actually executed. For example, we're going to go ahead and tell the tokens function to remove digits. Anything with a digit in it. A 0, a 1, 2, 333,413, whatever. If it's a number in terms of digits, remove it. Now later on in the video series, we'll probably swing back around and take a look at maybe engineering some features based on numbers. But for right now, we'll just go ahead and take them out and see how far we can get. Next up is we're going to go ahead and tell the tokens function to remove punctuation, commas, exclamation points, question marks, you name it. Please remove the punctuation. I don't want that. All I want are the words. I don't want the digits and I don't want the punctuation. I just want the words. Similarly, also, please tokens remove any symbols. So hashtags, @ symbols, ampersands, you name it, slashes, all that gone, $signs, all of them gone. We're going to remove the symbols as well. And lastly, anything that's hyphenated, we're going to remove the hyphens, essentially turn it into a space. So for example, if somebody had a some sort of hyphenated word, I'm trying to think of one right now, long term, right? So they had long dash term, long hyphen term. This would actually translate into the word long and the word term separated by a space. It would get rid of the hyphen. It would get rid of the dash in the middle. Okay. So we can ask Quantita to run this and it'll tokenize all of our text for us with these particular caveats in place. Get rid of the numbers, get rid of the punctuation, get rid of the symbols, and get rid of the hyphens. Okay. Now if I run this line of code, I get back a large matrix here. Excuse me, large DFM sparse here. Large DFM sparse. This is a particular object associated with the Quantita package, but it's actually pretty easy to work with. So for example, if we wanted to look at just the tokens of the 357th entry, and I picked this one for a reason, by the way, just so you know. If I run this, it'll actually spit out the tokens. Now you'll notice that this 357 corresponds to the text with the URL that we talked about earlier. So what we're going to do is we're going to run through a series of steps. This is known oftentimes as a pipeline. We're going to go through a text analytics data pre-processing pipeline here, step by step. And what we'll do each step of the way is run this same line of code over and over again, and we'll see how the raw text transforms over time. Right? So just to really make that pop, so here was the original text, right here, and here it is tokenized, right? Which makes sense, right? Essentially, it's just the words. But notice that we have HTTP and www.bubbletext.com as two separate things, like we were talking about before. This will allow the machine learning model to pick up on any signal if HTTP tends to be indicative of something, essentially ham or spam. Okay, so first step in the pipeline, we tokenize, no problem. Okay, next step, not surprisingly, as we talked about before and at the end of video 2, is we're going to lowercase everything. We're going to lowercase everything. And that's usually because, once again, our bag of words models tend to work very, very well without understanding things like capitalization, formal names of things. They tend to work really well without them. So generally speaking, we just lowercase everything to make sure that we have all of the words are into a single column. Because last thing we would want is two columns, one with your with a capital Y, and then another one, another column in our data frame for the word your without Y capitalized, lowercase y. So that would be kind of silly. So we just lowercase everything. So per our process, tokens underscore to lower does exactly what you would think. Convert the case of tokens. So you tokenize first using quantita, and then you can do various transformations on the tokens that you've produced. We're going to transform our tokens to be lowercase. So if we run these 2 lines of code, you can see here now the word your has been lowercase. And since everything else was already lowercase, it looks exactly the same. So this is two very common steps, almost de facto standard in a text analytics pre-processing data pipeline. Tokenize your texts, lowercase them. Okay, next up on the hit parade, stop words. Stop words. So stop words are, as we talked about in video 2, they are common words that are used in language that are typically used for grammatical sugar. They make the language flow, they make the language stream a little bit more streamlined, but in general, they don't add anything in terms of semantics, in terms of meaning, in terms of predictive power. So in the English language, the classic example is the word the. Typically, you want to remove stop words. Now, there's a note here in the comments which I should mention, which is quantita, as with many text analytics libraries, whether in R or Python or Java or you name it, will have predefined stop word lists. Now, depending on what problem domain you're working in, these stop word lists may be okay. They may have all the words on them and you say, fine, great, take them all out, I don't care. But sometimes you may actually care, and they may have more words in their list than you want actually taken out. So it's important to understand what is in the stop words list so that you can understand what the impact of that is in particular. So in quantita, you can get the English stop words that are included by quantita by default by using the stop words function. So let's pull up the stop words function. And we can access the built-in stop words. So for example, if we just ran this line of code here, you'll see here is the list of all of the stop words included by default in quantita. Basically, if quantita finds the word shan't, not likely, but possible, if it finds the word shan't, it's going to pull it out. It's going to remove that token because we don't want it anymore. So you go through this list, see if it works for you, and just be aware in general, anytime you're working with these libraries, make sure that the default lists of stop words will work for your particular problem domain. Okay, moving on. Tokens select. Let's look up that function because this is the function we're going to call. Select or remove tokens from a token object. Okay, cool. Makes some sense. Now this full line of code, this full function call makes a lot more sense now. Quantita, please select some tokens for me. Select from this particular object of tokens. In particular, I'm interested in these words here, the stop words, and I would like you to remove them. So I'm just going to go ahead and run this line of code again just to set our output up again. And if I run these 2 lines of code, now you'll see that before we had all of our stop words in here, right? We had all of our stop words in here. We had your and been and have and all that, and up and all that sort of thing. And you'll notice now we have a much smaller list of words. We removed the stop words because your probably isn't predictive. Because remember, the reason why it's not going to be predictive is because the bag of words model is positionally ignorant. So words like your and have and been kind of need position for them to actually have any sort of significance. And because the bag of words model by default basically messes with the token order, the word order, these words have a lot less predictive power than they would normally have. So we just remove them. And then what we get essentially is these remaining terms, tokens, credits, topped, renewal, HTTP, pin, bubbletext.com, and TGXXRZ, whatever that means. Okay. Now, lastly, we're going to go ahead and we're going to stem. Now, if you remember from video number 2, stemming is a super important process. Stemming is the way we take words that are very similar and we collapse them down into essentially a single term, a single column in our term frequency matrix. For example, we use the words ran, run, runs, and running as a particular example. What we would like is a process to say, okay, look, ran, runs, and running. Anytime you see one of those three words, change it into just the word run. And that way we essentially get this collapsing effect. Instead of having 4 columns for ran, run, runs, and running, we have just one single column that embodies the idea behind run. And in the example we used is in one context, the idea of run is essentially a human being moving as fast as they can under their own power. And we said, well, there could be other contexts as well, but that's okay because we can rely in the bag of words model on the other words in the document to provide context. And the example we used was computer systems, IT. If ran and runs and running were all related to computer systems, be okay. We could still collapse all of that down to the same single column. And other words like hard drive and CPU and disk and network and RAM, those sorts of things would then provide context to the model, to the machine learning model, that run in this case was not about a human being. Run was essentially about a computer system. Okay, so let's go ahead and look up the function tokens word stem. Okay, stem the terms in an object. Cool, right? Exactly what you would expect. So we're going to go ahead and use this function. Here's our tokens, and we're going to say, look, it's the English language that we're using. It's the English language that we're using. Now, if we run these 2 lines of code, you'll notice credits now became credit. Topped now became top. HTTP remains the same. Pin remains the same. Renewal became renew. And then these two, the bubbletext.com and tgxxrz, stayed the same. Now notice something really important here. Let's take a look at topped. Topped, tops, topping. These all have the same general concept of top. Notice how they get collapsed down. Same thing. Renewal, renewing, renews. All can get collapsed down to renew. Credits, credited, creditor, could all be collapsed down to credit. See how that works? That's stemming in action for you. So stemming is super, super powerful. And essentially what we've just walked through is the prototypical, almost de facto standard text analytics data pre-processing pipeline. Tokenize, lowercase, remove numbers, remove punctuation, remove hyphens and symbols, lowercase, get rid of stop words, and stem. Quintessential data pipeline. Okay. Now, of course, as I've mentioned several times before in previous videos, broad space text analytics is. You could certainly do other types of things as well, but this is, again, the 80-20 rule. This is 20% of the stuff that'll get you useful results 80% of the time. Classic pipeline here. Okay, so now that we've got our data pre-processed, let's go ahead and create our first bag of words model. Quantita has a function called DFM. Oops, you gotta spell it right, Dave. So, DFM, create a document feature matrix or a document frequency matrix, depending on how you want to think about it. But DFM is a function that will essentially take tokens, and as we'll see later, it can also take in just textual features as well. But it'll take in tokens, it'll take in our pre-processed tokens, and create for us a DFM, a matrix. Now, since we've already done a bunch of pre-processing, we don't need to set a lot of parameters on the DFM function. We just say, okay, DFM, please process our training tokens. You don't have to lowercase them because I've already done that. And you can go ahead and remove the stop words. This essentially is redundant. So we could just get rid of that actually because we've already removed the stop words up here. So we don't need to do that. Save us a little bit of processing time. And if we run that line of code, we get back an object. Now, the object itself isn't super useful, but Quantita provides, some functions that are actually quite worthwhile for us. There's a function called as.matrix. There's also one called as.data.frame. And these are functions you can use on DFMs that you return back, document frequency matrices that you return back from this function. And you can convert them into representations that are a little easier for you to work with. So for example, if I make this a matrix, it becomes just a standard R matrix, which I can then view in the spreadsheet view. So I'm going to run those 2 lines of code here. And what you're seeing is essentially the first 20 rows and the first 100 columns of our DFM. And you can see here, go and Jurong and point and crazy. That looks like probably been stemmed, right? C-R-A-Z-I. Avail, Bugie, maybe? Great, World, Buffet, you name it, right? There's a whole bunch of columns here. And essentially these are all columns for our distinct individual tokens for all of our terms. And you can see here counts. Like for example, promise, which I'm assuming this is the stemmed version of the word promise. Notice that it's a little bit mangled. There was 2, count of 2 in this particular SMS text message. Notice that most of the time you're going to see zeros. Most of the time you're going to see zeros. Okay, so there it is. We got a DFM. Great. Now, this is something that we're going to be talking quite a bit about in this video series. Check this out. So, you'll notice that our training data was originally 3,901 observations of 3 variables. We now have a feature matrix in our bag of words model that's much, much bigger. Notice that it's still 3,901 observations, right? Because the number of text messages does not change. But what does change is the number of columns. We now have 5,743 columns. So it's 3,901 rows deep and 5,743 columns wide. And as we know from this particular representation, most of the time, this is going to be really, really wide. This is only 100 columns wide. This is going to be more than 5,700 columns wide. And most of the time, most of the entries are going to be 0. So this is super interesting thing to remember. Another challenge of text analytics is that it creates your data, the size of data that you deal with explodes very, very quickly. Very, very quickly. I mean, we're only using SMS text messages here, and we're only using 3,901 of them. And text messages, generally speaking, are fairly small. But notice how many columns we get. Now, imagine if you were doing this on 3,901 Word documents. This would be 20,000, 30,000, 40,000 maybe, depending. Your feature space explodes dramatically. The dimensionality increases dramatically. If you're familiar with the term, text analytics very, very much suffers from the curse of dimensionality. That's one problem. The other problem is this idea that we see here, which is most of the time our matrices are going to be very, very large. They're going to be relatively deep because we'll have lots of documents, but they're going to be very, very wide. And most of the time the cells are going to be essentially 0. They're going to be empty. So this is a sparsity problem. So what we have is, not only do we have a large dimensionality problem, a curse of dimensionality problem, but we also have a sparsity problem. And we'll address that later with techniques like feature extraction. But these are things to know. Your data gets big in text analytics very, very fast. Very, very fast. Okay. And we can give you some example here. We're just going to take a look at the first 50 column names here. And some of these you'll recognize from the spreadsheet view, but I just wanted to print them out to the console to make them pop a little bit. Go and Jurong and point. Notice crazy. This is safe to assume that this is a result of stemming. Avail, also safe to assume the result of stemming. already. Look at this. Look how it changed the Y to an I. Also safe to assume the result of stemming. So notice that even though stemming was super useful in collapsing down the number of columns we need by standardizing our words, we still have a lot of columns here, 5,743 columns. Okay, so we're over time, so I'll go ahead and stop there. There you have it, a fully functioning standard, de facto standard text analytics data processing pipeline, data pre-processing pipeline. Okay, next time we'll actually build our first model over our feature matrix that we've just created. So if you like what we're doing, please subscribe to the Data Science Dojo YouTube channel. We'll be producing new content on a regular basis. Also, if you like what we're doing in general here at Data Science Dojo, feel free to follow us on social media. And lastly, I hope to see you in one of our upcoming Data Science Dojo boot camps. Until next time, this is Dave Langer, your host, and I wish you very happy data sleuthing. Hi, welcome. So we're in the RStudio environment, and we've ran all the code through the end of video 3, where we concluded with a nice document frequency matrix, a representation of our textual data in terms that R can understand. So as promised, we're going to go ahead and build our first model. So we're going to follow best practices in building our model, and we're going to leverage cross-validation as the basis for our model building process. Cross-validation is a technique by which we get maximum use of our training data, and it also allows us to create, ideally, representative estimates of what our model will do in production on brand new data that it's never seen before. And we do cross-validation to, as part of our process, to understand how well are our features going to perform. How well will the model that we use perform? How well will the model parameters that we're using perform? So on and so forth. So cross-validation is extremely central to our machine learning process. It is basically our workflow for determining, are we building a model that's going to be any good? Okay, and if you're not familiar with cross-validation, here's a link in the code to a wiki page on the Wikipedia website where you can find out more information about cross-validation. Okay, so to be able to perform cross-validation, we're going to need two things. We're going to need our features that we've created, right? We're going to need our document frequency matrix, or document feature matrix, as Quantita calls it. Essentially, this is our representation where each row is a document, and each column is essentially a token, a term, and the count of how often that particular term, that particular token, shows up in any given document in our corpus. And once again, a corpus is just the fancy term for the collection of documents. And in this case, for us, it is a collection of SMS text messages. Okay, so the data frame function, actually that should be as data frame. So the as data frame function will transform a Quantita DFM representation into a plain old standard R data frame. And so this is the first part of the equation that we need, right? These are our features, right? This is our representation of our textual documents in a way that R can understand. Next up, we're going to need to marry that with our labels because we're trying to predict ham or spam. That's the whole idea, right? We want to build a model that can accurately detect whether an SMS text message is ham, legit, or spam, illegit. So for a feedback mechanism to train the machine learning algorithm, we have to have the label. So we can use the cbind function and bind these two things together, and we'll call the resulting data frame that we'll create train.tokens.df. So if I run this line of code, it takes a second to run. But sure enough, if I expand this out over here, you can see here that I have my train.tokens.df, which is 3,901 observations, right? Good. That's the number of texts that we know are in our training set. And now we have 5,744 variables. Cool, right? Before we had 5,743, now we have 5,744 because we've added the label. Great. So now we have a good training set. So now here's the thing. You would think that normally we would be ready to go and start building some machine learning models, but often that's not the case. As I mentioned before, working with data and manipulating data and pre-processing data and wrangling data is part and parcel of machine learning in general, but it's even more important in text analytics because, quite frankly, text data tends to be quite dirty. So we're going to have an example of that. So if we said, okay, hey, let's just take a look at the names of this data frame that we've created, right? The names of this data frame will be basically the terms, the individual tokens that we parsed out as part of our tokenization process. And in particular, I'm going to pick out 4 here, and this is not at random, obviously. I have a nefarious purpose here. I want to illustrate something. So this says, okay, get all the names from the data frame, but I actually only want to look at these 4. So if I run these, you can see the names that we get. 8 a.m., second, for text, and try:\wall. So this is going to be a problem. This is going to be a problem because, quite frankly, these are not actually valid names for columns and data frames, strictly speaking. So if we use certain types of machine learning algorithms in our work, they're going to error. They're going to throw an error and say, I don't understand the name of this thing. 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 So we need to fix these up. We need to make these, we need to coerce them. We need to transform these names into something that essentially are legitimate column names universally across the board. Every machine learning algorithm in the world, not every machine learning algorithm in the world, every machine learning function in the R world, that's what I wanted to say, will recognize the names of these columns. And lucky for us, there's actually a function called make names. So that's worthy of taking a look at the help file. Make syntactically valid names. So this function implements some rules and processes for going through a whole collection of strings and saying, look, is this actually a syntactically valid R name or not? And if it's not, it'll fix it up. It'll fix it for us. So instead of having to go through all these by hand and figuring out which one of these columns out of the 5,744 that we have do we need to fix, we can actually just automate this process using the make names function. So I call make names. I feed it the names of my data frame. It fixes them all up. I then ask R to overwrite the existing names with the corrected names. And then we should be good to go. So I'll run that line of code. Sweet. Okay. Now we're ready. Our data is prepped, and now we can train our first model. So here's the thing. We're going to use stratified cross-validation. And the reason why we have to do that is because we have class imbalance in our data, right? Spam, while not exceedingly rare, spam is actually quite less prevalent in our data set than ham is. So that we have a class imbalance problem. So we want to make sure that as we do our cross-validation, which involves random sampling, that each sample that we take is representative in terms of the proportions of ham and spam. That's known as stratified sampling. So specifically what we're going to do is we're going to implement stratified folds for 10-fold cross-validation, which we're going to repeat 3 times. So what this code will do here is actually create for us 30 random stratified samples, because we're going to do 10-fold cross-validation repeated 3 times. Now, you may be asking, if you know about cross-validation, Dave, hey, I get the 10-fold part. That's totally cool. I grok that. Why am I doing it 3 times? And the answer is because if we can take the computational hit, if we're willing to take the time and effort to actually run cross-validation multiple times, we will actually get more valid estimates. We'll get more looks at the data, therefore our estimation process will be more robust. So we're going to do 10-fold cross-validation repeated 3 times with stratified samples. I also like to use repeated cross-validation when I can, especially when I have some class imbalance, because you just never know with class imbalance how that's going to work out. So this is a reasonable strategy to take, assuming that you're willing to take the computational hit. And we'll see later in the code, I'm going to do a few things to actually make this a little bit of a less of a burden for us. And even later on in the series, we'll actually reduce the size of our data down using feature extraction so that we can keep running these cross-validation, these repeated cross-validation processes with more and more complex models without us, having to wait like hours and hours and hours and hours for these models to train. Okay, so first up, we're going to use the create multifolds function. And this is a cool function from the Caret package. So let's go ahead and look it up. So it's one of the data splitting functions. And what create multifolds does is essentially allows you to create multiple stratified random samples. So basically, create multifolds is a wrapper around the create data partition function. The create data partition function is the basic function in Caret that allows you for creating stratified random samples. Multifolds just says, look, you know what? Just create me a bunch of folds. Bunch of folds. So we have to tell it, okay, fine. I want you to create multifolds for me, Caret. Here is the class label that I want you to use. It needs the class label. It needs this factor variable so that it can actually calculate what the proper proportions should be in each of the random samples, in each of the folds. And then we also have to tell it essentially how many folds we want. We say, okay, look, I'm going to be doing 10-fold cross-validation, and by convention, this is referred to as k-fold cross-validation, and the k is 10. We're doing 10-fold cross-validation. And we tell it how many times we want to repeat the process. We want to repeat a process 3 times. And so it'll say, okay, 3 times 10 is 30. I will create you 30 random samples where they are stratified. Each of the random samples will be proportional. Will be proportional in terms of the label distribution. Okay, cool. So next up, we have to then tell Caret, cool, how do I actually want to start processing my training? How do I want to do my training process? So this creates my folds. This just gives me the way to actually set up my data for the training, but it doesn't specify the process by which Caret will execute the training. That's what this call does here, train control. So this one's also worthy of a lookup. Okay, train control. This is, I'm not going to drain this help file. There's a lot of stuff in here. But notice that what this should tell you is, yeah, it's a big, complicated function, but there's also a lot of power here. Caret gives you a lot of fine-grained control regarding your machine learning model building process. So we're going to use an actually relatively simple setup. Hey, Caret, we want you to build our models using a repeated CV, repeated cross-validation process, where the number of folds is 10. The repeats is equal to 3. Now, you could just leave the code right here. You could just drop a closing parenthesis right here, leave this part out, and you'd be good to go. And Caret would be off to the races and happy to train you a model. But since we want stratified cross-validation, we need to specify the actual folds. Because if you don't specify this, by default, you're not going to get stratified cross-validation. So this is the mechanism by which we can say, okay, Caret, look, I've already pre-calculated all of the folds that I want you to use for the 10-fold cross-validation repeated 3 times. Please use these folds. And it'll say, okay, cool. And since we've built them to be stratified, we're good to go. So I'll go ahead and run this, and we're setting the seed obviously to make sure that you see at home what you see on the video. Okay, so cool. We've got our process set up. We're going to do 10-fold cross-validation repeated 3 times, and each fold is stratified, meaning that the proportion of the labels will be the same. Great. So here's the first trick that we're going to do. As I mentioned in the beginning of the video, I reserve the right to add packages to the mix. I am going to go ahead and do so right now. I'm adding a package to the mix. In particular, I'm adding the do snow package. So do snow is a package that you can use to run training in Caret in parallel. So that's the first thing that we're going to do to speed up our cross-validation runs, which is we're going to train them in parallel. So for example, we have 30 folds. So if I had a big enough machine that had 30 cores, 30 CPUs in it, I could actually train each fold all at once. I have 30 cores, I assign each fold to one of my cores on my computer, and I'm off and running. Now a 30 core machine is a very, very big machine. So most people aren't going to have access to that, but you get the idea, right? If you have a machine that has multiple cores or is hyper-threaded, so that, for example, if it has 2 cores, but it actually can run 4 threads simultaneously, sweet. This will make your cross-validation go faster because essentially you get linear scale out. If I have 4 cores instead of 1 core, I should be done in about a quarter of the time that it would take me to use only 1 CPU. And that works out to be about right. So we're going to train in parallel. I like using Deuce Snow. There are other packages you can use to do this, but I like using Deuce Snow because Deuce Snow works on both Windows and Macintosh. And Linux, I would assume as well, although I haven't tested it, out of the box. So I use Deuce Snow. So we're going to load up the Deuce Snow package. And for Grinsies, I'm going to go ahead and time the execution of this code, just so that you can see it. Now, here's something that's super important. Notice I put this in the comments, the warning here. The code by default, when you get it from the GitHub, is set up for a workstation or a server class machine. Specifically, it is set up to run on 10 cores, 10 logical cores. Now, as I record this video, I'm running on a laptop that is far, far less powerful than that. So I'm going to change this number to 3 because my laptop is a dual core hyper-threaded, so it has 4 logical cores. I need to keep at least 1 core for the operating system. So I'm going to only get 3 cores out of this. Now, as you might imagine, this is going to run for a while. So what I will do is we will step away from the video for a while and let this thing run, and then we'll resume back up after it's executed, and you can see how long it takes to run on my laptop. Now, just for preview of coming attractions, when I ran this on my workstation with 10 threads with 10 cores, it only took about 4 minutes. Now it's going to take approximately 3 times longer than that to run on my laptop here. So it should take 12 or so minutes, but we'll see for sure. But before I execute that code, let's go ahead and just walk through everything that we're going to do. So this first line of code is just a poor man's way of just doing performance testing. I'm asking R to give me the current system time, and I store that so that later on I can find the difference between when I started and when I ended. That gives me my elapsed processing time. Now what we're really interested in is these 2 lines of code here. Make cluster and register Deuce Snow. So this first function right here actually creates a Deuce Snow cluster for doing work in parallel. And the type that we're requesting is a socket cluster. Now if you're not familiar with sockets and clusters and that sort of thing, it's okay. The easiest way to think about this and the most intuitive way to think about this is make cluster effectively creates in the background on your computer multiple instances of RStudio. It's not 100% correct, but it's close enough for our purposes. It creates multiple instances of RStudio and then allows Caret to borrow those instances of RStudio and use them all at once to do its processing. That's effectively what this does. So I'm saying, okay, look, spin up behind the scenes 3 instances of RStudio and make those available to Caret to use if it would like to. That's what this does, right? And the higher this number goes, the more RStudio instances are created behind the scenes and the more CPU that I will use. Just so that you're aware, this setting right here will make my laptop run at about 96% CPU. So be really, really careful with how you set this. Okay, after the cluster is made, I then ask the Deuce Snow package to actually register the cluster. Now this is super, super important. This line of code actually alerts Caret that these instances of RStudio are available for it to use if it so chooses. This is not enough. Just building the cluster is not enough. You actually have to register it. And then once it's registered, Caret will recognize it and say, oh, okay, you want me to train in parallel. Cool, I can totally do that. And that's what will happen. Okay. So next up, we're going to use the train function. Now this is also worthy of a lookup in the help file. So the train function in Caret is awesome. It has tons of goodness in here. It allows you, this is the main function that actually builds your model. So I won't drain the help file, I'll just parse what we've got going on here. So first up, notice that there's this method variable, or this method parameter, excuse me, on the train function. This tells train what kind of machine learning model that I would like to build. So right now I'm going to use an rpart algorithm, but I could quickly change it to a random forest. Or I can make it an XGBoost decision tree. This is the power of Caret, is that it's highly configurable. All things being equal, with very few minor exceptions, it's very, very simple for me to build up a pipeline in Caret and just swap out the model, the algorithm that I would like to use by just changing this string value. Okay, cool. So the reason why we're using rpart trees is because an rpart is a single decision tree. So I said there was a couple things that we were going to do to speed up our cross-validation processing here in the beginning of the video series. One is we're training in parallel, always a good idea when you can do it. And two, we're going to use single decision trees, because single decision trees actually train relatively fast. A random forest is actually, not surprisingly, a collection of trees. So random forests would take a lot longer for us to train. And given that our data is actually relatively, it's not big data, quote unquote, but it's non-trivial in size. It's 3,901 rows of over 5,700 columns. That's no data to sneeze at, as it were. So we're going to try and speed this up by using a simpler algorithm just to kind of give you some intuition of what we're going to be doing over the course of the series here. Okay, so we're going to be using single decision trees, rpart trees. This function, this formula, my apologies, this formula says, look, predict label, and predicted by all the rest of the data in the data set. That's what this dot means. Predict label by all the rest of the data. And the data is stored, not surprisingly, in the data frame that we created, which is in the rest of the data. This dot is essentially our term frequencies for all of our documents. That's our feature set. We then also tell the train function, hey, here's the train control. This is the process I want you to follow. Notice how cleanly separated the process of doing your training is from the actual model, because those two are separate. Right? I define my cross-validation parameters in my data totally separately and independently of the algorithm I'm using. Cross-validation works exactly the same for random forests and decision trees as it does for logistic regression as well as artificial neural networks. So they're abstracted from each other in Caret. Okay, so that's our train control. And then lastly, this parameter right here tells the train function to say, look, you know what? Please try seven different values, 7 different configurations of the rpart algorithm. Try 7 different ways to configure rpart and find out which one of those 7 configurations works the best, and that's the one I want you to use, which is pretty nice. This is known as hyperparameter tuning. So this automatically tries 7 different values for a hyperparameter for the rpart algorithm and finds which of those 7 values works the best on the data and lets you know what that is and builds you a model using that. Cool. Lastly, once we're done training, we need to stop the cluster because we're done using those RStudio instances behind the scenes. So we might as well exit out of RStudio and free up the resources on the computer because it's a waste. So stop cluster, then do that. And then lastly, I calculate the total execution time, and we can take a look at our cross-validation results. So now I'm going to go ahead and highlight all of this code and run it at once. And then we will pause the video, and we will cut out the video, and then we'll resume back when the processing is done. And we can see how much more slowly this ran on my laptop than it did on my workstation. And that'll give you some approximate idea of how long this may take on your computer. Okay, so I'm going to go ahead and run this code, and we'll come back once the code is done executing. Okay, we're back. Surprisingly enough, my little laptop here actually ran all of the code here, ran all of the iterations of the cross-validation in parallel, only using 3 logical cores in a little over 7 minutes, which is not bad because my big beefy workstation took 4 minutes to do it. So that's not exactly what I expected. But anyway, you get the idea, right? Doing this work in parallel is a good idea because even on my laptop, this would have taken quite a bit longer if I'd only used a single core. Okay, so let's take a look at, if I run this line of code, I'll get this output that we'll see scrolling up here. And I'll just go through it step by step. Okay, so what we've got going on here is the output from Caret. And it tells us a lot of good things. So first up, what it tells us is, okay, Dave, what did you actually do? Well, I ran cart. I ran a cart tree. And it talks about, I had 3,901 rows and I had 5,743 features. And I had 2 classes. I had ham and spam. And then it talks about the process. It said, Dave, you didn't do any pre-processing, which we didn't because our data was okay. And here's the resampling method used. We used cross-validation, specifically tenfold, repeated 3 times. And it gives us a summary of the various sample sizes used. Notice that they're all about the same. Okay. Now notice the next step, there are 7 distinct entries here. Right, 7 distinct entries for the CP parameter. I won't go into what the CP parameter is. Just know that it is a knob, a dial that you can turn up or down and adjust how the cart algorithm works. And different levels of this particular value are going to give you different results. So for example, if it's set at 0.325, my average accuracy on my tenfold cross-validation repeated 3 times was around 88%. But notice that Caret actually tells you what the best value of the 7 actually was. It says, look, you had the best accuracy, you had the optimal model when the CP value was at 0.021032.5, which is this right here. And notice that we're at 94.3-ish% accuracy. Well, that's not too bad, right? Right out of the box. Just a very simple representation, just a very, very light cleaning of our data. The simplest text analytics data pre-processing pipeline you can think of, we did, and we got 94.3% accuracies, which is not too bad. Now, in future videos, we will see how we can improve this in a couple of different ways. One is, in the next video, we will use the mighty TF-IDF, the mighty term frequency inverse document frequency, to push this accuracy up a little bit by transforming the nature of the data that we have. After that, we'll then take a look at adding what are known as n-grams, which will add more features to our model, and we'll see how that will affect our performance going forward. Ideally, it will improve it. We'll have to see. And then after that, we will do feature extraction. We'll do singular value decomposition, which will actually take all of this ever-exploding number of columns that we have and shrink them down to try to find the underlying patterns of behavior amongst the terms in our text messages that actually most closely identify ham versus spam. And then lastly, we'll do some feature engineering using text lengths and some similarity scores, and that'll end our feature engineering. And at that point, we'll shift over from saying, okay, look, this is the set of features that I have. Can I use better algorithms? And that's when we'll move into the mighty random forest and see if the mighty random forest will actually improve our overall performance over using single trees. And that'll conclude the series. Okay, so this is a good point to end. Thank you for watching. If you have any questions at all, please, please, please use the comments section. We at Data Science Dojo monitor the channel on a regular basis, and we try to answer any and all questions. Also, if you like what we're doing here, if you like the tutorials, please subscribe to the channel. We'll be producing content on a weekly basis, and hopefully we can produce more things that you will find useful in your daily work. And lastly, I hope to see you in an upcoming Data Science Dojo bootcamp. Until next time, this is Dave Langer, and I wish you very happy data sleuthing. Hi, welcome back. So in the last video, we illustrated how we could take our document term matrice representation of our text data and use it to build a powerful machine learning model. Specifically, we illustrated in the last video that you could take our document term frequency matrix and train a single decision tree using 10-fold cross-validation repeated 3 times and produce an estimate of accuracy of more than 94%. So generally speaking, what that means is that if we built a model, a single decision tree model, and put it in production, we would expect it to be able to predict correctly legitimate text messages, that is ham, from illegitimate text messages, that is spam, more than 94% of the time. It should do that correctly more than 94% of the time. And that's pretty good. That shows us that document term frequencies matrices work. And more specifically, it tells us that this bag of words model, that is, taking our free-form textual data and running it through a data pre-processing pipeline consisting of things like stop word removal, tokenization, stemming, so on and so forth, actually works. Right? It's powerful. It works. It allows us to ignore things like context. For example, do we mean running in terms of a human being moving as fast as they can under their own power versus the IT context of a computer program running? We can actually say, look, these things don't matter. We can rely on the bag of words model to differentiate between those two contexts. We also have shown now that word ordering, we can get a lot of power out of this representation without worrying about word ordering. Okay, cool. But here's the thing, as powerful as this representation is, there's still some room for improvement. We have some issues that we can address. So first and foremost, there's this idea that longer documents will tend to have higher term counts. And this is actually a relatively intuitive idea. Let's take the example of 2 documents, and they're in the sports subject area. More specifically, they're about baseball. And let's say one is a baseball article from Sports Illustrated magazine, and let's say it's around 1,000 terms, or it's 1,000 words, let's say, total. And then we'll have the book Moneyball, which is also about baseball. And let's say, and I don't know for sure, but I'm making this up. So let's say the book Moneyball is 20,000 words. Now they're both about the same subject area, baseball. So we would expect very specific terms related to baseball to occur in both documents. Terms like ballpark and umpire and strike and bunt and RBI, you name it, right? There's a bunch of terms that are specific to baseball that we would expect to co-occur in both the Sports Illustrated baseball article as well as the book Moneyball. Now, intuitively, we will also realize that where those terms occur in both documents, it's far more likely that Moneyball will have higher counts of those terms just because Moneyball is just a longer document. The word umpire is just more likely to show up more frequently in that document, in the Moneyball book, than it is in the Sports Illustrated article. That's just intuitive. So that's one thing that we need to address. That would improve things. The other thing that we need to address is this idea that terms that appear frequently across the corpus aren't as important. So for example, let's say that I have a collection of documents, and once again, we'll just use the example of American baseball. And let's say I have every article about baseball that ever appeared in Sports Illustrated magazine, and that is my corpus. That is the collection of my documents. If my subject area is limited only to baseball, and more specifically, articles from Sports Illustrated magazine about baseball, it's highly likely that certain terms will show up in many of the documents. For example, the word umpire. It may be entirely possible that the word umpire may show up in 70% of the documents, 80% of the documents. Or here's an even better example. It's extremely probable, it's extremely likely that the word baseball itself will show up in 100% of those documents. It's not unreasonable to assume that Sports Illustrated articles about baseball, every single one of them will contain the word baseball, the term baseball. As such, you could make an argument that in that particular case, the term baseball isn't that important. If it shows up in every single document, how important can it be? It's not providing you a lot of information. It's not providing you a lot of information. So that's another thing that we can address. So here's the thing. We can improve upon this bag of words representation. We can improve upon our document term frequency matrices if we can achieve the following. One, if we can normalize documents based on their length. Whether I'm talking about a 1,000-word Sports Illustrated article about baseball, or I'm talking about a 20,000-word book like Moneyball, if I can normalize their term counts across both of those documents, irrespective of length, it puts those two documents on equal footing. And that's a good thing. That's a good thing. Because usually we're not worried about so much about document lengths. We tend to worry more about the words that show up and how frequently and how important they are within the document themselves. So normalizing the documents based on their length will help us with that. Second, if we can penalize terms that occur frequently across the corpus, that will also help us in our representation. That will make it more powerful. Again, for example, if my corpus is every baseball article that ever showed up in Sports Illustrated magazine, and the word baseball shows up in 100% of those documents, if I can penalize that term so that all of a sudden it looks less important, that would also help out. Because the term baseball is not likely to be predictive. If it's in every document, how can it be predictive? By definition, it's not going to be very predictive. So if we can adjust our matrices to accommodate these two things, it'll increase its power. Okay. Enter in term frequency inverse document frequency. This is exactly what TF-IDF addresses. So first up, let's take a look at term frequency and what does it mean. So we're going to get a little bit mathematical in these slides, nothing too serious, so hang with me on this. So if we let a function that we'll call FREQ, or frequency, the function frequency as defined by T and D, and we let that function be the count of the instances of term T in document D. So if we just define a function that says, look, for any term in the document, just count up how many times it shows up. That's basically all this means, right? So for example, if it walks like a duck and it quacks like a duck, it must be a duck. The frequency of the term duck in that document is 3. The word duck shows up 3 times. So further, let's define another function called TF for term frequency. And the TF for T and D would be essentially the proportion of the count of term T in document D. So for example, if I had a particular term that showed up in a document 4 times and the document was 10 words long, or had 10 terms in it, after my processing pipeline, after stemming and stop word removal, let's say, then that particular term represents 40% of the document, 0.4. That would be our expected value for that particular term, for the term frequency in that document. Pretty simple. Just what's the proportion of the term in the document, right? So we can represent that mathematically using this calculation. So the term frequency of T given D is essentially the frequency of T in D divided by the sum of all of the frequencies of all the T's in the document. This essentially just gives us the percentage, the proportion. So that's pretty simple, right? And notice how this achieves that first goal. This normalizes across documents. It essentially says, look, you know what? I don't care how long your document is. Just tell me what the relative proportion of this particular term is vis-a-vis the entire document. So again, if you take a 1,000-word document that is a article about baseball from Sports Illustrated, and you compare it to the book Moneyball, you can now say the term umpire is on more even footing, because irrespective of which document is longer, you're going to talk about how prevalent is umpire in terms of the proportion of the document in total. So it normalizes. So this is a way to normalize the term frequency across documents of different lengths. Sweet. So the math works out. It helps out our goal. Okay, next up we have inverse document frequency, or IDF. So if we let capital N be the number of documents in our corpus, that is the number of documents in our collection. So for example, if I had 1,000 articles about baseball from Sports Illustrated in my corpus, that was my collection of documents I was working with, capital N would be 1,000. If I define a function called count of t, where count of t just represents the number of documents in which term t appears, this is also relatively intuitive. Let's say, for example, once again, I have 1,000 baseball articles from Sports Illustrated magazine. And let's say that the term I'm interested in is the word baseball. And as we surmised earlier, let's say the term baseball shows up in every single one of those documents. Count of t would be 1,000. Baseball shows up in every single document in the corpus. There are 1,000 documents in the corpus, ergo count t is 1,000. Pretty simple. So given that, the IDF is essentially the log of the number of documents in my corpus divided by the specific count of a term. In how many of the documents across the corpus does the term actually show up in? That's all it is. So once again, notice that if I had capital N be 1,000, right, because I had 1,000 Sports Illustrated baseball articles, and then I said, look, I'm looking for the count of the term baseball in my corpus, and assuming that baseball shows up in every single article, I would have count t is also 1,000. So N would be 1,000, count t would be 1,000. 1,000 over 1,000 is 1, and the log of 1 is 0. Notice how this math also works out. Term frequency normalizes, that was our first goal. This one discounts, penalizes terms that show up frequently across the corpus. And in particular, if a term shows up in every single document in the corpus, this mathematical equation essentially gives it a weight of 0. You can't get much more penalized than that. Essentially, it says, look, baseball is useless. If baseball shows up in every single document in your corpus, there's no information in there that you need to worry about. So cool. We now have a mathematical representation of how we can address some issues in our document term frequency matrix representation. Okay, so this leads us to the mighty TF-IDF. So if we combine TF and IDF, we can enhance our document term frequency matrices to make them more powerful. And TF-IDF is very simple. It's simply the TF of a term for a document times the IDF of that term. And we'll see what that means here in a second in actual R code. Okay, so here we are in our R environment, and I've ran the code through essentially the end of video number 4 to set up the environment. So the first thing that we need to do is, if we're going to use the mighty TF-IDF in our solution, and I would suggest that we should try it out, because most of the time, almost all the time, TF-IDF actually helps you out. So it's actually, generally speaking, a de facto part of most text analytics data pre-processing pipelines. You lowercase, you remove stop words, you remove numbers and symbols and hyphens, you stem, and then you run TF-IDF. That's a prototypical data pre-processing pipeline in text analytics. So we're going to go ahead and hand roll our own TF-IDF functions, and we're doing this for 2 reasons. One, it's educational and illustrative of what's going on behind the scenes, and 2, it allows us to calculate our IDF values for all of the terms in our training data, so that we can cache that, we can keep that vector of IDF values and use it later to transform our test data into comparable representations. And that's super important, and we'll talk more about that later, but just to give you a heads up. Okay, so first up, we need to define a function in R for calculating our term frequency. So here's the code that we can use to do that. And notice that it's pretty simple, right? If a row in my document term frequency matrix represents a document, which it does, it's pretty easy. Take every member of the row and just divide it by the total of the row. right? R does vectorized processing, so this will essentially say, go through the first column, divide whatever's in that first column, that first cell, the first vector, the first value in the row, and divide it by the total of the row. And this just gives me the percentage across all the individual terms in the document. Nothing too difficult here. So we can just run that code and create our function. Sweet. Now, IDF, inverse document frequency, is a little more complicated, but not astronomically so. First thing we do is we say, okay, look, we do TF on rows, right? We normalize across each individual document, which is our rows. In IDF, we calculate by column, right? Because we want to actually look at the terms now. Term frequency is document-centric. IDF, or inverse document frequency, is corpus-centric or column-centric. So notice how we're working on columns versus rows. So the first thing we need to do is we need to calculate for each one of the columns, how many documents are there? What's the length of the column? Now, generally speaking, this is going to be the same for every column, obviously, because we have a matrix. And then our document count is exactly what you would expect, which is, okay, just give me the number of rows where the column is not 0, right? The count of this particular term for a particular document is more than 0, right? That's what we care about. That's what we care about for this particular term, and how many documents does it appear. That's what this code does. Cool. And then lastly, we take the log. Now notice in the slides, I used log generically and I didn't specify a base. Technically, it doesn't really matter. We'll use base 10 here because that's actually commonly used in implementations. For example, if you want to compare this code that we're going to be using to the quantita TF-IDF function, this code here will generate essentially the same output as quantita does if you make sure that quantita also normalizes, which it doesn't do by default. So if you want to double check this with the quantita TF-IDF function, you can go ahead and do so. Set the normalization to true on that, and you will get exactly the same numbers as we'll see this code generates. Okay, so now we've got TF and IDF. So if I run this function, this will generate my IDF function. And then lastly, we combine the two into our own custom TF-IDF. And as we saw from the slide decks, that's pretty easy. I just multiply X by IDF, and good to go. Actually, you know what? Let's change this. Let's make this even more specific. Let's make this TF instead of X times IDF. That's better yet. Cool. Look at that. Nice. Okay, so now we have our TF-IDF function. So we have all of our functions that we need to make this work. Okay, so first up, we have to do some matrix transformations. Right? We have this matrix, this train tokens matrix, right, from last time. So if I do a quick view on that, I'll just highlight this real quick and pop that bad boy in here. It'll take a second to pop up in the spreadsheet view. But you can see here, right, this is just all of our terms across the top and all of our documents down the side here, and just the individual counts, right? 111, 212, so on and so forth. Great. We need to transform that. First step, obviously, is that we have to transform all of the documents using the TF function. We need to normalize all of our documents. We want to get rid of that. We want to address that first issue, which is we want all of our documents, irrespective of length, to be on equal footing. So we need to normalize. So how we do that is we use the apply function. If you're not familiar, you can always pull this up in the help file, and apply functions over array margins, right? This essentially says, look, you can have R automatically apply a function over and over and over again, either against the rows or against the column of the matrix. This is a way that you can loop in R. If you're familiar with programming, this is essentially an R-style for loop. So here's what we can do. We can apply our term frequency function against this matrix, and the one says do it against the rows. So if I run these two lines of code here, what's going to happen is that it's going to apply the function against the rows. Now you'll notice something really super interesting here. I ran the dim here so that you're aware of this. Now originally, if I do dim on this matrix, notice that I had 3,901 rows and 5,743 columns. Notice that this is the output of this function call has transposed our matrix. It's essentially swapped the columns for rows. And in linear algebra, that's known as transposition. I've transposed the matrix. Notice I haven't lost any data. It's just basically swapped the rows for the columns. Just be aware of that. So we can quickly take a quick view at this and just see how things have been swapped from last time. Now the rows are now columns, and what used to be columns are now the rows. But notice that the numbers are now different. Notice that these used to be ones, right? This is our first document here. Whoops, excuse me. This would be our first document right here. And notice that these used to be ones, but now they're 0.0625 instead. These have been normalized, right? They've been normalized, which is cool. Okay, so next up, we need to calculate our IDF vector. And remember I said earlier in the PowerPoint that we're going to want to cache that. We're going to want to store it because we want to transpose, well, not transpose, we want to transform. We want to be able to map any brand new data once we go into production and new documents come in, new text messages come in. We need to be able to transform those new text messages into the same space that our machine learning model was built. So to do that, we need to make sure that we store, we calculate the IDFs and we store them, because that is the fixed set of IDFs that we use to train our machine learning models. Therefore, in our test data, any brand new production data, we need to use those same IDF values to transform new data that the model's never seen before into a space that it understands. Okay, so what we're going to do here is we're going to go ahead and use the apply function again against the matrix. But notice this time we're going to apply the IDF function, the inverse document frequency function, against the data set. And this time, instead of the rows, we're going to go against the columns, right? Because that makes sense, because IDF is not a row-based calculation, it's the column-based calculation. So if I run these two lines of code real quick, it'll take a second, and you'll notice that I get back a single vector, a single numeric vector that is 5,743 in length, and you'll notice here are the individual IDF calculations that correspond to each one of our terms. Sweet. So now I've got the TF, I've got my documents normalized, and then I also have the IDF values that I use. Okay, so not surprisingly, here we go. So we can apply the function again. Now this is going to get a little more interesting. We're going to apply on our data frame, right? Not our data frame, on our transformed, our normalized matrix here, right? This is our TF normalized matrix. And notice here, because the matrix was transposed, we're going to run against the columns, and we're going to apply the TF-IDF function to it, and we need to pass in our IDF vector values. So now if I run this, take a second, I'll notice that I've still maintained my transposed matrix. Remember, we originally had 3,901 rows and 5,743 columns. We've still maintained this transposition, which is why we oriented to the columns. But if we take a look at the data now, we should see that it's been transformed. Notice that the values now for text 1, they used to all be the same because they were normalized to that individual document vector. Now they're rationalized. They have been combined with the TF and the IDF values to achieve our two goals. The goal of, 1, normalizing documents based on their length so that we can compare documents on equal footing, and then 2, rationalize individual terms in our corpus to say, look, those terms that appear more frequently are going to be less useful than those terms that appear rarely. So for example, by definition, higher numbers here will represent things that appear less often. So for example, the word go, the term go, it's intuitive to us that it appears quite a bit because you'll see the lower score here. Whereas Jurong has quite a bit higher score. And intuitively would say, yeah, that makes sense. I would expect that in English SMS text messages, the word go, the term go, the token go, should happen to occur a lot more often, generally speaking, than the term Jurong. Okay, cool. So now we've got a mighty TF-IDF matrix. Excellent. So now here's the thing. We need to transpose it back, right? We need to get it back to be a document frequency matrix. Right now, it's actually in a term frequency document matrix format where the term frequencies are the rows and the documents are the columns. That's okay. You'll see most of the literature or a lot of the literature in text analytics actually use that representation. However, when you get ready to train a machine learning model, you'll need to flip it back. So that's what we'll do here. We'll use the T function, and if you run the help on that, the T function is a matrix transpose. So that's exactly what we'll do here. We'll go ahead and transpose our matrix. And notice we get back to our original representation. 3,901 documents with each one having 5,743 columns. And if we just view that real quick in the spreadsheet view, all is right with the world. We've now invoked the mighty TF-IDF on our document term frequency matrix, and we've got all kinds of predictive goodness in it now. Okay, but let's test it out. Let's test it out. Let's make sure that, in fact, I get the goodness that I expect. But we've got a little bit of a problem that we need to deal with here. When we invoke TF-IDF on something, we need to actually check for a particular degenerative case. And that is the case of after we've done all of our pre-processing, we've removed all the stop words, we removed all the symbols and numbers and etc., and we've stemmed, it's entirely possible that there's nothing left. There's nothing left. We basically remove everything from the string. So imagine if I just put a bunch of emoticons in a particular text, right? A bunch of smiley faces made with colons and dashes and parentheses and things like that. Those are all symbols. So our pre-processing pipeline would strip those all out. So we could actually have empty strings. Now, when we do a TF-IDF calculation on an empty string, we'll actually get essentially errors from R. So to check that, we can actually say, look, you know what? Go through my new mighty TF-IDF matrix and check out to see if there are any cases that are not complete. So for example, anytime there's an error in the calculations of TF-IDF, I'll get not a number as a result, and that will trip this complete cases function. And this is a way for me to test to see, look, did I in fact have any text messages where essentially I stripped everything out and there's nothing left, so I have essentially an empty string. So we'll go ahead and do that. And you'll see, yep, in fact, I do find cases that are not complete, in fact, incomplete cases. And if I go look at the original text messages of some of those, here's what I get. What are you doing? How are you? Well, we know these are punctuations, so we'll strip those out. And we also know that every one of these is a stop word. So therefore, this particular text gets essentially turned into an empty string from our pre-processing pipeline. In a similar way, this is just numbers, so our pre-processing pipeline will basically strip that all out, making an empty string. That's just a bunch of symbols, so our pre-processing pipeline will strip those all out and make it nothing, and so on and so forth, right? Same thing here, so on and so forth. Okay, so here's what we do. We can fix those incomplete cases up, because if we try to train a machine learning model with incomplete cases, most of the machine learning models that you use in R will throw an error. So we need to fix these up. And that's pretty easy to do. All we do is essentially say, look, for any row in my TF-IDF matrix that is incomplete, just replace it with all zeros. Just replace it with all zeros. It should be fine. We don't want to get rid of those rows because it's entirely possible that text messages that are essentially get turned into nothing by our pre-processing pipeline may actually be predominantly ham, right? Legitimate. These are probably legitimate text messages. These are probably legitimate text messages. Very likely. So we don't want to lose those records. So we just replace them with all zeros. And if there is any signal in the data, what will happen is that our machine learning model will pick up on that and actually show us what's going on. Okay, so next up, now that we've identified that we have some incomplete cases that we need to address, let's go ahead and fix them. So simply what we'll do is we'll just say, look, any place in my IDF that I've got missing data, I'm just going to go ahead and replace that with all zeros for all the reasons that we just described. So if I run on these lines of code, you can see here, I've still maintained my dimensions. Everything's great. I've got 3901 rows and 5743 columns. And notice now that I have no incomplete cases. I've taken those instances of those documents, those text messages where our pre-processing pipeline has essentially stripped all of the data out and made them empty strings. I've now replaced those with zero. So again, if my machine learning model can do it, it will learn some signal. Okay, last up, what we'll do is we'll clean up our data frame names, just like we did before, and get ourselves a nice, clean data frame. Now this time, instead of it just being the raw term frequency counts for each of the documents, it'll be the mighty TF-IDF adjusted scores for each one of those terms in each one of the documents. Okay, so now we're all set up and we're good to go. Since we're close on time now, I'm going to go ahead and stop here. And what I'll ask you to do is please, 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 if you have any questions or comments or concerns, please use the comments section of the video on the Data Science Dojo YouTube channel. We monitor the channel frequently and we try to answer any and all questions and comments and concerns promptly. Next up, if you like what we're doing on the YouTube channel, please subscribe to the Data Science Dojo YouTube channel. We will be producing new content weekly, so if you subscribe, you'll keep abreast of all the latest and greatest things that we're doing. Also, more generally, if you like what we're doing at Data Science Dojo, hook up with us on social media. We're on Twitter, Facebook, LinkedIn, YouTube, you name it. Hook up with us and you can get a nice, steady stream of data science goodness sent your way. And I hope to see you, lastly, in one of our upcoming data science boot camps. So until next time, this is Dave Langer, and I'm wishing you very happy data sleuthing. Hi, welcome back. What I have here is an R environment with all of the code through the end of video 5 executed. And where we ended up at the end of video 5 was we were able to create a nice clean data frame. That was populated with not just our term frequencies, but our TF-IDF transformed term frequencies, our mighty TF-IDF transformed term frequencies. And you'll see this here, right? Go and Jurong and point and so on and so forth. Now, what we learned last time was that in theory, TF-IDF improves upon our base representation. And our base representation, once again, was a document term frequency matrix, essentially for every document, just a count of the terms. And we talked about how, well, that's a very powerful model and it works pretty well. There are a couple of issues. One is documents of different lengths will, of course, have different counts. Longer documents will tend to have higher counts. And two, terms that appear frequently across documents, for example, hypothetically, a term that shows up in every single one of my documents isn't particularly useful from a predictive perspective. So we saw how TF-IDF actually addresses both of these issues in a mathematical calculation, and we use that to transform our data to get these values. But now the proof is in the pudding, right? Let's repeat our process. Let's repeat our 10-fold cross-validation repeated 3 times. building single decision trees each time, and see if in fact we can actually improve our model's performance as measured by the cross-validation process. So no problem, we can go ahead and do that. Now notice, as before, I'm going to go ahead and turn the number of cores down. The code by default is set up for a big machine, a workstation or a server class machine. I'll be running this on my laptop, so obviously I don't have 10 cores on my laptop, so I'm going to turn it down to 3 and have this run on my laptop. Now notice that all the rest of the code is exactly what we saw before. I'm going to go ahead and use do snow again so that I can train in parallel. I'm going to spin up 3 instances of the cluster. Behind the scenes, I will run my training as before. Everything's going to be exactly the same. The only thing that's different is now I'm going to use our mighty TF-IDF weighted data instead of just the normal document term frequency matrix as we saw earlier. And then we'll go ahead and see the total execution time and our results. So I'll go ahead and highlight all of this code and get it kicked off and running, and then we'll come back once it is done. Okay, so we're back. So notice that the code this time took a little bit longer to run than last time, took over 10 minutes. No problem. Let's check out our results. So as before, R and Caret handled this process for us, and we were training a cart tree over 3,901 samples, or 3,901 rows in our data set. Each predictor contained a TF-IDF representation of our data, and we had 5,743 predictors. So we did 10-fold cross-validation repeated 3 times, so all of this is the same. Now notice that once again, our CP value that was the best out of the 7 that we tried was again the lowest, this one right here, 0.0133, so on and so forth. And notice that our accuracy is 0.9476181. Now that is not much, but it is higher in accuracy than what we saw with the previous representation, which was just a simple document term frequency matrix. So what this shows us is, in fact, we did get some uplift. We did get some uplift in using the mighty TF-IDF on our data. Okay, cool. So that's great. So we've got TF-IDF, but now what? Is there anything else that we can do to improve the performance of our model? Is there anything that we can do to provide better data? Because, as I mentioned before, garbage in, garbage out. Good data is the linchpin of creating a good machine learning model. So we spend a lot of time worrying about data representation and creating good features to feed into our models. So what's up next? Well, what's up next is something called n-grams. N-grams. So let's go ahead and talk about that. Okay, so we're going to revisit our representation. So this is the second time that we're coming back and we're going to revise our representation. So if you recall, our original representation was a document term frequency matrix. Each row represented a document. Each column was a term as a result of our data preprocessing. So tokenization, stop word removal, lower casing, removing numbers and hyphens and symbols, and then stemming. That was our first representation. Then we said, okay, look, let's TF-IDF transform that. That was our second representation. And now we're going to take a look at how we can augment this representation with yet some more ideas. So if you remember, we had a sample document earlier in the video series. If it looks like a duck, swims like a duck, and quacks like a duck, then it probably is a duck. Right? So we just use this as an example. And what we learned was if we ran this through a prototypical text analytics data processing pipeline, we would get something that looks a little bit like this. Look like duck, swim like duck, quack like duck, probable duck. Right? First and foremost, we lowercased everything. Second of all, we removed all the punctuation, and then we removed all the stop words, and then we stemmed, because obviously you can see here, probably became probable. The rest of these were not affected by stemming. But notice words like and then, and if, and it, and were all removed. So essentially we get just the terms that essentially quote-unquote matter, or potentially quote-unquote matter. look like duck, swim like duck, quack like duck, probable duck. And as you can see, even though it's not proper English, since we know what the original document looks like, we can actually kind of squint our eyes a little bit, and from far enough away we can say, you know what? Yeah, this representation, while not ideal, actually captures the essence of what the original document is trying to say. So cool. Now, we also could see that, great, once I got that, this representation here, right, this result of our tokenization processing pipeline, we can then say, okay, great, I can transform this into a data format that R can understand. We can create a document term frequency matrix, and we just count up all of the individual terms and just create a table like this. So we have 1 look, 3 likes, 4 ducks, 1 swim, 1 quack, 1 probable. Cool. Great. That's our document term frequency matrix. We then said, okay, look, you know what? Later on, we said we can TF-IDF it and make these numbers actually more valuable than just the simple counts. But we'll ignore that for the time being. So what we need to do is talk a little bit more about n-grams. So far, our representations, whether they are just plain old term frequencies or they're TF-IDF transformed values, are still about single terms, like duck, walk, quack, so on and so forth. In natural language processing and text analytics, these are known as unigrams, or alternatively as 1 grams, which makes sense, right? 1 gram. That makes a lot of sense. If I have a single term, the number 1, there's conceptual alignment between this 1 and single. Cool. In grams, you can just say, okay, are terms. Sure. 1 terms, 1 terms. Cool. Given that, though, it's probably your intuition, which would be correct, that there are, in fact, also more than just unigrams. There are bigrams, there are trigrams, quadgrams, quingrams, or 4 grams and 5 grams, you name it, right? You can have combinations that are more complicated. N-grams are cool because they represent an extension to our bag of words model to include word ordering. Now, this won't be as sophisticated, for example, as a full-blown grammatical analysis or a full-blown, language processing analysis of everything, of all the terms. But if we say, look, you know what, at the end of our data preprocessing pipeline, our tokenization, our stop word removal, stemming, removing of numbers, so on and so forth, we say, okay, great. We have the collection of those terms that we get out of the result of that process. We can still extend our bag of words model to include word ordering to maybe get more powerful features, to get better data, to provide more information, more signal to the machine learning model so that it can better understand what's going on inside the text. Okay, so let's see how that works. So let's add bigrams to our existing sample document. So here we go. So once again, let's take a look at our process data, right? Look like duck, swim like duck, quack like duck, probable duck. Sweet. So we already know what the unigram model looks like, so we won't worry about that because we've seen that ad nauseum. Let's talk about bigrams. Now, what are bigrams? If we actually do a bigram of this particular document, this is what we get. Look like duck, duck swim, swim like, duck quack, quack like, duck probable, and probable duck. Now notice that this is actually not particularly difficult to figure out what's going on here, right? Essentially we say, look, bigrams are just essentially take two things that are next to each other and make that a distinct token, make that a distinct term, make that a column in our matrix. Look like are close together, so notice we just use the underscore here to separate them. Look like, we just pivot, like duck, duck swim, swim like duck, so on and so forth, right? Now notice that like duck shows up more than once. So instead of creating a new column, we just add to the count, just like we did before, right? Like duck, like duck, like duck. We got 3 of them, so we got a count of 3. But notice we have individual columns here for all of these different combinations. And notice that while we get a lot of power out of a unigram bag of words model, bigrams actually potentially add a lot more power. Look like duck, duck swim like, duck quack, quack like, duck probable, probable duck. So this is pretty cool, right? We can start talking about, okay, look, probable duck, duck probable, starting to infer something about the semantic of this document, and then you can see the quack likes and then like ducks and all that kind of stuff. Notice how this is more powerful than just the simple unigram representation, all right? Not surprisingly, word positioning, word ordering actually helps out. And as you can imagine, depending on your situation, bigrams will add a lot of power, trigrams could add a lot of power, quadgrams could add a lot of power, so on and so forth. But here's the thing that you have to be cognizant of. This is super, super important. Oops. If we add these bigrams, if we add this collection of columns to our original unigram model, we've more than doubled the total size of our matrix. Because if you recall, our original document term frequency matrix for this particular document was only 6 columns wide. We only had 6 distinct terms. We had look, like, duck, swim, quack, probably, right? We only had 6 terms. Only 6 terms. But now notice that we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 terms. So if we add them together, our 6-column document term frequency matrix now becomes a 14-column document term frequency matrix with our bigrams. So this is super important. This is super important. Adding n-grams dramatically increases the power of your matrix. It gives you a lot more power. More often than not, bigrams and trigrams and so on and so forth are going to make your models more accurate because they will learn more signal in your data. But there is no such thing as a free lunch in machine learning, and text analytics in particular. You pay for this extra power in a radical explosion in the size of your matrix. Not only that, but what you'll find, and we'll see this in a bit, is that not only do you pay the price in terms of a much larger matrix, right? You have a lot more columns, many, many, many more times columns than you had before when you start adding bigrams and trigrams and so on and so forth. But you also get this problem of sparsity. Most of the cells in your table, in your matrix, in your data frame, most of the individual locations are going to be 0. They're going to be empty because most of the time, most of the documents are not going to share the same bigrams. And as you add more powerful features like trigrams and fourgrams and so on and so forth, it's even less likely that the particular word orders that you get out of each individual document are going to be shared across multiple documents. So you get this sparsity problem, which is you get this huge matrix. It's very, very wide, lots and lots of columns. And most of the contents are 0. Most of the contents are missing. So you get this sparsity problem. Collectively, this idea of very, very large matrices and very, very sparse individual data elements in those matrices is known as the curse of dimensionality problem. Text analytics suffers from the curse of dimensionality problem in spades. It doesn't take much for a relatively small data set in text analytics to explode to a really, really big problem space in terms of your matrix size. So you have to be really super cognizant of that. Okay, there you have it. That's the basics of bigrams. Let's go ahead and go back to R and see how we can now enrich our current feature matrix with bigrams. Okay, so we're back in R, and let's see how we can add bigrams to our document term frequency matrix. Okay, so if you recall, way early on in our code, we had this object of train tokens, right? So if I actually go ahead and pull out 357, which is one of the examples we looked at before, this is where we had, right? We had our individual processing pipeline, the results of our text pre-processing pipeline, right? So we tokenized all of the SMS text messages. We lowercase them, we broke them up into individual tokens, we then stem them, we removed symbols and numbers and all that. And notice that 357 was essentially this text that talked about the website bubbletext.com. Okay, great. So we're going to go ahead and reuse this object, and we're going to use a new function from the quantita package called tokens underscore engrams. And I'll pull that up in the help file here, and you can see here, over here, create engrams and skip grams from tokens. So we're not going to talk about skip grams. That's a more advanced topic. But we'll talk about, well, we have talked about engrams. So what this is the function in quantita that you can use on a tokens object to add engrams to it. And notice, so we call the function and we pass in our tokens object, and we can see example of what is included in that tokens object down here. And then we say, okay, great. We can tell it, look, what kind of engrams would we like? So for example, if I just said 1, which is the default, I would get a unigram model. Right? That's the basic bag of words model, unigrams. Now, if I do 1 through 2, I will get both unigrams and bigrams. Now, notice I don't have to do this. I could just say, look, just create me bigrams only, and I would just specify it this way. Or if I wanted to get really crazy, I could do something like this, which says, give me a model, return me back an object that essentially is unigrams, bigrams, trigrams, 4grams, and 5grams. But we won't go there because that, as I talked about before, that will radically explode our feature spaces we'll talk about in a second. So let's go ahead and run this code here. And now notice that what I've done, right? So this was entry 357 before we added bigrams, right? Credit, top, HTTP, bubble text, so on and so forth. And notice now, instead of 7 individual tokens, when I add bigrams, I now get 13 tokens. Notice how I get credit top and top HTTP, and then HTTP underscore bubble text, and then bubble text underscore renew pin, and pin TGXXRZ. Right? Cool. So now I've got my bigrams. This is great. So now that I've got that, I'm going to have to go ahead and do the rest of the pipeline as before. So here's what I'm going to do. I'm going to go ahead and highlight all of this code here and just let it run, and then I'll go back and talk about all the other stuff that we're doing, because this will actually take a little bit of time to run, because as we'll see in a second, our feature matrix is much, much bigger. Okay, so I'm just going to run that and go back and take a look at this code. Okay, so notice as before, we'll go ahead and transform that raw token object into our document term frequency matrix representation using the DFM function from quantita. We'll then turn it into a plain old vanilla matrix as we saw before. Right? This is just a base R matrix, so we can work directly with the numbers. I then actually invoke the actual DFM, so I get this output. So this is if you just type in the name of a quantita DFM variable on the command line and just let it run, this is the feature, this is the output that it'll give you. It'll talk to you a little bit, it'll give you a little information about how this DFM is structured. And here's the thing that we want to take a look at. So as before, we have 3,901 documents. But notice this. We've gone from 5,700-ish columns to over 29,000 columns. 29,000 columns. So we've gone up by more than 5 times, right? By adding bigrams, the number of columns in our matrix has increased by more than 5x. 5x. Now this is super indicative of that problem I was talking about earlier in text analytics, is that, excuse me, let's scroll back up here. So you will get radical explosions in your feature space using bigrams, trigrams, so on and so forth. However, they're often extremely useful in making your models as accurate as they possibly can be. And lastly, what I want to show out in this output here is notice that this is 99.9% sparse. And in fact, I'd be willing to bet that it's more like 99.999-ish. 3 nines past the decimal point, sparse. That is, the vast majority of locations in this matrix are going to be 0. They're just going to be 0. There's going to be nothing in there. There's going to be no values in there. Because think about this for a second. How likely is it that another text, an SMS text message, in our entire corpus of 3,901 text messages is going to have this exact combination of tokens, this exact combination of terms, HTTP followed by www.bubbletext.com? I mean, it's possible. I mean, these text messages come from the UK, and maybe bubbletext.com is a wildly useful and popular website, and people get lots of text from it in the UK. But I kind of doubt it. Probably even more germane is this right here, which is pin_TGXXRZ. This seems like some sort of code, and I would be willing to bet that there's a certain it's highly likely that this code is relatively unique. So there is no such thing as relatively unique, but you get the idea, right? That this is not going to be common. Ergo, this will not be common. So we've just added things that are probably unlikely to be duplicated across our matrix, right? So likely to be, example right here, www.bubbletext.com_renew. So that tells you a lot about what's going on here. We're radically exploding our feature space. But yet at the same time, we're not necessarily getting a lot of uplift in terms of data inside those individual cells, right? That's the sparsity problem. We'll potentially get a lot of predictive power out of this, but we're going to pay the price of huge numbers of columns where most of those columns are essentially empty. Okay, cool. Now you'll notice that this code that I wrote took quite a while to run as opposed to last time. And that's because this code is just plain old R code. And we've written it this way so that you get an idea of what's going on behind the scenes, but it is not optimal. So just so you know, there are plenty of libraries when you get serious about doing text analytics that have much more efficient implementations of the TF-IDF calculation than what you see here. And you'll be able to use those to accelerate your execution time. But here's the critical thing, and I've mentioned this before, and we need to make sure that you have this in your calculations, right? Which is you need to maintain whatever library you use, whatever package you use, whether you hand roll it yourself or you use Quantita or you use the TM package or whatever. When you do this and you calculate the IDF vector for your training data, you have to cache those values. You have to maintain that and store it somewhere. You have to have access to those IDF values, because as I mentioned in the last video, and this is super important, and it bears worth repeating, you need these IDF values stored because as new data comes in, it is required to translate any new documents that you're interested in working with into the same space, into the same footing, into the same transformational area that your training data was located. That's the easiest way to think about it, is to think about it geometrically, right? We need the ability to transform new documents into the same TF-IDF space that our training data was transformed into, because our models will only understand documents in that TF-IDF space. So we need to have this data retained so that we can do that transformation. This is going to be super important because we're going to revisit this same concept when we talk about singular value decomposition, when we do feature extraction. This will be essentially the same idea. We're going to be projecting our training documents into a different space, into a different representation, into a different transformation. This will make more sense later, I promise. And our model will learn that. Our machine learning model will learn that because the only thing it can learn is the data that we provide it as part of training. So we need to maintain that data, maintain that that mapping, that transformation for any future data that comes in. So we have to, not only do we have to maintain the IDF vector for future data, but when we do singular value decomposition, we will also have to maintain those matrices that we get out of that operation for exactly the same reason, so that we can do the transformations. Okay, so the rest of this code is exactly the same. So what we get here is a clean data frame, that is now a TF-IDF transform representation of both our unigrams and bigrams. Now, the last thing I want to show here is the GC command. Now, if you're not familiar with this in R, this is going to be super important when you work with text analytics. This GC command forces R to do what is known as garbage collection. This essentially tells R, hey, go in and free up any memory that you can free up. Now, periodically, R will do this automatically. It'll go through and free up memory that it doesn't need anymore. But as we're doing a lot of these calculations and these transformations, we're actually going to be using quite a bit of memory. So as you can see right now, my laptop has 16 gigs of RAM in it. Not too bad. But notice right now, my RStudio session is using over 7.2 gigs of RAM. Now, if I run this line of code, you'll notice that that a bunch of stuff gets cleaned up. And if I go back, you can see now that actually it didn't help very much, which is a problem. Because this tells you very, very simply, like, I'm starting to stretch the limits of my laptop here in terms of working with this textual data. And that's something that's going to be pretty common. And that's something that we'll be covering in the next video, is that we'll see, okay, look, now that we've got this much larger representation, this 3,901 observations of 29,000 variables, we're going to start running into some problems. We're going to start running into scalability problems in our machine learning algorithms that we're using to do our work. So, but that we'll table that for next time. As always, if you have any questions or concerns, feel free to use the comments section on the video. We at Data Science Dojo monitor our YouTube channel frequently and try to answer all questions promptly. And if you like what we're doing here in terms of our tutorials, please subscribe to the Data Science Dojo YouTube channel. We will be publishing new content weekly, so that if you subscribe, you'll be able to keep abreast of the latest and greatest offerings that we have on data science. Also, even more generally, if you like what we're doing at Data Science Dojo, feel free to follow us on social media. We're on Twitter, Facebook, LinkedIn, you name it. And if you connect with us on social media, you'll get a nice steady stream of curated data science goodness. And lastly, I hope to see you in one of our upcoming Data Science Dojo boot camps. Until next time, this is Dave Langer, and I wish you very happy data sleuthing. Hi, welcome back to video number 7 in Data Science Dojo's series on Introduction to Text Analytics with R. I am your host, Dave Langer. So what we have here is an R environment, an RStudio environment, with all the code ran, executed through the end of video number 6. And if you recall, at the end of video number 6, what we did was we created bigrams. So we added both unigrams and bigrams into our feature matrix, and what we got was a very, very large matrix. As you can see here, we have our new training set as a result of having both single tokens, single individual words, as well as bigrams, that is two words that are right next to each other, gives us a data frame of size 3,901 rows and 29,298 variables. And we finished last time talking about how this is a very indicative problem of text analytics, this cursive dimensionality problem, which is it's very easy to explode your feature space. This is very common, where you will have data frames with rows that are far less in number than your columns. So that's actually very common in text analytics, especially when you start adding n-grams, so unigrams, bigrams, trigrams, etc. And then we also discovered as well is that what happens is that these individual columns, we explode out our data frames. They get very, very wide. So we have lots and lots of columns, but for the most part, the columns are essentially empty. We saw, for example, that our data frames were 99.9% sparse, which means that 99.9% of the cells essentially have values of 0 in them because there was no signal in the data. Another way to think about this is that any particular, if you want to think about it from a bigram or a trigram perspective, any particular combination of two words right next to each other, or three words right next to each other, is going to be far less likely across all of the documents, all of the rows in your data frame. Ergo, it makes sense that most of the values would be 0, would be empty, because there's not a large number of intersections of documents with particular word combinations. That's very typical in text analytics. So text analytics suffers very much from the curse of dimensionality problem. We'll talk more about that in the slides that we'll be going through later in this video. Okay, so as promised last time, so we've got this new data frame, but what did it do actually to the performance that we saw in our modeling efforts? For example, we've been using, for the sake of argument, single decision trees so far in the video series, mainly because they're easy to understand and they train fast. It's purely the only reason why we've been using them essentially just as a device to understand what's going on in terms of the efficacy, the effectiveness of our representations of our textual data. So not surprisingly, following the pattern of the video, we can go ahead and actually do some code to actually train a single decision tree using 10-fold cross-validation, repeated 3 times, using 7 different parameter values to try and find a really good performing tree. Now the problem is, though, as I mentioned last time, is you start running into scalability. So you'll notice that the code that we'll look at right now is all commented out. And the reason for that is this right here. So I ran this code originally on a 10-core workstation. So a workstation with a lot of RAM. It has 10 virtual processors on it. So it's a beefy machine. And it took 38 gigs of RAM approximately and more than 4.5 hours to execute. So that gives you some idea of the sense of scale. If you don't have a really big machine, then doing the kinds of things that we're doing, robust cross-validation using the entire sparse data frame, can lead you to some scalability issues. Now, the good news is in this day and age of the cloud, this is not that big of a deal. It's trivial to go out to Amazon EC2 or go out to Microsoft Azure, rent yourself a fairly large VM. For example, you can get VMs in Azure that are 16 virtual cores, 116 gigs of RAM. They cost around $350 an hour to rent. So I mean, you could rent one for maybe $20 and do this if you wanted to. So in this day and age of the cloud, you know, the scalability concerns are not nearly as concerning as they used to be. But I just wanted to give you some sense of what's going on. So you can, if you'd like, you can go ahead and uncomment all this code and run it. Just be aware that you're going to need a big beefy machine and quite a bit of time to actually get it all to execute. But for the sake of argument, for the sake of discussion, I've gone ahead and just summarized what we got out of the results here. And you'll notice that the run that I did actually decreased the accuracy, decreased the effectiveness of the model slightly. You'll remember that previously with a unigram matrix of TF-IDF values, we were around 94.7 was our about our accuracy for a single decision tree. When we added the bigrams in, it actually went down slightly, just a skosh, just a bit. Now, that's not uncommon. So I will mention this. If as many of my students, my bootcamp students can attest, we tend to use the term "it depends" a lot in answers to lots of questions. For example, Dave, will bigrams always improve my model? And the answer is, it depends. This is a good example of that. In the case of this particular process, which is 10-fold cross-validation repeated 3 times using a single R-part decision tree tuned over 7 parameters using caret, the answer is no. Adding the bigrams actually decreased the effectiveness a bit based on this measure. However, and we'll see this later on in the video series, this is super important, is that while the addition of bigrams affected a single R-part tree, it actually will help out a lot for when we move to a more sophisticated model, notably the mighty random forest. So that's where the depends comes in. Certain models maybe it will hurt, and certain models maybe it will help. So you just need to test this all out. And as my students can also attest, I will argue this is a good thing because this is job security. If you knew all of this stuff a priori, what was going to work and what wasn't, then it could be commoditized and automated, which as of the time of this recording, it cannot. So this is part and parcel of being a data scientist, is understanding the tools at your disposal, exploring them, understanding the trade-offs, and then using the right tool for the right job. As it'll turn out, adding bigrams to our feature matrix is actually the right tool for this particular job, and we'll see that later on in the series. Okay, so moving on. So what we've got now is a problem. We have this very, very large data frame. As you can see here, it took us an awful lot of RAM and an awful lot of time on a pretty beefy machine to actually just work with this data. And what we know is that it's sparse too. So we get this double whammy of, we're taking lots of RAM and we're taking lots of time to execute, and most of the data that we're working over is 0. So it's almost like kind of wasted effort. Now, the good news is that we have tools at our disposal to help us with this. To say, look, you know what? You've got this raw data, these 3,901 rows of 29,298 columns of TF-IDF, unigram and bigram goodness. What more can we do with it to actually improve what's going on? And the answer is that we're going to do latent semantic analysis, or LSA, using a technique called singular value decomposition, which is a matrix factorization technique that allows us to implement feature reduction or feature extraction. And that was a lot of shock and awe terminology, and I did that by design, hopefully to get your attention. But it's actually not as difficult as you may think. So with that, let's go ahead and bust out into some slides so we can actually understand what's going on and how we can improve this representation, how we can simultaneously make it smaller so that way we can use more robust algorithms like the random forest with it, while simultaneously also improving the representation of the data so that the columns that we get are actually far more feature rich, they're far more signal intensive than these highly sparse 29,298 columns. Okay, so let's bust out some slides. Okay, so before we dive right into LSA and SVD and that sort of thing, let's talk a little bit about our progress so far, because that's going to set the context, the conceptual context. So we've made a lot of progress. We've created representations of unstructured text data in formats that are amenable to all types of analyses, and most importantly, for the construction of machine learning models. That's pretty important. So we've also shown how you can build essentially a de facto standard data preprocessing pipeline that can be the starting point for easily 80% or more of your text analytics projects. We've also shown how we can take the base bag of words representation and we can make it even better by using the mighty TF-IDF calculation. And then lastly, we've also extended the bag of words model, the initial unigram model, with word ordering by incorporating things like bigrams and trigrams and fourgrams and so on and so forth. How n-grams allows us to expand the feature capabilities of bag of words representations by adding word ordering. But here's the thing. We've also encountered some problems, some notable problems. First and foremost, as we add n-grams in particular, our document term matrices explode to be very wide. Lots of columns, right? We just saw how we have over 29,000 columns in our unigram and bigram representation. So this is very, very common. And we also discussed they don't contain a lot of signal, right? They're sparse. As a result, we're running into scalability issues like RAM and huge amounts of computation. Building single decision trees in 4.5 hours on a 10-core workstation, I mean, that gives you some sense of scale of what we're talking about. And then all of this basically translates into what we call the curse of dimensionality, which essentially is that as these data frames get very, very, very large, there's all kinds of implications that go along with it, right? Not the least of which, quite frankly, is essentially just the computational aspect. They just take a long time to crunch through to build your models. And anything that slows you down as a data scientist is bad. Quick iteration is key for driving the most business value as a data scientist. So curse of dimensionality is something that you very much need to pay attention to in text analytics. But here's the good news, right? This is all not gloom and doom. All the progress that we've made allows us to use what is known as the vector space model, and we'll discuss what that means in a second. But this vector space model representation, which is essentially what our bag of words model gives us, allows us to address a lot of these problems. And we'll discuss how we're going to do this in the future slides. Okay, but first let's talk about the vector space model. So here's the core intuition, right? And this should make sense. Think about this from a data frame perspective. Essentially, every row in our data frame is a document. And essentially, if you go horizontally across the data frame, it's a collection of numbers. In mathematical terms, that could be thought of as a vector. If you're a computer programmer, you can think of it as an array. Same idea, right? It's essentially a one-dimensional collection of numbers along the horizontal. So if we can represent things as vectors, then we can also think about our documents geometrically, because vectors are geometric constructs, which means we can think about them in terms of geometry. And this is great because it allows us to take a hypothetical document term frequency matrix, such as this one here. And I'm totally making this up, right? It's the simplest thing you can think of. There are only two terms in my corpus of documents. I got bar and foo. That's it. And in this particular document term frequency matrix, you can see here I have 3 documents and 2 terms. Document 1 has 6 bars and 10 foos, so on and so forth. Okay, cool. So if we want to think about this hypothetical matrix geometrically, we actually get something that's highly intuitive. We can visualize it as such. Since we only have 2 terms, we can actually visualize our documents using a 2-dimensional plane, an XY axis. Voila. So on the vertical, I've just mapped the foo-ness, the foo term, to the y-axis, and I've just mapped the barness, or the bar term, to the x-axis. And it was an arbitrary decision on my part. You could reverse that. Doesn't really matter, to be absolutely honest. Now here's the other idea. If we assume that all documents start at the origin, 0, 0, right, where the y and x axis cross, we can now plot our documents in this 2-dimensional space. So for example, document 1 had 6 bar and 10 foo. So I can plot a point in the vector space here. Let's say this is the point 610. And I can draw a line through it starting with the origin. And that's essentially the vector space representation of document number 1. Pretty simple. Document number 2 had 10 bar and 3 foo. Once again, we can create a vector. And the last document, same idea. Create a vector. This is super awesome. This gives us a lot of power. First and foremost, we get the ability to do some intuition. If you take a look at this, you don't have to be a mathematician. You don't have to be experienced in text analytics to just look at this and go, okay, based on this geometric representation, my intuition tells me that document 3 is more like document 1 than document 2 is. And reflexively, document 2 seems to be more like document 3 than doc 1 is. And in fact, your intuition would be exactly correct. The benefit of thinking about our documents using the vector space model geometrically is we can actually take advantage of mathematics. For example, we can use trigonometric functions to analyze, for example, the angles between these documents and understand something about them. Once again, as so often is the case in data science, trigonometry turns out to be wildly useful. Who knew? Okay. So let's talk specifically about some of the mathematics that we can use. So if we have 2 vectors, we can use what's known as the dot product to actually do some mathematics on these vectors and understand something about the underlying text. So if you're not familiar with the dot product, we're going to go ahead and go through it. But first and foremost, the reason why we're going to go through it is intuition. Now, since this video series is designed for a very broad audience, we're going to use only as little math as we need to convey the idea. So we're not going to spend a lot of time spelunking into mathematics. What we're going to focus on a lot is the intuition. Because to be honest with you, a lot of the mathematics you won't be doing yourself anyway because most of it's implemented in the libraries that you use in R. So understanding the intuition is actually far more important. Now, of course, if you always want to go back and learn the underlying mathematics, it is absolutely helpful and useful, but you don't necessarily need it to get started getting business value in your daily work. As long as you have the intuition and you know how to use the libraries, you're going to be able to get business value quickly. Now, if you want to be an expert, obviously you'll need to click down a little bit and understand the mathematics more deeply. Okay, enough said. So here's the mathematical representation. If I have a dot product of 2 vectors, A and B, the dot product, A dot B, you can see right here, A dot B, is simply just go through each one of the vectors. And notice here that the implication is that the vectors have to be the same length, which in our data frame representation is not a problem, right? Every row has 29,200 and something columns. So that's not a problem. Just know that's a requirement. For a dot product, the vectors have to be the same length. So we just go through the vectors one piece at a time, and we say take the first piece of A and the first piece of B, multiply them together. Take the second piece of A, the second piece of B, multiply them together. Add those 2 things up. And then we just repeat this process over and over and over again. This is the dot product. The intuition of this is that you can think of the dot product as a proxy for correlation. A proxy for correlation. The dot product will give you a general indication. It's not exact. That's why I say it's a proxy. It'll give you a general indication of how alike two vectors are. When we talk about cosine similarity later on in the series, cosine similarity is actually a better proxy for correlation, but the dot product is part of the cosine similarity calculation. So you can think of this also as a high-level proxy for correlation. And this is super important, as we'll talk about later when we do SVD and LSA. Okay, so what does that mean? So if we take our hypothetical document term frequency matrix that we have here, we can actually calculate some dot products using the mathematical equation above. So first and foremost, here are the calculations for doc 1 versus doc 2, doc 1 and doc 3, doc 2 and doc 3. And you'll notice here that the scores, these calculational scores that we see here, actually match our intuition of what's going on. For example, doc 1 and doc 2 only have a dot product of 90, but doc 1 and doc 3 have a dot product of 118. Now, if we go back a slide, that'll make a lot of sense because we know that, yeah, just geometrically, this vector is closer to this one. So, yeah, they're probably more similar. This one and this one, the doc 1 and doc 2, are farther apart. So it makes sense that, in fact, the dot product score would actually be less between doc 1 and doc 2 than it is between doc 1 and doc 3. So there you have it. The dot product aligns to our geometric understanding. Notice that the intuition that you had just by looking at the geometric plot actually matches the numbers that you see here of the dot product. So the dot product is going to be super useful conceptually. And we'll see why I'm belaboring this point in some later slides. Okay, moving on. Since the dot product is useful, it would be nice to be able to calculate the dot products of all the documents all at once. So we can do that using matrix multiplication. Now, if you're not familiar with linear algebra, or you took linear algebra a long time ago, it's okay. Just follow along. Just try to understand that we can use matrix multiplication to calculate all the dot products of all the documents all at once. So, and how you would do that is simply saying, look, if I had a hypothetical, document term matrix, the dot product of all the docs would be essentially X, if that's my matrix, times the transpose of X. The matrix X times its transpose. So once again, given the document term frequency matrix that we're using, this is the mathematics that we get out. Notice how this is just our matrix. This is just our matrix. This is the same as this. Transpose just puts it on its side, right? Columns become rows, and rows become columns. Same idea. And then we multiply them together using matrix multiplication. And notice that we'll recognize some of the numbers in here, right? The 90s and the 118s and the 101s. Right? So this row right here essentially represents the dot product for document 1. The dot product of document 1 with itself is 136, but it's only 90 with document 2, and it's 118 with document 3. And we saw those calculations on the previous slide. That's how these all line up. But notice now I can start looking at the matrix all up and start understanding higher level patterns between the correlations between the documents in my matrix. Once again, this is super important, so it bears repeating. The dot product of the documents is indicative of the document correlation given the set of the matrix terms. So what this is this is the correlation of all of my documents with each other given this limited set of terms, bar and foo. Now, obviously, if my documents had other terms in them or more terms other than bar and foo, this would obviously change, right? These mathematics are based on the idea of I've got 3 documents with only these 2 terms. As soon as I add more terms, for example, if I add bigrams, these numbers are going to change by design. But the core idea is the same. It shows you the relative correlation between documents given the term space. And as we've seen, this is super important because part of what we do to enrich our data frames in text analytics is we manipulate the term space using things like bigrams and trigrams. Okay. Next up. Now, if you want to think about it in this way, the dot products of documents essentially treat the matrix along the horizontal. Right? We take the perspective of document, centricity, the horizontal, the rows. But that's not the only way we can think about correlation. We can also think about correlation along the vertical. We can also say, look, you know what? how does the terms actually correlate with each other? Now, as we'll see in a second, given our particular hypothetical example with only 2 terms, there's not much going on here. But if you had 29,200 and something terms, this may actually be highly useful. So once again, we'll use matrix algebra. And we can see here, all right, we're going to calculate the dot product of all the terms in the document term frequency matrix, we'll do x transpose x. So notice that we've just flipped essentially the x and the x transpose. Once again, here's our hypothetical matrix, and you can see here the mathematics involved. And lastly, you can see, okay, the correlation of bar with itself is 200. The correlation with bar and foo is 146. And you can see here that the correlation of foo with itself is 158, given this document term matrix. Now notice, as I said before, this is not super useful with only 2 terms, but as you well know, this is extremely unlikely that we're going to have a very small term space. Your term spaces are going to be very, very large. So this is actually a very useful thing in practice. So again, here's the intuition. The dot product of terms is indicative of term correlation, given the set of matrix documents. And this should make some intuitive sense, right? If you think about our data in 2D terms, right? Along the rows, I've got my documents, so I can think about the world from a document perspective. What are the relationships between the documents? But then you can also flip it on its side and say, okay, look, you know what? I'm actually going to take a term centricity and say, look, what terms have high correlation? And let me use an intuitive example. Foo and bar is a bit abstract, but how about, for example, the idea of the terms loan, credit card, and debt? Let's say I work in the financial services space and I'm analyzing textual documents in financial services. It's probably likely that those terms are highly correlated. They probably show up a lot in the same types of documents. So that gives you an idea that looking at it from a term perspective may also be potentially interesting as well, because at a certain level, maybe, just maybe, the idea of credit cards, the idea of loans, and the idea of debts are all synonymous. Or there may be advantages of me essentially collapsing those 3 columns down into a single column that represents some higher level concept related to debt. This is a key intuition, as we'll see later. This is a key idea behind latent semantic analysis. This core idea of saying, look, maybe I can actually collapse those 3 things down into a single column and actually get more signal out of my data. But more on that later. Okay, LSA, latent semantic analysis. So here's the intuition. I would like to be able to extract relationships between documents and terms, assuming that terms that are close in meaning will appear in similar, i.e. correlated, pieces of text. This is just a fancy way of saying what I just said on the previous slide, using the example of credit cards, loans, and debt. It would be nice to be able to say, okay, look, is there some sort of probabilistic mechanism, some sort of mathematical way of saying, look, based on the correlation of how certain terms appear across all of the documents in my corpus, can I essentially extract out core concepts that aren't actually manifest in the document? For example, the idea that loans, credit card, and debt are all basically ideas of debt in this particular corpus. So instead of having 3 conceptual distinct ideas, can I merge them into one higher level relationship construct, mathematically represented? That's the intuition. So the answer is yes, obviously it works. There's a name for it, LSA. So obviously it works. The implementation is uses what is known as a singular value decomposition, an SVD. And an SVD is a factorization, which essentially means it's a way of decomposing a matrix. You take a matrix, a table, if you will, that you've created. Maybe it's unigrams and bigrams, and it's all TF-IDF awesomeness. And then you say, look, I want to decompose it. I want to actually break that down into smaller chunks using a strict mathematical formula, algorithm, that then provides me with certain benefits. And in fact, when you apply LSA to a term document matrix, you actually do exactly this. You extract out the relationships that we got from our intuition. For example, credit card, loans, and debt actually transform into a higher level relational construct. You may not recognize it. It may not be human recognizable, but the mathematics pulls it out for you automagically. And this is cool. Now, one thing I do need to note here, though, is that the mathematics here are going to get a little bit more complicated than what we saw in the dot product. Once again, stick with me. Bear with the intuition. Most of the time, you're not going to need to implement this code directly. You will use libraries that will help you out, but understanding the intuition is important. The other thing I should note as well is that we'll need to transpose our matrix, because notice that here, singular value decomposition of a term document matrix, because notice so far we've been working with a document term matrix. Documents are the rows, terms are the columns. Everything that you see in the literature, for example, if you go to Wikipedia and you look up latent semantic analysis, is going to assume actually a term document matrix. And just for the sake of the sanity of people watching this video, since all the documentation that you find on the internet uses a term document matrix, I will actually show you in the code, the R code, assuming a term document matrix, even though so far we've actually been assuming a document term matrix. That's just for your sanity. So if you go look it up, then you'll understand the code a little bit better. So just be aware that we'll need to transpose our matrix. Okay, so here's the thing. The SVD of our term document matrix, is equal to a matrix called U, this thing called sigma, and a transpose of a matrix of V. Now, that's not super helpful, so let's talk a little bit about what these constituent pieces mean. So, the matrix U contains the eigenvectors of the term correlations. That is X times X transpose. Now notice that these are opposite from what we saw in the previous slide, because again, we're working with the transpose of our matrix, right? Working with the transpose, that's why they're opposite. And V contains the eigenvectors of the document correlations. But this is what's super important. Ignore this fancy eigenvector thing. Just say, look, this matrix U contains the term correlations, and this matrix V contains the document correlations at higher levels of abstraction. I'm extracting relationships, semantic relationships, out of the documents. So this isn't the term-by-term correlations. These are a reduced set. Once again, using the previous example, this isn't credit cards, loans, and debt. It is a combination of the three as a higher level construct, which is super cool, because notice that not only have I reduced the number of columns in my hypothetical example, but I've also increased the signal in the column. And this is awesome, right? I'm getting a double whammy here. And then lastly, sigma contains the singular values, and we'll talk a little bit more about what that means here in a bit. Okay, so not surprisingly, LSA to the rescue. So LSA often remediates. Now I say often because not always. As I said, look, it depends. Generally speaking, you're going to use SVD quite a bit, but it won't always help you out. Not always, but most of the time it will. So the matrix factorization has the effect of combining columns. And as I said, that has the effect of not only reducing your dimensionality, but also potentially enriching the signal in your data. Not surprisingly, you can actually use LSA to dramatically reduce your dimensionality. For example, it's very common to use several hundred columns in your LSA. So we will go from over 29,000 columns to about 300. So this is great, right? Dramatically reduces your feature space. Now, as always, in machine learning and data science, there is no free lunch. There's always some sort of trade-off. Performing the SVD factorization is computationally intensive, as we'll see in the next video. It takes quite a while. Now, here's the other thing. The reduced matrices, right? These higher level abstractions, right? This combination of credit cards and loans and debt into a single column, these reduced factorized matrices, these quote unquote semantic spaces, are approximations. They are approximations. So they won't be exact. You're going to get a little bit of information loss. But the idea is that the combining of, for example, credit cards, loans, and debt into a single column, even though it's an approximation, the combination of those three things actually adds way more signal than you lose by it being an approximation. So you get a net gain. That's the idea. And then lastly, and this is super important because we talked about this with TF-IDF, is that once again, we'll need to project the new data into the semantic space. Now, hopefully you're starting to understand why this is super important, why I've made a big deal of this in previous videos. When you think about the vector space model and you start doing these transformations, either TF-IDF or bigrams or even LSA for that matter, you start to remember, okay, look, if I train my model based on these vector space transformations, it only understands things that have been translated into that vector space. Ergo, that means any new data that comes in, I have to be able to manipulate the data, transform it, and then present it into that same vector space. And if I can't, then the model's not going to understand what's going on and it won't create good predictions, or maybe not create predictions at all. So that's why it's super important. And we'll see how to do this in the video series so you'll know how to do it in your own work. So, not surprisingly, SVD is effective and is a staple of text analytics pipelines. It's almost essentially de facto default. So, at a high level, what do? I lowercase, I tokenize, I stem, I remove stop words, I do TF-IDF, and I SVD. All those things are pretty standard because generally speaking, most of the time it produces very, very good results. Very, very good results. Okay. Lastly, let's talk about how we project new data. So how we do that is, as we said before, we're going to have to do a bunch of manipulations on the data. So it's useful to talk about this process at a high level. So here is our high level process for projection. Not surprisingly, after we create our tokens, right? After we tokenize, whether we create unigrams or bigrams, we remove stop words, stemming, whatever, that process, assuming that's already done, the first thing that we do is we normalize the document vector. We normalize the rows using our term frequency function, which we saw earlier. Okay. Then after that, we have to complete the TF-IDF projection using the TF-IDF function. Because remember, we cached our TF-IDF values, and now we're going to use those to normalize any brand new data into that space. Now, right now, our training data is done. That's cool. But when we talk about the test data, when we talk about data that flows in from the production system once we go live, this is the process that we'll have to follow. We'll have to tokenize, we'll have to bigram, trigram, whatever we're doing, and then we'll have to do the TF-IDF projection. And then lastly, the last projection we'll need to do is the SVD projection. Because, as we'll see, we're going to reduce our TF-IDF columns from over 29,000 down to 300. So any new data that we work with has to follow exactly the same exact process, otherwise our model won't understand what's going on. Okay, and here's the mathematics for doing the SVD projection. So D hat represents our transformed document, our projected document, the final thing that we actually create our predictions on. D in this math here represents the TF-IDF projected document. It's been tokenized, it's been stemmed, it's been stop word removed and lowercase, and then it's been bigram, trigram, whatever, and then it's been TF-IDF'd. And then lastly, we multiply that document vector, that row, by the U matrix transposed, and that by the sigma values inverted. And that will give you the new document projected down into that 300 column space. Now, once again, if the math is a little bit wonky for you, don't worry about it. It's okay. We'll see this implemented in code in the next video. Okay, there you have it. You've learned quite a bit today in this video. You've learned about the vector space model. You've learned about dot products as a proxy for correlation between documents. You've learned about the mighty LSA, latent semantic analysis. In particular, you've learned about LSA's implementation using singular value decomposition. These are all very valuable tools that will drive your text analytics projects to the highest levels of effectiveness possible. Okay, so until next time, this is Dave Langer signing off. If you like what we're doing here on Data Science Dojo's YouTube channel, please subscribe. We'll be publishing new video content, new tutorials weekly. More generally, if you like what we're doing at Data Science Dojo, feel free to follow us on social media, whether that be Facebook or LinkedIn or Twitter, what have you. And we provide lots of curated data science content for folks that are interested in learning more about the space. Also, if you have any questions at all, please use the comments section on the YouTube page for the video. We do monitor our YouTube channel on a regular basis and try to answer any and all questions promptly. And lastly, I hope to see you in an upcoming Data Science Dojo bootcamp. Welcome back to Part 8 of Data Science Dojo's Introduction to Text Analytics with R. I'm your host, Dave Langer. So what we've got here is an RStudio environment set up with all the code ran through the end of video number 7. And in particular, what we're going to start with is our latent semantic analysis. The last video we talked about the theory, we went through a bunch of slides, talked about the intuitions and the mathematics behind it. Now we're actually going to show how you do latent semantic analysis, LSA, in R. And in particular, we're going to leverage a package, the IRLBA package, this package right here, to actually perform the singular value decomposition, the SVD, the matrix factorization that actually makes LSA work. So first up, of course, obviously, we need to load the package. Now, this package is really, really nice because what it does is what is known as truncated SVD. And we should talk a little bit about that before we run the code. Now, as we discussed last time, SVD is a mechanism by which we can accomplish a number of goals. One is we can enrich our data. We can use it to extract out higher level semantic relationships between terms. For example, we use the hypothetical scenario of credit cards and loans and debt are all terms in my document term matrix. It would be nice if we could extract out a single higher level feature relating to the concept of debt that covers all three of those things. And this is exactly what SVD does. Now, in particular, what this package does, the IRLBA package allows you to do is truncated SVD, where you can tell it, look, I only want, out of all of those extracted terms that you can create using SVD, I only want the X number of most important, the most significant. And this is known as truncated SVD because instead of calculating all of those extracted features, all of those what are known as right singular vectors or left singular vectors, those are those concepts that we're talking about, you can just say, look, just give me the 300 most important, and it will only do the 300 calculations that it needs. And the reason why that's important is because it allows the algorithm to scale, and it also allows the algorithm to run faster than if it calculated all of these right singular and left singular vectors, i.e. those higher level semantic constructs. It would take a lot longer if it calculated all of them and only gave you the first 300 that were worthwhile. So this one actually just finds the first 300 and gives you the first 300. So that's really, really cool. So, but that being said, this code will still take a while to run. As we talked about, one of the downsides of using SVD, what we discussed is there's no such thing as a free lunch in machine learning or data science. The power that you get from using SVD as part of your latent semantic analysis, you pay for it. You have to run the code, you have to do the calculations, and it takes a while. So let's go ahead and take a look at the code, and then we'll run it. And what I'll do is we'll cut from the video, so you don't have to wait for it to run. Obviously, that would take too long. And we'll just show you exactly what the results are in terms of processing time. Okay. So here is the meat of our singular value decomposition. This is just this one line of code. And as always, of course, never hesitate to use the help system. Okay. Find a few approximate singular values and corresponding singular vectors of a matrix. Okay. So as I said before, the concept of singular values, that's that thing that we saw in the previous video, which is called sigma. That's the singular values, correspond to the singular vectors. And the singular vectors and the singular values are the pieces of the mathematics that represent that higher level abstracted relationship that I was talking about. Again, using our scenario as the frame of reference, SVD finds that credit cards and loans and debt can all be combined together and extracted out into a higher level concept known as, let's just call it debt, just debt. In the mathematics, there would be a singular value and some corresponding singular vectors to that higher level construct. And if you remember from the previous video, there is a U matrix, which represents the correlation of the terms, excuse me. So the left singular vectors would be the terms, and the right singular vectors were in that V transpose matrix, and the right singular vectors correspond to the documents. So you get both the term perspective and the document perspective at the same time, which is super useful depending on what you're trying to do. But those singular vectors, those matrices, will now include the 300 most relevant extracted higher level concepts from our term document matrix. Okay, cool. So that's what we're doing. Now notice that per the last video, our current representation is a document term matrix. Documents are the rows, terms are the columns. But as I indicated, in general, when you do latent semantic analysis in SVD, it actually assumes the transpose, where the rows are actually the terms and the columns are actually the documents. So the T function, and as always, don't hesitate to use that, matrix transpose. So this essentially says, look, take this matrix and make what are currently the columns now the rows, and what are currently the rows, make them the columns. So that essentially flips our matrix from a document term matrix to a term document matrix, which is what all the mathematics expect. So that's what this code does right here. This code right here. Very simple. This code right here. Okay. Next up is NV. So let's go back. And if we scroll down here on the help file for the IRLBA function, NV is the number of right singular vectors to estimate. The number of right singular vectors to estimate. So this is the corresponding higher level constructs pulled out from the documents. Give me the vector representation of the higher level concepts extracted on a document basis, on the per document basis, the document perspective. Okay. Now if we scroll up a little bit, what we'll see here is that by default, NU equals NV. And we know that NV is the right singular vectors, the vectors that correspond to the documents. NU corresponds to the left singular vectors, or the terms. Because remember, on the left side is the term perspective, the correlations of the terms, and on the right perspective is the correlation of the documents. So what this says is by default is, if you don't tell it otherwise, if you create 300 right singular vectors, I'm also going to create 300 left singular vectors, which is what we want. So we set NV to 300. And as I mentioned in the last video, research has shown that SVD tends to be particularly effective in the several hundred range. Now, ideally, you'll take the time to play around with this in a production type scenario, right? You'll say, is 250 better than 300? Is 350 better than 300? And you can kind of dial in the number of vectors that give you the best results. We're just using 300 here because it's a reasonable starting point based on academic research. And as we'll see, it actually works pretty well. Is it optimal? Maybe, maybe not, but it's beyond the scope of this particular video series to tune how many singular vectors we need. But in fact, you would do that in a production scenario. Next up on this code is maxit. This just tells you how many iterations of the algorithm should you run at a maximum. So if the algorithm can find all 300 singular vectors in less than 600 iterations, it will stop. But at most, it will do 600 iterations. And we're just picking the number. I'm just picking a number double the number of singular vectors that we need, because usually it works pretty well in practice, because this will find 300 singular vectors in 600 iterations, within 600 iterations. Okay, and then that will create essentially a return object, which we'll take a look at after the code executes, which will include the sigma, the singular values, the U matrix, which is the correlation matrix for the higher level concepts from the term perspective, and then the V transpose matrix, which is the higher level extracted concepts from the documents perspective. And that V matrix actually becomes our brand new training data, as we'll see later on. Okay, so let's go ahead and highlight all this code, and we'll set it off and running. And we'll come back to the video after it's done executing, so you can see, how long it's going to take, so we can set your expectations if you decide to run this code on your own computer. Okay, so we'll take a break and come back when this code's done executing. Welcome back. As we can see here, it took almost 14 minutes for the singular value decomposition to run on my laptop, which is, well, it's not a small machine. It's not necessarily a big machine either. So on a workstation or a server class machine, you can get this number down a bit, but figure it's going to take you a while to run singular value decomposition. And as the size of your matrices grow, this gets even more and more significant in terms of how long it takes to process. Now, the good news is that the IRLBA package will leverage various sparse matrices inside of R. That will help out quite a bit, especially for very large matrices. Unfortunately, we don't have time to go into that in more detail. Feel free, if you're interested, to post on the comments section, and we can take that up there. Okay, so we've got our singular value decomposition completed. So let's take a look at our new training matrix. Now, first up, you'll notice that I'm accessing the V matrix. And if you're interested in more details about the return values from the function call, you can go down here to the help file, scroll down to the section called value. This is the standard place in our help files where functions will tell you what they return back, the structures of the things that they return back. So this particular function returns a list with the entries. D, which is the singular values. This is the sigma that we saw in the slides from the previous video. U, which is the left singular values. Left singular values are the higher level concepts extracted from the perspective of the terms in the matrix. V is the right singular vectors, which are the embodiment of the extracted terms from the perspective of the documents. So this line of code right here says, hey, take a look at the new features for our documents. So if we go ahead and pull this up, you'll notice that we get 3,901 entries, right? Which makes sense because we have 3,901 documents. And you'll see here the 300 columns that we now have. Now this won't show all of them just because of the nature of the display. It shows you the first 100. But notice the naming convention, V1, V2, V3, V4. That's by design because you don't actually know what these things really mean anymore because they're simple mathematical constructs. This is what's known as a opaque or a black box technique. You have to trust in the mathematics that essentially says, look, these 300 columns are now the single most important, the single most significant, the single most feature-rich, information-rich representations of the data, the higher level concepts extracted out of the term document frequency matrix. So maybe this one has to do with things like, hey babe, let's say. I don't know, I'm making this up, right? Maybe someone texted the words hey babe in the SMS message, let's say. And this one is essentially the higher level concept of those two words mixed together. You wouldn't know that, but that's okay because in the end, we're not really necessarily looking at trying to understand the interpretability of the model. We're trying to create the most effective model possible, right? How do we detect between ham and spam? So this is often a trade-off that you see in machine learning, where you give up the ability to actually explain what's going on to get more power. And this is replete in all kinds of scenarios. SVD is one, artificial neural networks is another. Deep learning in particular, it's very difficult to explain how a deep neural network actually works to anyone because it's primarily a black box technique. So there's research trying to improve that, but in general, just know that this is true, right? Once again, there's no such thing as a free lunch. Oftentimes, you will give up explainability for effectiveness, for power, and this is an example right here. Okay, so that's our new training data set, right? We have 300 columns, 3,901 rows. This is great because now we can start looking at using other types of algorithms that would take just god-awful amounts of time to train. For example, we wouldn't want to train random forests on all 29,200 some odd columns of data. It would just take forever to build random forests with that much data. So this is a much better representation because now we can start building random forests effectively because now we have a much more compact representation. Okay, so as we talked about in the video last time, in video number 7, as with TF-IDF, when we use singular value decomposition, we're essentially creating a projection of our data into a new geometric space. Now, this is a recurring theme throughout this series, and it's super important. Originally we take our raw text documents and we create bag of words models out of them. Those bag of words models can be represented in the vector space model geometrically. We saw that in the last video. We can represent them as vectors. We can then add to those things like bigrams and trigrams, thereby increasing the number of features we have, increasing the number of dimensions. But the core idea of the bag of words model is that you can have, you can map them to this vector space model, these vectors. Then we improved again by putting TF-IDF on top of all that, which then translates to yet another geometric representation because we're transforming the numbers in the vectors using TF-IDF calculations. And now lastly, we're doing it one more time using SVD. So we've gone from simple word counts to TF-IDF calculated numbers for those cells in the data frame. And then lastly, we're using singular value decomposition to recalculate numbers in a smaller space. We've gone from 29,200 and some odd columns of data down to 300, which means every time that we want to use data that wasn't part of our original training set, we will need to do the same transformations, the same projections to make that new data match the vector space that we trained our machine learning model on. So this code right here shows you an example of that using our training data. Now, the last slide in video 7 showed you what the transform was. And the transform was essentially take the inverse of sigma times the transpose of the U matrix times the TF-IDF document. So this line of code represents that math that we saw at the very last part of the very last slide in video number 7. Here's how you get the constituent pieces. So D, returned back from our call to IRLBA, is our singular values. That maps to sigma. The inverse essentially is just 1 divided. So the inverse is essentially 1 over these values. And that gives us the sigma inverse portion of our mapping calculation. Next up, U transpose, not surprisingly, just take the U matrix that's returned by our IRLBA and transpose it using the transpose function. Nothing serious going on there. And the document, just for grinsies, we'll just take the first document, right? So this says, go to this data frame, which is our TF-IDF representation of our training data. Just grab the first row and all the columns, please, and make that my document. Cool. So document hat should be all of this mathematically multiplied together. And if you're not familiar, notice that this syntax right here, %, asterisk %, that is how you do matrix multiplication in R, as opposed to just regular multiplication. So matrix multiplication. Okay, so now what we can do is we can compare the logic just to illustrate that this calculation right here works. This is the way you map a TF-IDF document into the singular value decomposition at semantic space. Okay, so document hat, if we look at the first 10 values, and then if we take a look at the first 10 values of the first document in our new training matrix, right, which is the V singular value matrix, you'll notice that for the most part, the values are exactly the same. Not all of them. They're very, very close. So for example, the first 3 are all the same. They're exactly the same. But then notice the fourth one is a little bit different. But notice that these are at e to the negative 17th. These numbers are exceedingly small. Exceedingly small. So even though they're not exactly the same, like for example, here's one that's actually quite a bit different. This one's a negative and this one's positive. Notice that they're still very, very small numbers. Extremely small numbers. Extremely small numbers. So in fact, what will happen is we'll see later on when we study cosine similarity, if I calculated the cosine similarity between these two vectors, all up, all 300 values of each vector, did a cosine similarity, the value that I'll get back is 1. Because these values are so small, and there are so many of them, there are 300 of them, once you calculate the similarity, they will come back exactly 1. So essentially, mathematically, these two things are equivalent, which is exactly what we expected, right? This shows you how you actually map an arbitrary document that's been TF-IDF'd using our functions that we've defined in our previous videos. I can take any piece of data now, whether that's the test data that we held out at the beginning of the series or brand new data in production. This shows you how you mathematically project that TF-IDF document into the semantic space, and we can create predictions from it. Sweet. Okay, moving on. So, how do we use this in practice? Well, that's actually pretty easy. So what we can do here is we can create a new data frame, which we can call train.svd, and we need our labels, of course. So first up, we'll grab all the labels, all 3,901 labels of ham and spam, and then we say, look, create a new data frame, and then have one column that's our labels, and then have the other column be the 300 new features that we've created as embodied by the v vector that gets returned back from the IRLBA function. This is our new training data, right? This is our refined data, our reduced data, the higher signal data based on these higher level relationships between terms and documents in our term document frequency matrix. Okay, so we got our new data frame. And not surprisingly, we can go ahead and also run this code one last time. And we'll go ahead and run this. I'm going to change it to 3 because I'm running on my laptop here. And what we'll do is we'll run our part for one last time. One last time. So I'll just go ahead and run that. And it'll take a while to run. So we will go ahead and cut out and then come back when it's done executing. But before we go and do that, I should mention one thing. This is the last time that we're going to be using the rpart algorithm, because now that we have a smaller dimensional space, we can actually work with more powerful algorithms like the random forest. And what we'll see is the random forest will give us quite a bit of uplift. Oh, actually that ran pretty quickly. Never mind. We didn't have to break it all. Excellent. So we've got 25.8 seconds-ish, which is pretty quick. So if we take a look at our results here, we can see that our best accuracy was right here at 93.36. So as we talked about previously in the last video, we added bigrams, and what we saw was that a single decision tree actually performed a little bit worse with the bigrams than it did with just the single unigram matrices. And now what we see here is that we've actually reduced our performance even further by using SVD. Because as we talked about in the last video, SVD is an approximation. So essentially what this is saying is that from the perspective of a single decision tree, we've lost signal by doing two things. One, by adding bigrams, and then by adding SVD on top of the bigram matrix, unigram bigram matrix, we've lost even more signal. So we've actually reduced from our high. If you recall, our high was a TF-IDF unigram matrix with a single decision tree, and it was around 94.7% accurate. Now we're down to about 93.4%. So we've lost more than 1 percentage point. Now the good news is that we will gain everything that we lost back and more, because now we can use the mighty random forest algorithm. So let's go ahead and take a look at that. Okay. So before we do that though, we need to take a step back and understand what's going to happen here. And this is documented in the code for posterity, but I'll go ahead and talk about it anyway, which is this. We're going to use random forests because they're powerful. They're a great general purpose algorithm. In our boot camps that I teach, I tell my students all the time, if there was only one algorithm that if you were stranded on a desert island, let's go that way. If you were stranded on a desert island and you could only have one machine learning algorithm, which one would you take? And I would advise you take the random forest, because it is a great general purpose algorithm. It has many, many qualities about it that make it very, very desirable. However, it's not necessarily the fastest algorithm in the world to train. So we should talk a little bit about that. So the random forest is powerful, it's useful, it's awesome, but it does take a while to train. And I want to explain the math of why that's going to be the case. So here's the deal. So our process that we follow right now is we do 10-fold cross-validation repeated 3 times. Now, as we saw previously with our part, and I didn't go into much detail on this, but I will now, we also tune over 7 different values of a tuning parameter. In the case of our part trees, it was CP, the complexity parameter. I didn't bother going into it in any level of detail because I knew that we weren't going to be using our part as our serious algorithm. We were going to use random forest. So I will go into detail on that going forward on what that means. But in terms of just the raw math, in terms of just the raw processing time, you need to understand that we're doing 10-fold cross-validation repeated 3 times, and then we do that process, the 10-fold cross-validation repeated 3 times, again a total of 7 times overall, because we're using 7 different values of the parameter to find out which one is the best, which is the best parameter value to use. And then lastly, the Mighty Random Forest by default builds 500 decision trees per random forest. So that gives you this math right here. 10 times 3 times 7 times 5. And then at the very end of the process, once Carrot has found what the optimal value for the parameter is out of the 7 that it tried, which one works the best, it builds one more random forest using that value with all of the training data. That's this 500 right here. So when you add this all up, what you get is our process is going to build 105,500 trees over our data, which is 3,901 rows of 300 columns. So, as you might imagine, that's a lot of processing. So this takes a lot of time. So for example, using the 10-core workstation that I've been using throughout this series, it took 28 minutes using 10 cores simultaneously to actually run this process through and build a random forest. Now the good news is that we're going to get pretty good estimates of our accuracy. We have good estimates of how well this model should perform in production. The bad news is that it's going to take about a half hour every time that we test this. So as a result, what I've done for this video series is I've ran this code previously and I've cached the results in the GitHub as binary files that we can load up so we don't have to run the code every single time. You can go ahead and do that if you'd like. Feel free to do it, but you won't have to. Okay, so let's go ahead and take a look at this. So you can see here, here's all of the code and it's commented out. And you can go ahead and uncomment it, of course, and run it if you would like. But notice that it's going to take quite a while to run. But if you get the R data file, the binary from the GitHub, you can just run this line of code and it loads up into the memory space, and now we can just check out the results, lickety-split. Okay, so here is the output of us running the Mighty Random Forest. So I'm not going to drain all of this up here. We've talked about it before. This essentially just is output that tells you what Carrot did. What we're going to focus on, as I mentioned earlier in the video, is this right here. In particular, we're going to ignore the kappa statistic in favor of other metrics that we'll see later from the confusion matrix function. What we'll concentrate on are these 2 columns, mtry and accuracy. Now, essentially, we don't have time to go into how the random forest algorithm actually works at base. So feel free to get on YouTube, do a quick search on random forest, and you can find lots of great tutorials on how the random forest algorithm works. What mtry is specifically, and I'll be very brief about this, is essentially a parameter that controls how much data gets used in building the individual trees. How much data gets used in building the individual trees. Now, as we know from before, random forests by default in R build 500 trees, but as each individual tree gets built, you can specify how much data gets used for each tree. And specifically what mtry is the number of randomly selected columns that each tree gets to use to build itself. So this is a way of constraining the amount of data each individual tree gets to see. And obviously that will have different levels of impact. As you might imagine, the less data you have, the trees will tend to be less accurate overall because, well, they have less signal to work with. And you may suspect that in general, as you get more data, so for example right here at an mtry value of 300, all 300 columns are available to every single tree. They get access to all the data. You would think that that would lead you to always have the best results, but in fact, it's not. Usually it's somewhere in between these two extremes of very little data, right? This would be, you only get 2 columns out of 300 to work with, which isn't very much data at all the way up to 300 columns, which is all the data. And what we find here is that for the binary saved out for the run that I did previously on the workstation, somewhere in the middle is the Goldilocks zone, 151. So the best random forest was built using approximately half the data being available to each individual tree in the random forest. That's how you should interpret mtry. And we've just went through 7 different values and honed in on one right here. So using about half the data for each individual tree in the random forest produced us the best accuracy of 96.753%. Now what's interesting here is that this is about 2 percentage points higher than the best single R-part tree, which shows us that, as I mentioned earlier in the video, the random forest is actually better able to make use of the data preprocessing pipeline that we have. And in particular, it's able to make better use of the LSA SVD matrix factorization than a single decision tree is. Okay, cool. So moving on, we can also get more interesting results by using the confusion matrix function from Caret. Now, as always, don't hesitate to, confusion matrix. And you can see right here, this is a great function. It produces a lot of detail. So we'll go ahead and run this. And we'll go into more detail in later videos because we're going to explore all of these, well, not all of them, but a number of these metrics here more closely as we tune our model and try and zone in on the best model that we can. But what I did want to call out real quickly is one thing. Notice that the accuracy reported is a little bit higher. That's because we're working with all the data here, all the data, as opposed to cross-validation where you're only working with tenfold cross-validation, you're working with 90% of the data, 9 folds is what you use for training, and then 10% you're using for your testing. So here we have all the data, so we get slightly better results, 96.8. But notice here we get this nice confusion matrix, not surprisingly, and this shows us a couple things. One, when we predict ham, we're pretty good. We got 3,371 correct, which is nice, and then we erroneously allow 7 pieces of spam through. We said, in fact, these SMS messages were spam, but we said they were ham, they were okay. That, you know, that's something we can improve, but this is actually pretty good. Looking at this confusion matrix, this is the line where we're actually probably going to want to focus, because here we allowed 117 legitimate SMS messages to be labeled, to be predicted to be spam. And generally what we're going to want to do is concentrate on fixing this if we can, because it's probably likely that our customers are going to be more dissatisfied in the scenario where we move their SMS messages, let's say, to a spam folder erroneously, than they are to get an occasional spam message coming through into the legitimate folder on their phone, let's say. So this is definitely something we're going to want to concentrate on going forward. And we'll use the confusion matrix function in the upcoming videos to actually help us with that. All right, so I'll go ahead and end there. So hopefully you're enjoying the video series, you're finding it useful. If you have any questions or concerns, feel free to use the comments section on the YouTube page for this video. We at Data Science Dojo monitor our YouTube channel frequently and try to answer any and all questions promptly. Next up, if you like what we're doing on the channel, please subscribe. We'll be publishing new tutorials weekly, and then that way you can keep abreast of the latest content. Also, if you like what we're doing more generally at Data Science Dojo, feel free to follow us on social media. We're on Twitter, LinkedIn, and Facebook, and you can tap into a font of curated data science goodness by following us on social media. And lastly, I hope to see you in an upcoming Data Science Dojo Bootcamp. I'm Dave Langer, and I'm wishing you very happy data sleuthing. Greetings. Welcome to video number 9 in Data Science Dojo's series on Introduction to Text Analytics with R. I am your host, Dave Langer. What I have here is an RStudio environment with all the code through video number 8 executed. And as you recall from the end of at the end of video 8, we were discussing some of the output from the awesome confusion matrix function. As a refresher, don't hesitate to use the help system here. Confusion matrix, create a confusion matrix. Now, in particular, what we talked about was that the confusion matrix function from caret not only produced a confusion matrix, which is this table of numbers right here, and provided you with an accuracy number, but it also provided you with a bunch of other metrics that would be useful. And the focus of today's video is going to be drilling on these first two highlighted metrics, sensitivity and specificity, particularly in the context of when you're doing applied data science in the real world. Accuracy is obviously a very common metric that is used. It's very intuitive and people understand it, but it's not always necessarily the best metric to use. And it may be beneficial for you to either change your metric from accuracy to something else as your major KPI, or alternatively, you still keep accuracy as your major KPI, but you also use other metrics as well to help guide you in your efforts for building the most effective machine learning models. And the example that we used last time, which bears repeating, is that you can make an argument that in a spam filter case, a spam detection case, that there are two scenarios that can occur, two bad scenarios that can occur, and one is probably worse from a business perspective than the other. And as a refresher, one of those scenarios is I have spam, right? I have a bad email, an illegitimate text message, what have you, that comes in, and we incorrectly predict with our model that in fact it's legitimate. So even though it's spam, we say it's ham, and it falls through. It flows through to the user. That's not ideal, but arguably is not as bad as the alternative, which is we have a good piece of email, a good SMS message, a good Twitter, whatever, a tweet, whatever, but in fact we erroneously predict, or we erroneously classify with our machine learning model that in fact it's spam, it's illegitimate, and maybe put it in a separate folder or in a separate part of our application. That is arguably worse. It's arguable that our users will tend to forgive us from occasionally thinking that spam is actually legit, rather than on a fairly regular basis incorrectly taking their legitimate messages and thinking that they're bad and then put them like in a spam folder where maybe they missed them. So using accuracy alone isn't going to necessarily get you where you want to be. Other metrics can hone in, for example, on how well you're doing for classifying spam, how well you're doing for classifying ham, and you can use those in conjunction with accuracy to actually gauge whether or not your models are actually improving in the way that the business needs, or if your feature engineering efforts are producing the results that the business needs. Okay, so what we'll do is we'll actually pop over into some slides and talk a little bit more about sensitivity and specificity and how we can use those to help us build a more effective spam predictor model. Okay, so here we have in our PowerPoint a representation of a confusion matrix which matches what we saw in the R command line output. Our columns here, ham and spam, are our references, or the actual labels. In fact, these are the hams, and in fact, these are the spams. In the rows are our predictions. Our model predicted ham, our model predicted spam. Now, where these intersect, we now have 4 quadrants, A, B, C, and D. Now, if you're familiar with statistics at all, you will immediately recognize that these are in fact mapped to the ideas of true positive, right? It was ham, and I predicted ham, so true positive. False positive, it was spam, but in fact I predicted ham. That's a false positive. False negatives, it was in fact ham, but I predicted spam. And then lastly, the true negative. The message was spam, and I predicted spam. Now this will be important because as we talk about accuracy, sensitivity, and specificity, we'll use these terms. We'll use the quadrant letters as well as TP, FP, FN, and TN, as well as part of our mathematical definitions. But the thing to remember is the stuff that I get correct is along this diagonal from the top left to the bottom right. This is the stuff I get correct. The stuff I get wrong is the opposite diagonal. Okay. So first up on the hit parade, accuracy. Now you'll notice that I just added the TP and the FP and the FN and the TN here, but otherwise this table is exactly as the one that we saw previously. So I like to think, when I talk about metrics, when I teach metrics to our bootcamp students, I like to talk about the intuition. What is the metric trying to tell you? What is the metric helpful for? What kind of questions does the metric answer? These usually put these different kinds of metrics in a very intuitive light, and then you can start to think about how they work, which ones will be appropriate for your business situation, so on and so forth. So I know this will be exceedingly simple because everyone knows what accuracy is, but it just go with me for a second here. Okay. So the intuition of accuracy is simple. What percentage of the predictions were correct? That's all it is. I made some predictions. My model made some predictions. What percentage of all the predictions were actually correct? So mathematically, accuracy can be formulated this way. It's a ratio. Most metrics are ratios, obviously. So accuracy is no different. So if we actually take this apart and just take a look at the numerator and the denominator, the first thing we can see is that the numerator of accuracy is essentially the diagonal, which is, I said earlier on the previous slide, the diagonal from the top left to the bottom right is what we get right. That's what it is. So the top part is what we get right. The bottom part is basically everything. So intuitively enough, accuracy simply is just the ratio of the things I get correct vis-a-vis all of the predictions that I make. The predictions I get correct divided by all my predictions. That's the accuracy. It's your percentage. Very intuitive. But as we've seen, accuracy alone may not necessarily be enough, because I'm actually maybe more interested in ensuring that I get ham correctly predicted more than I'm interested in getting spam correctly predicted, because my customers may be more forgiving of spam errors versus ham errors. So moving on, we can look at sensitivity. Now here's the intuition around sensitivity. Sensitivity is what percentage of my ham messages were correctly predicted. Not what percentage of all the predictions were correct, just only the ham messages. I don't care about spam for this particular metric. I only care about ham. Out of all of the ham predictions that I made, what percentage of those predictions were correct? And there's the math. Not surprisingly, we'll go ahead and decompose it just like we did before. So our numerator is the true positive, right? Of the ham messages, how many did I actually predict were ham? That's A, the green box. Versus the total number of ham predictions I made altogether, both correct and incorrect. Now, obviously, sensitivity is going to be a good metric for us to pay attention to, under the assumption that we would prefer in general to make mistakes on the spam side of the house rather than on the ham side of the house, because our customers are likely to be more forgiving in those kinds of mistakes. Now, if you're in the business world, you can think of any number of situations where this idea is going to be true, especially in the binary case, because they're replete in the business world, where you could say, look, you know what? If I had to make an error one way or the other from a business perspective, I would rather make this kind of error because it's less costly, it generates more revenue, it has less customer dissatisfaction, you name it, right? So there are all kinds of examples of this. So sensitivity is a very, very good metric to use in those types of situations. Not surprisingly, if there's one for ham, if there's a metric for ham, there's also going to be a metric for spam. And in fact, there is. This is called specificity. And the intuition here would be exactly the opposite of what we saw in the previous slide. What percentage of the spam messages were correctly predicted? And once again, the math is not too terribly difficult, as you might imagine. It's just Tn over Fp plus Tn. Or if we decompose it again with our little colored boxes, the numerator is how many of the spam messages did I in fact correctly predict, divided by the total number of spam predictions that I made. And that gives me the relative percentage. Now here's the thing. And this is one of the things that makes data science both a lot of fun and frustrating at the same time, which is you can create lots of features. Feature engineering is super, super important in applied machine learning, applied data science, especially in business scenarios. You make new features, it allows the information to pop, it makes the machine learning algorithms work a lot better. However, most of the time what you'll end up finding is that your features either don't work, and that's totally normal, by the way. You have to go through a lot of features to find the nuggets of gold, or they work but they have unintended consequences. For example, and this is the reason why we're going through these metrics here, it is entirely possible for you to engineer a feature that increases your accuracy overall, but negatively impacts, for example, your sensitivity. Because if you go look at the metrics, what will happen is your accuracy will go up, your sensitivity could go down, but your specificity goes up at a higher rate than sensitivity is going down. Ergo, you get a net increase in accuracy. Now, maybe that's okay, but in our particular case, this hypothetical example wouldn't be so ideal because we prefer to have mistakes, if they exist anywhere, on the spam side of the house. So what we would tend to prefer as a result is if we had to choose, now obviously we would like both to go up at the same time, both sensitivity and specificity to go up at the same time, but if they cannot, we would tend to prefer sensitivity to go up more than we would prefer specificity to go up, because we prefer being correct with the ham example, the ham scenario, than we do about the spam scenario. Okay. So there you have it. Quick and dirty coverage of metrics. Enough with the slideware. Let's go ahead and get back to R code. Okay, so we're back in R. And let's move on. So what we have here is a pretty good indication of what's going on. So we have our data. So we ran it through a pre-processing pipeline, lowercase, tokenized, removed stop words. We stemmed. We added bigrams in addition to our unigrams. We TF-IDF'd it. And then we projected it down using singular value decomposition, SVD, from 29,200 and something features down to 300 features. We built a mighty random forest, and this is what we got from the results of our cross-validation run. 96.82% accuracy, but notice that our sensitivity is 96.65, and our specificity is 0.9831. And based on the metrics, you would know that this essentially is, this value comes from dividing this number by this number plus this number, and this number comes from this number divided by this number and that number. And just to prove it to you, 406 divided by 413 gives you 98.3, or 0.983, sorry about that. There you go. So, not bad. But what we see here is that our model is actually better at predicting spam than it is ham, at least to start with. So ideally what we would like to do is engineer some features that not only increase our overall accuracy, obviously, because ideally we'd like to be 100% accurate, even though that's probably hard to do in practice. We'd like to increase our overall accuracy, but in general we would also like to see these sensitivity numbers coming up, because our core assumption again is that we prefer not to make mistakes in the sensitivity space if we can help it. Okay, so early on in the video series, we created a feature. If you recall, we created a feature called text length. And essentially this was just the count of the number of characters in the SMS text message. And we did a little ggplot2 action on that. And we found that in fact, it was actually looks to be a pretty good feature. Just based on inspection, it looks like it would actually be quite predictive potentially. So why don't we go ahead and add that into the mix? We can add a new feature to our train.svd data frame called text length. Just pack in the original data that we calculated on it. And now we have a new feature to augment our SVD features that we have for all the unigrams and bigrams. So if I run this line of code, I could then, of course, now redo my process, right? You know, our tenfold cross-validation repeated 3 times with mighty random forests with 500 trees apiece, tuned over 7 different values of mtry. Now, it'll take a while to run, and you'll need a pretty beefy machine to run it as currently coded. But as before, I've actually ran this already and cached the results in a binary file that's available from the GitHub. So if you get the files from the GitHub, there'll be one called rf.cv.2.rdata. You can load this up with the code and check out the results without having to wait 20, 40, 80 minutes to actually have the above code run. So let's go ahead and execute that. And here's what you can see. You can see that in this particular run, the best value for mtry was not 151 variables per tree, but 101 columns per tree. And you'll notice here that the accuracy was a little over 97%, which was higher than the previous example. But as we know, accuracy alone is not enough to understand what's going on. So let's drill down. Once again, let's use our confusion matrix function from caret and drill down on what's going on here. Now, first up, what you should notice is that our accuracy has gone up. It's gone up a little bit. But more importantly, look at our sensitivity and our specificity. Both of those numbers have gone up as well. Our specificity is approaching 100%, which means we are getting very, very close to being able to identify spam correctly, at least based on the training data, because notice we only get 3 wrong. Also notice that we did have a reduction in our ham errors. In the previous confusion matrix, if I go up here real quick, I'll show you, we had 117. So we actually were able to now correctly classify an additional 7 here. So we went from 117 wrong to 110 wrong, which gave us a little bit of a bump. So in general, this is a good feature. This is what we like to see. Our accuracy is going up, but also our sensitivity and our specificity are also rising at the same time. Now we got more bump in specificity. We got more increase in our ability to correctly classify spam than we did ham, but at least we got both going in the right direction. They're both going up. So this is a good feature. Now, the reason why this is a good feature is that this is a good indication. It's only an indication, but it's a good indication that this feature may actually be useful in production against unseen data. And this is going to be super important because, as we'll see later in the series, towards the end of the series in particular, this is going to be super important because when we train our model, we're only going to have a certain number of n-grams to use because we'll only have the text messages at our disposal to use to build our training set. Now, as everyone is probably aware, people tend to use different types of words and use different types of styles, especially for social media communication, and it morphs pretty regularly over time, which means that your data is going to become stale pretty quickly. So ideally what you're looking for is features that actually capture, not to sound very, very flowery here, but capture the transcendent underlying truth of the data. So a feature that can, such as text length, that tends to not only increase accuracy but also increase sensitivity and specificity, that's a good indicator that it's possible that text length may be one of those transcendent universal truths in the data, that in general, spam, no matter what, tends to be longer than ham, because that's what we saw earlier. We won't know this for sure until we can confirm it in production or use our test holdout to confirm it, but in general, that's a good indicator. So these are exactly the kinds of features that you're looking for as a data scientist. Okay. That's great. Okay, but we're not done. So let's take a look at feature importance. So one aspect of the mighty random forest that is super, super cool is that as the algorithm runs, it can actually keep track of variable importance. If you actually go back up and you look at the code here that is commented out, I've actually specified that the random forest actually track importance. This is turned off by default, but you can ask the mighty random forest as it's training itself to say, look, keep track of what variables are actually important. Which ones are the most useful? Which ones are the most predictive? And it'll keep track of it for you. And then you can actually ask the mighty random forest later, hey, by the way, which features, which variables, which columns were actually important? Which ones were actually highly predictive? So we'll go ahead and take a look at that real quick. And then we'll end this video. So I need to load the random forest library first up. And then I can run the var implot function. And as always, never hesitate. Var implot. Variable importance plot. Interestingly enough. Now what I'm going to do is I'm actually going to do the first CV run. This is the run without text length. Right? This is the first one we looked at. This is one that was 96%-ish accurate. Just so you get some idea of what was going on with that particular model. So if I zoom in on that, you can see that the variable that is x24 is by far and away the most important. You can see that way over here. It's by far and away the most important. And the next up was x159, x85. Now, as I promised in previous videos, what is x24? We don't know. We don't know, right? Because it's some sort of weird combination of one of those 29,200 and something columns that the mathematics said was actually significant. But the main idea is to show you is that some features will tend to be very, very predictive, very, very significant, far over here on the right, far over here on the right. And then some will be less, right? For example, x57 is way down here. Notice how far apart it is. Okay, excellent. Next up, let's take a look at our new. Okay. Now you'll notice that the visualizations are a little bit different. Don't worry about that. Notice that this right-hand graph, this right-hand plot was the same plot that we saw in the previous visualization. Okay. And notice this is super interesting, right? In our first plot, x24 was by far and away the most important. But notice that text length has essentially squished all of these features down. So what's the interpretation? As a data scientist, what should you think about this? And the answer in very simple terms is that text length is by far and away a better feature than any individual column that we were able to extract out using latent semantic analysis. That is, our singular value decomposition, our matrix factorization that tried to extract as much info as they could out of those TF-IDF unigram and bigram columns weren't nearly as powerful. There isn't one that is nearly as good as the text length. And that actually happens quite a bit in text analytics. Generally speaking, individual word features most of the time tend to be relatively weak. And the features that you can engineer as a data scientist will often be far stronger. And that's really where you make your money as a data scientist, right? If you could just get away with just, you know what, I'm going to create my standard pipeline, I'm going to go ahead and TF-IDF it, I'm going to go ahead and SVD it, and that gets me all the way, home, 99% of the time, then the data scientist position wouldn't be one of the best jobs in the world because it would be commoditized and automated, right? It's this idea here. I mean, it's a very simple feature, to be sure. Don't get me wrong. I mean, this is not genius, by the way, but I'm just using it as an example, an example of saying this is where you add value as a data scientist is feature engineering, because you get this. If you create good features like this, they will typically be disproportionately powerful, disproportionately useful in a text analytics scenario. And that's where you make your money as a data scientist. Okay, I'm going to go ahead and stop there for this video. In the next video, we will actually take this idea of feature engineering a little bit further. We'll use cosine similarity and engineer a new feature and add it in and see how it works. And so hopefully you'll be excited for seeing that. And that video will be coming up 1 week after this video gets published to the YouTube channel. So if you like what we're doing here, if you like this video series, if you like our YouTube tutorials in general, please subscribe to the Data Science Dojo YouTube channel. We'll be producing content on a weekly basis. Also, if you like what we're doing at Data Science Dojo more generally, we do have various social media feeds on Twitter, LinkedIn, Facebook, etc. You can go ahead and subscribe to those, and you'll get a font of curated data science goodness if you're interested in learning more about what's going on in the world of data science. Also, if you are so inclined, we do teach a 5-day intensive data science boot camp. So if you're interested in bootstrapping into some new foundational data science skills, and you don't necessarily have the ability to take 12 weeks off of work to do that, you should probably check out our website at datasciencedojo.com. Okay, this is Dave Langer signing off, and I wish you very happy data sleuthing. Hi, welcome back to video number 10 in Data Science Dojo's Introduction to Text Analytics with R. I am your host, Dave Langer. Per our process, what we have here is a RStudio environment with all the code executed through the end of video 9. And where we ended up at the end of video 9 was the situation as embodied by this plot. So we built ourselves a mighty random forest. And in particular, what we did is we built a mighty random forest with not only our textual features that we had processed extensively, but also we added in a feature that we engineered earlier in the video series for text length. We said, okay, look, can we improve our model over just the textual representations that we've created by adding this text length feature into the mix? And the answer was yes. Adding text length not only improved our accuracy overall, it also uplifted both our sensitivity and our specificity. And as we talked about in video number 9, there are many metrics that we can use to gauge how effective our model is. Accuracy is one, but we can also drill in and have more detailed type of metrics. And in this case, we talked about sensitivity being essentially the metric that says how good is your model, how effective is your model at predicting ham messages correctly. And then specificity was the metric that tells you how good your model is, how effective your model is at predicting spam messages. And what we saw is that text length not only increased our overall accuracy for our model, but it also increased sensitivity and specificity at the same time. And we said, that's great. While not necessarily a guarantee, it is indicative that maybe text length is a very powerful feature that will be universal. And the idea, the hypothesis being, for example, in general, spam messages will always be longer than ham messages. Therefore, it may be a universal feature that will always be predictive over time and space. No guarantee of that, of course, but it is indicative when it raises both sensitivity and specificity at the same time. Okay. We also postulated at the end of last video that we could engineer another feature potentially and add it to the mix and see if we could get even more improvement. And what we mentioned was we could use cosine similarity as the basis of that feature. So before we actually get into the code to actually check that out, we should probably talk about what cosine similarity is. Not surprisingly, I have some slides to discuss the concept. Okay, so we've talked about similarity in vector space in a previous video where we talked about specifically about the dot product, how you can use the dot product between two vectors as a proxy for correlation, the proxy for similarity. Specifically, the dot product between two vectors that seem to be closer in vector space will be higher than the dot product between two vectors that are further away in vector space. And as you recall, we had a vector space, a hypothetical example of vector space that looks like this. I won't reproduce the document term frequency table, the hypothetical table that we use to draw this diagram because it's not necessarily germane to this conversation. Go back into the previous video if you're interested in more detail on that. But what we have here essentially is a hypothetical vector space consisting of two dimensions. All of our documents either have foo or bar in them. And consequently, we can map our vector representations based on their foo-ness and their bar-ness in this vector space model. And what we saw was doc1 is the green line here, and doc2 was this red line. And we could see that, well, they're not very close together. Right? Doc2 seems to have a lot more bar-ness than foo-ness, and doc1 has more foo-ness than bar-ness, and therefore they didn't seem to be too much alike. And we confirmed that in fact, based on the dot product between the two, they're in fact not, they're not necessarily highly correlated. But we promised in that video that actually there would be a better way for us to actually understand the similarity between two document vectors in the vector space model than just using the dot product. And we said specifically that would be the cosine similarity. So if we think about this, rather than just using the dot product between two vectors, if we actually say, look, I can actually measure the angle between these two vectors, maybe I can use a metric there that's actually more powerful than just the dot product. And specifically, we can use the cosine function. As we'll talk about in a bit, there are some particular advantages to using cosine versus some other trigonometric function like sine or tangent, that sort of thing. And now if we pretend that the angle between doc1 and doc2 has been labeled theta, we can essentially say, look, we can measure the similarity between doc1 and doc2 in vector space given the cosine of theta, the cosine of the angle between these two documents. Now, as you recall from the previous video, we also had the example of doc3. represented here in blue. If we say the angle between dock 1 and dock 3 is alpha, we could also measure the similarity between dock 1 and dock 3 using the cosine value of alpha. And then we can then compare cosine alpha versus cosine theta and actually get a more definitive understanding of which document vectors are more alike than others. And not surprisingly, what we'll find is that dock 1 and dock 3 have a higher cosine value than dock 1 and dock 2 do. But let's go in a little bit deeper on cosine, right? So why exactly is cosine an improvement? I'm stating here on the slide that cosine is an improvement over using the dot product. So let's talk about why. So some advantages of using the cosine for document similarity are, one, given our representations here, the cosine will be between 0 and 1, which is nice. Whereas before we saw that dot products could be any sort of particular, there could be some arbitrary number, 136, 212, 95. You don't know. All you could talk about was the relative magnitude of the numbers and not necessarily getting anything more definitive. But given our representations, the way we represent our vectors in vector space, we will get a cosine value between 0 and 1, which is nice because we know that a 1 essentially means perfect similarity. So a cosine of 1 would essentially mean the document vectors are exactly the same. They have exactly the same number of words, and if we're using bigrams and trigrams, they have them in the same exact order, so on and so forth. So you would essentially see two lines on your graph overlapping in the case of a cosine similarity of 1. 0 would be essentially 90-degree angle. They're completely orthogonal. And in our particular case here, using our particular vector space model here, essentially you would have, the only way you could have a cosine of 0 is dock 1 would only be foo. It had only foo in it. And dock 2, for example, would only have bar in it. Then they would be orthogonal, right? They would be at right angles, so therefore cosine would be 0 in that case. Okay. Now, this is true also to a certain extent with dot product, but just go with me here for a second, is that cosine similarity is also very, very nice because it works well in high dimensional spaces. And as we've talked about before, and as we saw earlier when we just added bigrams to our data frame, text analytics is a high dimensional problem, right? It suffers from the curse of dimensionality big time. It's not uncommon for you to have tens of thousands of features, 100,000 features, 200,000 features. It all depends upon the size of your corpora, right? How many documents do you have in each of your corpuses that you're looking at? Or it's also a function of how big the individual documents are. Or in the worst case, you have a very large corpus, many documents, and the documents happen to be big. For example, imagine doing text analytics over every science fiction novel published in the United States in the 20th century. Your data frame would be gargantuan. Good news is that cosine works very, very well, even in high dimensional spaces. Now, of course, you would probably SVD that to shrink it down, but you get the idea. So cosine is really, really nice. So let's talk a little bit about the mathematics then. Okay, so how do you calculate the cosine similarity? So here's the mathematics for it. So the cosine of theta, which is the angle between vector A and vector B, is essentially the dot product of A and B divided by the length of A times the length of B. Or alternatively, you can think of it in this mathematical formulation. We saw this previously, right? This right here. Take the first part of A times the first part of B plus the second part of A times the second part of B plus the third part of A times the third part of B, so on and so forth. That's your numerator, the dot product. Now notice below, what you've got here essentially is a stylized representation of the Pythagorean theorem. Turns out the Pythagorean theorem is wildly useful. Who knew? Right? If you remember, the Pythagorean theorem says c squared equals a squared plus b squared, essentially. Right? Well, all right, fine, fair enough. But it turns out that the Pythagorean theorem actually works well in high dimensional space in addition to low dimensional space. So, for example, the Pythagorean theorem scales. So, if you have three-dimensional space, you just have 3 terms, your n will be 3. If you have 37,000 dimensions, the n will be 37,000, so on and so forth. But it still holds. So this essentially gives you the length of the vector. This gives you the length of the vector. You just multiply them together. So Given the document term frequency matrix here, which we saw in the previous video, we can actually do some calculations. So the cosine similarity of doc 1 and doc 2, not surprisingly, is 6 times 10, 10 times 3, that's your numerator, and then 6 squared plus 10 squared, 6 squared plus 10 squared, times 10 squared plus 3 squared, which gives you 60 plus 30, so on and so forth. And then over here you get 0.7391963. That's the similarity between doc 1 and doc 2. Notice how the math actually is relatively simple here. It's because we're only dealing with 2 dimensions. Now, obviously, if this was a 300 dimension table, right, like we did, as you saw when we SVD'd down to 300 columns, this calculation gets pretty hairy. It's not difficult. It's just big, right? So it's prone for error by doing it by hand. Lucky for us, we can stand on the shoulders of giants and use our libraries to calculate it, but it's still worthwhile to know how the calculations are actually done. Okay. Not surprisingly, we can also do the cosine similarity between doc 1 and doc 3. And I won't drain the math. You can easily plug and chug. But here's the thing that you want to take a look at. This matches our intuition. Notice that the cosine similarity between doc 1 and doc 3 is 0.9518606. It's quite a bit higher. Almost, about 21 point something higher than this. That's good. That's good. Now, here's the thing. Do not interpret this as a percentage. This doesn't say that doc 1 and doc 2 are 74% similar. It's not. You can't think of it that way. You can't think that doc 1 and doc 3 are 95% similar. You can't think of it that way. How you can think of this, though, is in terms of relative similarity. This is substantially more substantially more similar. Substantially more similar than this is. It's about 22% more similar than this is. Not in absolute terms, right? You can think of these in terms of the differences because it's on a scale from 0 to 1. This one is about 21% higher than this one on that scale. Notice that I'm comparing these two values. I'm not comparing the docs themselves, just these two values. That's logical and okay to do. Just remember, this doesn't mean 74%. This doesn't mean 95% similarity between the documents. But you can compare these two numbers to each other and say this one is about 21% higher than that one. That is okay. Okay, cosine similarity. Excellent. So let's go ahead and go back to R and actually see some code. Okay, so we're back in R. Let's go ahead and close this plot down. Let's go ahead and move on. So we can do cosine similarity calculations using any number of libraries in R. I've chosen to use LSA. That's just a choice that I did. Quantita can also calculate it, but for the purposes of this video, LSA works pretty well. So go ahead and load up the library, and if we run the help file on the cosine function, we get cosine measure of matrices. Okay, cool. But what's really germane is this right here. Calculates the cosine measures between two vectors or between all column vectors of a matrix. So what that means is, in the context of our PowerPoint slides that we just saw, I could use the cosine function here from the LSA package to calculate the cosine between doc 1 and doc 2, doc 1 and doc 3, and then doc 2 and doc 3. I can do that one by one. Or alternatively, I can just create a matrix. And if I make the columns of my matrix my individual documents, I can ask the cosine function from the LSA package just to calculate all the similarity scores all at once, which is nice because it means I write less code and I just let the computer run and plug and chug and calculate everything for me. So, which is nice. So as a consequence, we need to unpack this code so you can understand what's going on. So first up, let's take a look at train.svd. And if we do a quick dim on train.svd, as a reminder, you can see here that I have 3,901 rows. Each one of those is my training documents in 302 columns. And if you recall, the reason why we have 302 columns is because we took the 300 features that we pulled from our LSA, from our SVD, and then we added the label at the front. We made the first column the labels, ham or spam, and then the 302nd column ends up being the text length, which we just added as part of our last mighty random forest. So what we need essentially is everything but those two bookends. We don't need the label because obviously we're not going to be calculating cosine similarity on the label. And also we're not going to be calculating cosine similarity on the text length. That makes no sense because that's a feature that's totally outside of our vector space representation. So this code says, okay, R, go to this data frame, filter it, and specifically I want you to get rid of the first column and also the last column. Because if I highlight this code right here and run it real quick, you'll notice it'll spit out 302, which is the last column. So get rid of the first column and the last column. And you know that because I got a minus sign here. Okay, cool. So that whittles down my data frame to just the 300 vector space columns of features, okay, feature data. I then transform this into a matrix because cosine will not work on data frames. So this basically is I cast it. I transform from a data frame to a matrix. And then I transpose it. Because remember, the cosine function only works on column vectors. So I need to flip my matrix. Because right now, it's in a document term frequency format. But I can then flip it to be a term frequency document. And then my documents will now be the columns, and then I can calculate the cosine on it. So I'm using the transpose there to get to my documents to be the column vectors. I run cosine on it, and basically it gives me a nice large matrix, 3,901 by 3,901, with all the cosine similarities being populated between all the documents, which is nice. Now this code will take a number of minutes to run, so I've already ran it. So if you do dim on train.similarities, there you go. I've got 3,901 rows, 3,901 columns, and each individual cell is essentially an intersection of one document and another, and what's their cosine similarity. Sweet. So now I can start using that. All right. So what I'm going to do is I'm going to engineer a feature. And here's my hypothesis behind this feature. If I pull out all of the spam messages, if I find out in my training data what are all of the rows, all of the document rows that are spam messages, I can then say, look, you know what? I have a hypothesis that says, on average, any given spam message is going to have a higher average cosine similarity with all of the spam messages than ham would. That's going to be the hypothesis, right? This idea that's saying, look, spam messages should always have a higher cosine similarity with other spam messages than ham should with a spam message. Right? This is a core assumption we're making, that we can differentiate between ham and spam based on our vector space model, right? The way we represent our documents as vectors. So it stands to reason that the cosine similarity between, on average, the cosine similarity between spam messages is going to be higher than on average the cosine similarity between a ham message and a spam message. So we can actually build a feature to actually calculate that on a per document basis. Hey, for each document in our corpus, for each 3,901 documents, what is the average cosine similarity between that document and all of the spam messages in the training data? And in general, we would expect that spam messages would have a higher cosine similarity than ham. And then that way we can maybe feed that into a model and it'll improve the performance. Okay, so first thing we can do here is we can run this line of code, which essentially says, look, give me the indexes of all of the spam messages. Go through all of the labels, tell me which ones are spam. Just give me the numbers. So if I run this line of code, you can see down here, I will now have spam indexes, and there are 523 indexes. So out of the 3,901 training documents, 523 are spam, and 4, 5, 6, 8, 11, 14, so on and so forth are the row indexes for the spam messages. Okay, cool. So next up, I'm going to go ahead and just use a good old-fashioned for loop. It's not considered best R practices to use a for loop, but I think it's relatively intuitive, so I'm just going to go ahead and use a for loop. But to be able to store these values in the location, I need to pre-allocate a new column on my data frame. So I say R, go to the train.svd data frame, access it, and create a new column called spam similarity on it. And then I want you to fill it with zeros. Fill it with zeros. So I run this line of code, and if I pull train.svd up in the spreadsheet view, actually that's not going to work because it's too wide. But if you imagine, if you will, if you scrolled all the way over to the right, you would see a new column here called spam similarity, and it'd be filled with zeros. Filled with zeros. Okay. Now that I've got a placeholder, now that I have a storage location in my data frame to store these spam similarities, I can just go through row by row. So this code says, hey, R, just iterate. Take this variable I, make it 1 all the way through n rows. And once again, if you run this code, n rows gives you 3,901. So make I the value of 1, make it the value of 2, 3, 4, 5, so on and so forth, all the way up to a value of 3,901. Just iterate over this data frame. Okay, and here's what I want you to do. Overwrite each location of spam similarity, the first one, the second one, the third one, the fourth one, all the way up to the 3,901st one, and overwrite them each in turn with this value, which essentially is the mean. Calculate the average of the similarities, where the row in question is my current document, and then the columns are just the spam indexes. Now think about this for a second. Remember, our similarity matrix is 3,901 rows and 3,901 columns, which essentially means I can think of this as a two-dimensional representation of all my documents. So on the horizontal, I'm saying, hey, deal with the first row, deal with the second row, deal with the third row. But I want you to grab all of the similarities from the columns for just those documents that are spam. So this will say, look, here is, for row number 1, here is all of the cosine similarities for this with the spam messages. For row number 2, these are all the cosine similarities for all the spam messages. For row 335, these are all the cosine similarities for the spam messages. And just average them up. Sweet, right? Just give me the average. So if I run this code, it'll give me a nice new feature populated with all this goodness. Now, not surprisingly, we could go look at them. I could whittle the data down and pull it up in the spreadsheet view. But it's actually better to visualize what's going on with a feature. We teach this day 1 in the boot camp at Data Science Dojo. We teach all of our students this. Visualize, visualize, visualize. Super, super easy way for you to understand what's going on in your data, especially in the features that you engineer. So we're going to go use the ggplot2, the mighty ggplot2, to actually create a histogram to actually show how this feature works. In particular, we're going to do spam similarity along the x-axis. We're going to use label to fill it. And what we want to see is how well does this new feature differentiate ham from spam. So we can just go ahead and run all this code. And there you go. Voila. Now this is super awesome. Super awesome. Look at this. So along the x-axis here, this is the mean spam message cosine similarity. So on a per message basis, what is the average cosine similarity between that message and all the other spam messages that we have? And notice all the orange. And ham is orange. Notice all the orange down here. Only a little bit of spam. And notice spam. So this plot is indicative of our hypothesis maybe having some merit. Where we said, look, our hypothesis is in general, spam messages should have higher cosine similarity on average with other spam messages than they do with ham. And the opposite should also be true, that on average, ham messages should have lower cosine similarity with spam messages. And this plot seems to indicate that. So this is pretty exciting, right? This is indicative of maybe this is a pretty powerful feature. But as always, though, we just can't rely on the data per se or the visualization of the data per se. We have to actually run it through a model and test it out. So not surprisingly, once again, we're going to use our same process here. We're going to use tenfold cross-validation, repeated 3 times. We're going to build a mighty random forest each time with 500 trees. We're going to ask caret to try 7 different values for mtry being the number of random variables each tree gets to use as it builds itself, to find out which of those 7 values of mtry is actually the best. And then caret will find that model for you, build it with all of the remaining training data, and return it back to you. Okay. Now, as usual, this will take a while to run, so I've commented it out. And if you get the binaries from the GitHub, there'll be one called rf.cv.3.rdata. That's essentially the cached binary version of this run, which allows you just to load it up and take a look at it. So let's load it up, run the results, and as you can see here, these numbers look pretty high. Notice that mtry is 52. Now, if you remember, our first mighty random forest mtry value was 151. Then it came down to 101 when we added text length, and now we're at 52 when we added our second feature of spam similarity, which is pretty interesting. Notice that our accuracy is going up, and the number of trees that we need, the number of features, the number of random features that we need for each tree is going down. It's a strong signal. It's not definitive, but it's a strong signal. But as we were in last time, this is not enough. Let's take a look at the confusion matrix so we can actually drill down on this. Okay. So what we got going on here? Okay, so our accuracy went up. Our accuracy went up to 97.9%, which is great. This is sweet. But what's more important is to go down in the sensitivity and specificity to actually know what's going on. And here's the kicker. Our overall accuracy went up, but notice that our specificity actually went down vis-a-vis our previous random forest model. The specificity was nearly 100% in the previous model. Now it's down to 97.22%, but notice that we got quite a jump, or more than 1% jump in sensitivity. So what this means is the model has degraded in terms of being able to correctly identify spam. This number here in the confusion matrix has gone up, but this number has dropped quite a bit. If you recall, this was 100 in the last model. Now it's 69. And as we talked about before in our hypothetical business scenario, this is good because we're operating under the assumption that our customers are going to be more forgiving of an occasional spam message coming through erroneously than they are us taking a legitimate message and putting it in a spam folder, for example. So this is great. So what this shows is that maybe we found a feature that we can put together with our text length feature and then the rest of our 300 SVD features and get a pretty awesome model, 97.9% accurate. Okay, so that's pretty exciting. So we'll go ahead and stop the video there. Well, actually, you know what? Let's not do that. Let's take a look at one more thing here before we stop. And let's take a look at the importance plot. Okay, so check this out. Check this out. Now, if you remember on the previous plot, text length was way over here, and then x24 was way over here. Notice how spam similarity now dwarfs even text length and really scrunches up all of our text features. So what this is telling you is that spam similarity is a super, super powerful feature. Now, there's one thing we should probably mention. This is super exciting, but it also should be sending your data scientist spidey sense into overdrive, because this may be indicative of overfitting. You remember we said earlier that text length was a good feature because it raised both sensitivity and specificity at the same time. Notice that, in fact, spam similarity did not do that. It reduced specificity and increased sensitivity, which is okay from a business perspective. But when when it's combined with this dwarfing thing, how it becomes so much more important than everything else, this should send your spidey sense in overdrive saying, okay, I'm going to be a little skeptical. I'm cautiously optimistic that this feature is going to be awesome, but it may be overfitting. It may overfit. So we'll need to test that. So we will end the video here because this is a good place to pause and say, okay, look, next time we'll actually start working with our test data. We'll get it transformed into our vector space that we need it to be in and actually start running our test to actually say, look, you know what, is this model, is this mighty random forest with all of these features as awesome as we think it is now on our test data? And then we'll be able to verify a couple things. One is our model awesome? And then two, is this spam similarity feature awesome or is it overfitting? So you'll just have to wait until next time to find out the answer to that. Okay, so if you have any questions or concerns, please use the page for this video. We at Data Science Dojo monitor our YouTube channel often and try to answer any and all questions promptly. Also, if you like these tutorials, please subscribe to the YouTube channel. We'll be producing content on a weekly basis, and then that way you can keep abreast of our latest tutorials. More generally, if you like what we do at Data Science Dojo, you can follow us on Twitter, LinkedIn, Facebook, all the social media channels where we provide our subscribers with a font of curated data science goodness. And lastly, I hope to see you in an upcoming Data Science Dojo bootcamp. This is Dave Langer, signing off and wishing you very happy data sleuthing. Hi, welcome to video number 11 in Data Science Dojo's series on Introduction to Text Analytics with R. I am your host, Dave Langer. So what we have here is an RStudio environment where all of the code through the end of video 10 has been executed. And at the end of video 10, we built a very powerful model, a model that achieved more than 97% accuracy in terms of detecting ham versus spam in our text messages as measured by tenfold cross-validation repeated 3 times. We used a mighty random forest. That code took a long time to run, so what we did is we loaded up some binaries that I had pre-ran and cached in the GitHub to actually see what the performance was. Now, one of the things that we looked at last time, which bears repeating, is that when we look at the variable importance plot here, we noticed that when we added spam similarity, it became very, very important. It was like way out here. It essentially dwarfed all the other features that we had. And what we also saw was there was some indications here that maybe spam similarity, while quite an effective feature as measured by our cross-validation runs, may potentially be a problem for us in terms of overfitting for 2 reasons. 1, because it so much dominates everything else. And 2, because when we looked at the sensitivity and specificity, we saw that this particular feature actually helped us detect ham correctly, but it actually decreased our ability to detect spam. So we thought, it didn't raise both of those metrics simultaneously. That could be indicative of a potential for this to overfit. But there's only one way to be absolutely sure about that, and that's what we're going to start working on in this video, which is let's start prepping our test data, the 30% that we held out for testing, that needs to be set up. Now, what we have is essentially our test data from way back from video 1, video 2, video 3, but it hasn't actually been pre-processed. So we've done a lot of work in this video series on our training data. We've tokenized, we've lowercased, we've removed stop words, we've performed stemming, we've added bigrams, we've done things like TF-IDF, and we've done SVD. All of those sorts of things now have to be done to the test data as well, because we have a trained model. But we've pre-processed the training data so much that the model can only work with data in that similar format. So everything that we've done to the training data, we now have to do to the test data as well to get it in the right format, to get it in the right semantic space, to get it in the right geometry so that it will work with our trained model. So that's what we're going to do. So looking at the code, go ahead and expand this a little bit. Not surprising, the first thing we're going to do is we're going to tokenize, just like we saw before. We're going to tokenize, we're then going to lowercase, we're going to remove stop words, we're then going to stem, we're going to add bigrams, and then we're going to convert this to our document term frequency matrix. So we can go ahead and run all this code right here real quick. And here's the first thing that you notice. Right? So we have Our training data has 3,901 documents. We're totally familiar with that. We've seen that all along in this video series. And our training data has 29,297 features, and it's 99.9% sparse. Now, what's super interesting about the test data is that, not surprisingly, because there's this much smaller number of documents, right, less than half the number of documents, notice that we have less than half the features. Now, that's going to be super interesting because, not surprisingly, our machine learning model that we've trained expects the same features that it's always seen when it's working on test data. So, for example, assuming that we didn't do any SVD, let's say we didn't get down to 300 singular vectors, which is just working with the bigrams, the unigrams and bigrams in TF-IDF, we would expect that these two numbers to be exactly the same because our model is expecting, in the case of not using SVD, 29,297 features. That's the sum total of the unigrams and bigrams. And that's what it expects. It says, look, I need a data frame that's 29,297 features wide. I don't understand anything else. You can send me more data than that. That's fine. But you have to send me at least the 29,297 features that I've been trained with. That's the data I expect. That's the contract that you and I have. Now, you'll notice here that we don't have that. So we're going to have to fix this up later. So this is super important to realize in the beginning, which is this. When you do text analytics in particular, you're going to train on a historical set of data. That historical set of data is going to have a collection of words, a collection of bigrams, a collection of trigrams that reflect the data that you had at that point in time. It's fully expected that in production, after you move a text analytics model in production, that you're going to see documents with new words in them. And in text and tweets, for example, this is extremely common, that people will actually morph the types of characters and words and phrases that they use over time. And you would fully expect that there's going to be this gradual diversion between the nature of the textual data that you're going to get in production with your new data versus what you train your model on. And this is a prime example of that right here. We can see for a fact that even with our 70-30 split of our data, we're getting different numbers of features, and that's totally expected. So it's totally expected. So we're going to be doing things with our test data to essentially morph, make, transform new test data so that it looks like our older training data. And this is what happens all the time in text analytics systems in production. And one of the things that you have to realize is that your text analytics models, once they get put in production, eventually become stale. They eventually need to be retrained because eventually you'll get an ever-increasing amount of new types of words, new types of bigrams and trigrams in your test data that are not reflected in your model and can't actually be used. Essentially, we're going to have to strip them out, and we'll see how that's done later. We'll have to strip them out. And at a certain point, that sheer amount of data that you've never seen before becomes so valuable that you want to incorporate it into your model, which essentially means your model gets stale and it needs to be retrained from scratch and redeployed. So that's one thing you need to be very clear on when you're engaging these types of projects with your stakeholders is that, look, once we build a text analytics model and put it in production, you're not done. That model will need constant care and feeding. It'll need refreshing over time. Ergo, it's going to need budget. It's going to need staff to actually do that sort of work. Okay, enough about that. Okay, so we've got our document term frequency matrices, no problem. So here's the step that I mentioned. So we need to make sure that our test document term frequency matrices, tables, data frames, have to look exactly like the DFMs that we used for training, right? Because if they don't, when we do TF-IDF, when we do SVD, it won't be valid. Those transformations on the test data will not be valid. Ergo, our predictions will not be valid. So we have to make sure we do all the things, all the pre-processing exactly the same way between training and test. And then we have to ensure that the base document term frequency matrix, the DFM, is exactly the same in terms of the number of columns. Not only the number of columns, but also each column has to be in exactly the same order, and it also has to have exactly the same meaning in terms of the order. So, for example, if column 37 was the word fluke, I'm just making this up. If column 37 in training was the word fluke, column 37 in the test data frame also needs to be the term fluke. So they have to be exactly aligned. So this code actually does this. So you can see here the DFM select, and as always, don't hesitate to use the help system, DFM select. Select features from a DFM or FCM. Okay. Now if we do this and run these 3 lines of code, you'll see exactly what I'm talking about. Look at that. Notice that I've got 29,297 features. This is great, right? This means that now my 2 DFMs are aligned. The training DFM had a particular structure. We have now enforced that the test DFM has that exact structure, which is great because now we can apply our additional transformations. So next up, we're going to go ahead and, of course, use the mighty TF-IDF on the test data. Now, as I mentioned earlier in the series more than once, and it bears repeating because it's so important, notice this is why we've had to cache the IDF values. Remember earlier I made a big speech about how we have to cache the IDF values, no matter if you write the code yourself or if you use another package that somebody else wrote in R. The original IDF values have to be maintained from the training examples because we know now that the DFMs are going to look the same. We're going to force them to look the same between train and test, but in fact they are not exactly the same. Ergo, to correctly project the new test data into the same vector space, the same TF-IDF vector space that we created for training data, we need to reuse the same IDF values from the training data. Okay, so I won't drain this code because essentially we've seen it all before. First thing that we can do is we can apply the TF calculation to our test matrix, and that'll come up here shortly, and we can see the structure of the resulting calculation. Okay. Notice there, we've got our terms have now been the rows and our documents are now in the columns, just as we saw before. And then we'll go ahead and apply the TF-IDF calculation. Now notice here, this is super important. We're reusing the IDF values that we calculated from the training data. This is super important. This is super important because in production, you're going to get new rows one at a time, right? New texts are going to come through one at a time, let's say in a hypothetical production system, and we're going to need to project each one of those texts one at a time into the same vector space. So we have to have the IDF values to do that. So we'll go ahead and run all the rest of these lines of code. Now, one thing to mention while that code is running is that when you're looking at doing TF-IDF in a production system, be very, very sure that if you decide to use a package, that the package's API, the collection of functions that it provides, will actually allow you to calculate an IDF, all the IDF vector values for the training data and then maintain them over time, because some of the libraries just kind of assume that all of your data is just in one big matrix and you don't have access to the actual underlying IDF values. And of course that won't work for you in a production system. Okay. So you can see here, everything has been ran just fine. We're going to fix the incomplete cases, and you can see here that based on our summary, we in fact have no missing values, so everything's good to go. So now, just to recap, we've taken our text data, we've done our text preprocessing. We tokenized, we lowercased, we removed stop words, we stemmed, we removed punctuation, all that good stuff. All that stuff is gone. We added unigrams and bigrams. We created DFM. We've now TF-IDF'd that DFM after we made sure that DFM had the same structure as our training DFM. So now, not surprisingly, the last thing that we need to do is we need to actually apply our SVD projection, right? Because that was the last step. We need to actually get down from our 29,297 columns down to the 300 singular vectors from our SVD that are the most predictive. And this is the calculation that does that. And we saw this in video 8 when we looked at the mathematics, the slide. There's a slide that showed this equation. So essentially what we need to do is we need to take the inverse, the sigma inverse, right? This is the inverse of the singular values. we multiply that by the transpose of the U matrix, which essentially is the eigenvectors of the term correlations. And then lastly, we need to then multiply that by the transpose of our actual TF-IDF data frame. So if I run this line of code here, and it'll take a second here to run, and what we should get back is a nice data frame that will be 1,600 or so rows, because that's the number of documents that we have, number of texts in our test set, and then also should have 300 columns. So if we do svd raw, there you go. 1,671 rows. Each row is one of our test tweets, and then our 300 columns. Notice that these dimensions are extremely important, especially this 300 columns, right? We have now projected our test data into the same semantic space, latent semantic space that our training data resides. So this is really super cool. Okay, now we can build ourselves a test data frame. You can see here, we're going to have our test data. It's got our labels from our test data. We got our SVD raw features, and then we're going to add text length. All right, this mimics the same features that we had in our training data. And then next up, we're going to add similarities, because remember, we said we're kind of concerned about this spam similarity calculation, but we should certainly test it out just to make sure, we have a hypothesis, but as data scientists, we want to verify our hypotheses with data. So we're going to go ahead and test out how accurate our predictions are on the test set with the similarities thrown in. Okay, so this code probably bears a little bit of explanation. So first thing that we're going to do is we've got our raw data, or our SVD data, right? We have 1,671 rows of our test text messages, 1,671 rows. And then we have our 300 columns, of SVD'd features for the test data. That's going to be the basis. And then what we're going to do is we're going to add rows. We're going to add rows at the bottom. Here. And what we're going to add is we're just going to go back to the original training data, the SVD training data, and say, okay, look, what we really need to do here is we need to actually pull out those vectors that correlate to the spam. Right? So if I run spam indexes here, you can see we calculated those before. These are all the indexes in the training data of the text messages that are spam. And we have, a little over 500 of them. So this says, look, go back to the training data, grab only the vectors that correspond to spam. And in particular, grab the document vectors, right? So these are the projection of the spam SMS messages into the latent semantic space. So we say, okay, look, take our test data and then graft onto the end of that the rows that give us the spam. So that essentially gives us a data frame with our the documents that we care about, right, which are the text messages. But we're also adding in the data for the spam, the representation of the spam SMS messages, because we'll need that to actually calculate the average similarity between each individual text message and spam. Okay. Now what we do here is we say, okay, look, we've got this data frame. Let's go ahead and calculate the cosines between them. I'm just going to run this code and explain it while it's running. So we're going to say, okay, look, you know what? We've got the first 1,670 rows of our test.similarities data frame is our test text messages. The next 500 or so rows is the spam SMS messages that we got from the training data set. And then we'll say, okay, look, we know that cosine similarity will calculate cosines between all column vectors in a table. So what we do is we say, okay, fine, look, if we transpose this, our documents now become the columns, right? Because they're rows in the test.similarities data frame. So transposing it will actually make the documents into the document rows into the document columns. And then cosine will calculate all the similarities between these documents, which will be cool because it'll make our calculations a lot easier, as we'll see in the next line of code. Okay, So you can see here, I'm going to go ahead and pre-populate a spam similarity feature on our test SVD data frame. This will be the placeholder that will hold all of these similarity values. And then we're going to go and say, okay, look, the spam columns in our new test similarities data frame is essentially all of the columns that start after the original test data and go to the end. So let me explain what that means in a little bit more detail, right? So if we do the dimension on test.similarities, it should be about 2,200 rows. 2,200 rows and 2,200 columns, right? It's a square matrices, right? But we know that not every column and every row is actually a spam message. We know that only the end rows and the end columns actually correspond to the spam messages, because remember, we added to the end up here the spam messages. Okay, great. So this actually tells us what actually is the spam columns in terms of numbers. And you can see here, if I just run this real quick, you can see, yep, it's everything starting at 1672. Notice that's one more than we actually have in terms of test rows, all the way up through 2194. Okay, cool. And that allows us to do a nice simple calculation right here. Go through every row in the test set, every row in the test.svd data frame, every row, and calculate the spam similarity. And all the spam similarity is the average, the mean, of the trained similarities for that row in question and the spam column. The spam columns, right? That actually calculates them on an individual basis. Okay, this mimics the code that we saw before. All right, so we run all that. And you can see now that we've got our spam similarity feature is now totally calculated. So now we can create some predictions, right? So we can say, okay, look, you know what? Take our third random forest that we created from cross-validation, right, which we saw was over 97% accurate as measured by cross-validation, and then use that mighty random forest that we built to create some predictions for the test data. And then we can do a confusion matrix on our predictions versus the actual labels right here. So let's go ahead and run that code. And this output is super interesting. Super interesting. Okay. Look at this. A commonly used definition of what is known as overfitting in machine learning is doing much worse on test data than you did on your training data. Now, in our training data, as measured by 10-fold cross-validation repeated 3 times, our mighty random forest scored over 97% accuracy. And notice here that on test data, it only scores 86.59% accuracy. And more importantly, notice this. Our sensitivity is 100% and our specificity is 0, because our model predicts that everything is ham. Our model predicts that everything is ham. It doesn't even try to say that anything's spam. It just says, look, you know what? Everything's ham. It's all good. All these text messages are good. It's not a problem. Now, we know that to be patently false. We know that because we created stratified samples for both training and test. So we know the proportion of the spam messages in the test data set mimics that of the training data set. So we know for a fact there's spam in there. But our model currently, given the features that we provided to it, automatically assumes that everything is ham. Now, we had a hypothesis that said, look, this could be the direct result of the fact that our spam similarity feature is going to overfit, because essentially what it does is the spam similarity feature is very, very good at differentiating ham from spam in our training data only. It does not generalize to data it's never seen before. It's too tightly bound to the training data. Ergo, it's probably a risky feature to have. And this kind of bears it out. This says, look, you know what? Okay, yeah, I have almost an 11% drop in accuracy, and I'm predicting everything to be ham, just blanket. So that, I mean, this isn't This is not a good situation. So this is highly indicative of overfitting. Okay, so this is a great place to end video number 11. We've accomplished a lot in this video. Most importantly, we've discussed arguably one of the most important things in rolling out a production text analytics solution, and that is being very deliberate, being very careful to ensure that when we have brand new data, in this case SMS text messages, that come into the system, that we perform all the transformations, all the tokenization, the stemming, the stop word removal, the bigram, trigram, whatever, TF-IDF calculations, and lastly, the latent semantic analysis projections to make sure that that test data lands in a format, lands in a geometry that our trained model first of all understands, and then two, can actually work with productively. Because here's the worst case scenario. Worst case scenario is that you do something funky in your data pipeline. Maybe you have a bug, maybe you missed a step, what have you. And what happens is that the model recognizes the data. It doesn't say there's any format error, but yet the projection, the final representation of that test data, is not actually in the exact format which the trained model can work with most effectively. And what you end up getting essentially is no error information from the code, but what you get are essentially suboptimal predictions. That's the worst case scenario. Another scenario which is bad, but not nearly as bad, is that you make a mistake in your pipeline, you submit the new text information for a prediction, and the code just throws an error saying, look, I don't know what to do with this record. It's not in the format I expect, or maybe there's some other sort of error. That's actually, it's bad, but it's far less insidious than the previous problem, which is you get no error signal at all. You just get a bad customer experience. So we've covered this in depth. Hopefully you understand how important this is. Okay, the next video in the series, video number 12, will be the conclusion. We will wrap up. We will show how we can fix this current situation where we are obviously overfitting. You know, here our model is around 11% lower in accuracy on the test holdout than it is in our cross-validation runs. And we're going to see how by eliminating the spam similarity feature, we'll actually increase our accuracy on a test holdout, which shows us that removing spam similarity is indicative of producing a model that is more generalizable, that is one that will work better on unseen data in production. Okay, so if you like what we're doing here on the Data Science Dojo YouTube channel, please subscribe. We'll be producing new content weekly, and if you subscribe, that's the best way to keep abreast of our latest tutorials. Also, if you have any questions at all about this video series, feel free to use the comments section of this video. We at Data Science Dojo, we monitor our YouTube channel frequently, and we try to answer any and all questions promptly. Next up, if you like what we do at Data Science Dojo more generally, we're on social media. So if you follow us on Facebook or Twitter or LinkedIn, you can tap into a curated stream of data science goodness that you may find useful in your daily work. And lastly, I hope to see you in an upcoming Data Science Dojo bootcamp. This is Dave Langer signing off. And until next time, I wish you very happy data sleuthing. Greetings. Welcome to video number 12 and the conclusion of Data Science Dojo's Intro to Text Analytics with R. I am your host, Dave Langer. Okay, per our process, what I've got here is a handy-dandy RStudio environment with all the code executed through the end of video 11. Now, where we ended up in video 11 was a bad spot. Specifically, we saw that on our test run, our mighty random forest, which scored over 97% accuracy in our cross-validation runs, in fact scored quite a bit less, almost 11% less in accuracy. As you can see here, 86.59% accuracy. And we had a hypothesis early on that was going to, this might happen because we engineered a feature in our training data, which essentially said, look, for each individual text message in the training set, what was its average cosine similarity to all of the spam messages in the training set? And we saw that that was actually a pretty good feature. It actually gave us a lot of power, a lot of predictive power in our cross-validation runs. However, we also hypothesized, we also worried that that feature may overfit because the characteristics of spam in the training set may not necessarily be the same as the characteristics of spam in the test set. And ergo, that feature may be very, very powerful, but only in terms of the training data. And this hypothesis has been borne out by what we see here, which is this accuracy, which is far lower than what we saw in our cross-validation runs on the training data. And as we talked about before, one common definition of what is known as overfitting in machine learning is when you do much, much better on your training data, as measured by cross-validation, than you do on test or unseen data, which we see here. And we said, even worse yet, than an 11-point drop in accuracy was the actual behavior that we saw, which essentially the predictions from the mighty random forest said, look, none of the test data is spam. It's all good. It's all good. And we know that to be patently false. But what we saw here essentially is the definition of overfitting. The model that we trained cannot recognize spam anymore in unseen data because it is bound too closely to the training data. It is memorized, if you will, or it has almost memorized the characteristics of ham and spam in the training data. And by doing that, by being over-specialized, it isn't very good in the real world when it sees brand new data that it's never seen before. And this is what we see here. So what we said was, look, you know what, let's backpedal a little bit and let's take out the cosine similarity, the similarity feature from the training data and see if we actually can get some generalization back into the model. So that's what we'll do right now. So if you see here, it's pretty easy to do in R. If you set a column on a data frame, a variable on a data frame to null, it gets removed. So what I'm doing here in these two lines of code is I'm removing the spam similarity from the training data and the spam similarity feature from the test data, getting rid of it. We're keeping text length because we saw that text length was a good feature because not only did it raise our overall accuracy, it simultaneously raised both our sensitivity and our specificity. And we hypothesized that, well, that's probably indicative of a good feature. So we should probably keep that one in. So that's what we're going to do here. So I've actually ran this code previously just so that you wouldn't have to wait to see it run. And you'll see why in a second. So I won't run these two lines of code because I already have. Now, next up, I'm running this code, and the code in the GitHub, this will be really important. The code in the GitHub, it will be configured for 10 logical cores. I actually ran this on my laptop, which is what I use to record the videos. So I turned the cluster cores down to 3 because I only have 4 logical cores on my laptop. So you will want to adjust this number based on the power of your machine. That is the CPU, how many cores, how many logical cores it has. By default, the code is set up to run on a workstation class machine with at least 10 logical cores. So be sure to change this if you run the code directly. Otherwise, you'll get your computer will not be happy with you. Let's put it that way. Okay, so to give you some idea of the execution time here, as we've seen in the code, I've just set up a poor man's timer essentially for recording how long it took to run the code. So I set up a cluster here using the do-snow package, and I'm asking it to use 3 logical cores. I started my timer. I then set the seed, and the reason why I did this was I wanted to ensure that if anyone who run this code directly would see the same results that I see. And the easiest way to do that with a random forest is just to explicitly set the seed. Now, I wouldn't do this in a production scenario, but since this is a tutorial, a teaching tool, and it helps when students see the same thing on their local machine as they do on the video, that's why I'm setting the seed explicitly here. Now, I'm doing another cross-validation run. This is everything we've seen before. I'm trying to predict the label, ham or spam, based on the rest of the features. I'm using a mighty random forest. I'm using the same train control setup that we've been using all along, which is 10-fold cross-validation repeated 3 times. I'm also asking, per the usual, that caret use 7 different values of the mtry parameter, the number of features that are given to each split in each decision tree in the random forest, to find out which one of those values works the best in terms of accuracy. And then we stop the cluster when we're done, and we take another timestamp so that we can actually say, okay, how long did this execute? And if I scroll down here, you can see the results. So on my laptop, using 3 cores, this took 2.5 hours to run. So just to give you some idea of how intense this is. Obviously, if you have more cores, it's going to run faster. but it took 2.5 hours. So I just basically fired this off and then went off and hung out with my wife while it executed in the evening. But what we get out of that essentially is a nice random forest. And of course, actually, you know what, let's go ahead and take a look at what we see here in terms of our predictions. So I'm using the cross-validation run, and the predict function will automatically pick out the best final trained random forest automatically and create predictions on our test data set. And then we're using the confusion matrix function out of the caret package per usual. And we can see the results here. So you'll notice that our accuracy jumped up a lot by almost 10%. So we had, what did we have before here? We had 86.59%, and now we have 96.47%. So almost a 10% jump in accuracy by removing that the spam similarity feature. So we kept text length in, and then we had our 300 features that we engineered, that we extracted using singular value decomposition, latent semantic analysis. And you can see here that we get a generalization score very, very close to what we saw with our training data using our 10-fold cross-validation run with the text length added, but not the spam similarity feature added. And this is good, because what this does is this is a strong indication that we have built a generalizable model. Now, what's a little bit disconcerting, though, is that what we don't get is nearly the balanced performance in terms of sensitivity and specificity that we saw in cross-validation. And this is common, by the way. These results that we see here are common. They typically won't be as good on unseen data as they are on training data. That's just kind of the general rule. This is actually quite good, as measured by overall accuracy. But when we drill in on the sensitivity and specificity in particular here, we can see that we've given some stuff up in terms of actual performance and unseen data when we compare it to the performance as measured by our cross-validation repeated 3 times. We saw that our sensitivity and specificity were both very, very good. They were in the 90s before, but now what we see here is we're very, very good at correctly predicting ham, but we're not very good at correctly predicting spam. Now, if we look at the confusion matrix, we can actually see the trade-off and put it in the context of what the end user experience was going to be like. So we can see here that our prediction of ham was great. So everything that was ham, we got 100% correctly, which was good, right? Because we hypothesized that in the real world, our customers would prefer us never to misclassify their actual legitimate text messages as spam. They would, because they may not see them, because they may go to a spam folder, you may just pull them out of the feed or whatever. So we hypothesized that, look, we very much want to make sure that all the ham gets through from a business perspective. That's a reasonable approach. So that's the good news, is that right now we perfectly predict all the ham. Now, what the bad side is we do let a little bit of spam through, right? Which is why our specificity is quite low, because you can see here that out of all of the spam messages, 59 of them, almost actually more than a quarter of them, actually get through. Right? Our specificity says, look, we only classify correctly spam about 73.66% of the time. So that means more than 25%, more than 1 in 4 spam texts get through. But our overall accuracy is quite high, 96.47%. And given the nature of the business problem, that maybe a little bit of spam getting through, but all the ham always gets through, might not be such a bad thing. This may be a reasonable trade-off in the business world, and this is something that you see often when you do text analytics models in production, which is nothing's ever going to be perfect. So you need to negotiate with the decision makers to say, okay, look, here's what we can do. Is it acceptable from a business perspective? For me personally, my gut would tell me this is not bad. This is not bad. Now, could it be improved? Absolutely. Absolutely. And we'll talk more about that in some slides at the end, towards the end of the video. But right now, this is pretty good. I think this is great, that we've got 96.4% accuracy on our test holdout, on brand new unseen data. This is a very, very strong indicator that, in fact, you can use historical text messages as embodied by our data set You can extract features from it, and you can build models that, in fact, are useful for future unseen data as measured by our test holdout here. So this is really, really cool. Okay. So lastly, let's take a look at our cross-validation run so we can compare what the cross-validation estimates were vis-a-vis our test holdout. So here you can see the results from a cross-validation run. And Carrot says, look, Dave, I tried out 7 different values of mtry using 10-fold cross-validation repeated 3 times. And I found that the best value out of the 7 that I tried was 101. And you'll see here that the accuracy as measured by the cross-validation runs is about 97%, which is actually very, very close to what we see here, right? Only a little over maybe a 0.5% difference. So this is great. This is great. This tells you that given the feature set that we have, the feature hit, the 300 features that we extracted using SVD, text length only, seems to be a very good set of features, very generalizable, as measured by both not only our cross-validation run, which is an estimate of generalization error, but also as embodied by our test holdout set, which is an even more indicative estimate of what our error rate or accuracy, reflexively our accuracy, will be in production. Okay, so there you have it. That'll conclude all of the code for this series. You've got a firm foundation in text analytics now. It's a great introduction. We'll flip over to some slides now so that we can talk about, for those of you that are interested in pursuing text analytics further, what your next steps may be. Okay, for those of you that are interested in exploring text analytics further, and hopefully I've whetted your appetite for text analytics, it's one of my absolute favorite things and wildly, wildly useful in practice. Okay, so in general, what's next? You say, okay, Dave, what should I tackle next? If I'm interested in learning more about it, what can I do? Well, you can take the code, you can take the data that we've been using throughout this series, and you can actually expand upon it. You can actually engage in some additional feature engineering exercises on your own to see if you can improve the score, right? We saw that our sensitivity was 100% on our test holdout, but our specificity was quite low, around 73-ish%. So there's a lot of opportunity there to maybe engineer some better features that could improve that performance. So for example, what about adding trigrams and 4grams? 5 grams, 6 grams? That may be helpful. It's something to try out. We only used unigrams and bigrams in this, and we got a pretty good score. So maybe if you went to trigrams as well, maybe you get better performance. Also, you never know as well, you may find that using just bigrams, and we're using unigrams and bigrams, but maybe you just try out bigrams by themselves, and maybe bigrams work better than bigrams and unigrams, or bigrams and trigrams. There's a whole bunch of different combinations that you can try if you're interested. And sometimes an unintuitive combination may actually work better than what you started with. So for example, and I'm just making this up, maybe the combination of 2 grams and 4 grams, but not 1 grams and 3 grams, just 2 grams and 4 grams actually works the best. Sometimes it's entirely possible that could happen. So there's a lot you can explore there. We also engineered text length. We saw that text length was a good generalizable feature. Well, at least measured by our test holdout set, it was a good generalizable feature. We also engineered spam similarity. That turned out to be not so good. But there may be other features like text length that you could engineer. So it may be worth some time in a benefit of your skill building to say, look, what are some other features that I could potentially engineer and test them out to see how they work. Now, next up, algorithms. So we leveraged a mighty random forest, and that was purely an arbitrary decision on my part, mainly because they are a good general purpose algorithm. They're not always the best in every situation, but they are a good general purpose algorithm, and they're very easy to tune, which is why I chose to use them. However, it may not necessarily work the best on this data set. So for example, could you get better performance if you use boosted decision trees? Something like the mighty XGBoost package in R may actually give you better performance than a mighty random forest. So you could try that out. Also, almost a de facto standard in the text analytics space is the use of support vector machines, or SVMs. You could certainly try out SVMs as well. They may actually work better than a mighty random forest. And as we talked about previously, the reason for that is that text analytics features tend to be very, very low signal. Remember we said, look, that text analytics explodes your feature space, explodes the number of columns that you have, but those columns are mainly empty because of the sparsity problem. Ergo, each individual column doesn't have a lot of predictive signal in it. And as we saw, the mighty random forest worked much better with SVD, collapsed down features to 300 rather than working with all 22,000-ish features. SVMs tend to actually work okay in high dimensional spaces where each individual variable, each individual column has a low amount of signal, which is why they're commonly used in text analytics. So that may be something you may want to try. And then lastly, you can always learn more ways to analyze, understand, and work with text. I mean, this is just the tip of the iceberg, what we've covered. I know it's about 6 hours of content, but it's just the tip of the iceberg. So on this last bullet, I wanted to expand on this and give you some interesting resources that you may find useful if you want to pursue text analytics more in depth. Okay, so here's what I always recommend. This book by Matthew I think it's Jockers, maybe. Jockers. I'm not quite sure how you pronounce the gentleman's last name. Anyway, so he's a professor, and he works essentially in a literature department at a university here in the United States. And oddly enough, lots and lots of folks who study literature at university in the U.S. are getting into R. They're doing a lot of text analytics these days. So he wrote a book specifically on how to do text analysis with R for students of literature. So this is really, really cool for a couple of reasons. One is this is arguably the best introduction that I've found to thinking analytically about text. You think about it, if you're a literature student, let's say you're getting a PhD in English literature, let's say, and you want to analyze the literature that you're doing, you need a guide. You need to think about it in a very analytical way. And this book is really, really great about introducing the basics of how you think about text analytically. So this is great for that. Because it was written specifically for literature students, folks who most likely do not have strong mathematics or programming background, it is extremely accessible to a broad audience. I mean, if you've never coded R before, you could probably learn a lot of R coding and a lot of goodness just by reading this book, just to start with. This is just great for that. Also, the book also illustrates some techniques that we don't cover in this series. For example, it covers topic modeling, which is a very, very useful technique in text analytics. You can create topic models, and then and the book shows you how to create topic models and then visualize them as word clouds. People love word clouds, and for good reason. They're a good way to gain a high-level understanding analytically about maybe the themes or topics that are going on in a body of text. So there's a lot of goodness in this book. So I always recommend people start here if they're really getting serious about text analytics. So next up is a book called Taming Text. Now, this book is actually written for Java programmers. Now, you may be saying, Dave, heresy. Dave, this is heresy. What are you doing? The reason why this book is super useful is that there is a lot of theory in the book. I mean, honestly, if you didn't feel inclined to understand the Java code that's actually in there, it's okay. I would still say read the book anyway, because it teaches you a lot about theory. And there are packages that implement all of the theory that is talked about in this book. And this book is very, very well written. It's not very long. It's not particularly dense mathematically. It covers a lot of good theory. And then what it does is it provides you a nice foundation. And then later on, when we go look at the library of R packages that do text analytics, you'll understand what the packages are used for, because this book will teach you the theory. Now, probably most importantly is there's good coverage in this book about the OpenNLP package. Now, OpenNLP was originally written in Java. There is an R wrapper called OpenNLP, that's the name of the package, that wraps this. So you can actually use OpenNLP from R, and it actually does a lot of really cool things, like part of speech tagging. It allows you to help you do chunking and things like that. So reading this book will teach you about the OpenNLP package, and this is directly relatable to R because R has a wrapper for it. So this is a great book. Okay, so once you've read those first two books, you're going to get a good foundation for text analytics. The first book will teach you a lot of practice and some ideas about analysis of text. Taming Text will teach you a lot about the theory. And then it's time to actually go say, okay, look, you know what? I know enough. Let's go see what R offers for me. So the first thing that you want to do is you want to go to the NLP task view on CRAN. I mean, literally, you can just Google this right here. Just Google this right here, CRAN NLP task view, and you'll get the page. You click on it, and what you'll get is a big long list of all of the packages in the R universe that work with text analytics. If you're not familiar, NLP stands for natural language processing. You can kind of think of it as a synonym for text analytics. After you've studied taming text in particular, you'll know so much more about what these packages, what they do and what they would be used for, and how you would structure them in as part of your pipeline and as part of your solution. So that's why I recommend reading Taming Text first, and then go to the CRAN NLP task view, and then you're off and running. Okay, next up, here's an easy way to think about search. Think about Google, think about Yahoo, think about search in SharePoint, you name it, on Amazon's website, on Netflix's website, you name it, right? Search is everywhere. Search is basically a text analytics problem. So actually studying information retrieval, which is the branch of computer science, if you will, that focuses on search, is actually a good idea. There's a lot of goodness to be gleaned from it. And this book right here is the single best resource for IR for beginners. This is great, information retrieval. It talks a lot about some of the concepts that we discussed today. It talks about singular value decomposition and LSA. In information retrieval, they call LSA LSI, latent semantic indexing, but it's the same thing. This book talks a lot about the vector space model. It talks about cosine similarity. It talks about naive Bayes. It talks about a lot of stuff. So this is a really, really good book for you to go into to expand your knowledge and understand it more, because think about it, right? If I've got to search through mountains of text, I need to do text analytics and understand those features and structure my solution in such a way that my search engine gives you relevant results. Most of these tools and techniques are useful also for classification as well. So the good news is that you can buy this book. You can certainly buy it from Amazon, but it's also available free online from Stanford. So this is great. It's a great resource. You can just read it online. It's free. Covers awesome amount of stuff. So I highly recommend this book as well for folks once they reach a certain stage of text analytics and they're interested in going further and further and further. And then lastly, Python. Now, those of you who have either attended my talks or have attended the Data Science Dojo Bootcamp know that I am an R aficionado. I am an R fanboy. I do use Python occasionally, and typically the only time I use Python is text analytics. And the reason for this is simple. Python has the Natural Language Toolkit, the NLTK. It is pure, unadulterated awesomeness. In R, you can do everything with text analytics in R that you can do with Python. Don't get me wrong, you can absolutely do this. There's no problem. The only downside is that in R, you typically have to use a number of packages to get it done. In Python, you've got a one-stop shop. It's the NLTK. So it's a really, really good, powerful library. Not surprisingly, the book about it is also extremely useful for R programmers doing text analytics as well, because this book contains a lot of theory. It talks about chunking. It talks about a lot of natural language processing, a lot of text analytics techniques that you can all do with R with the right packages and everything. You can totally do it in R. But there's not a really necessarily that I've found such a good, solid resource for it. So I just say, look, you know what? Just read the NLTK book. This book, you can get it online. It's free. It's online. It's free. You can get it. You can just Google it and you can find it. You can either read the version 3 or the version 2 book. It doesn't matter because you're looking at it from an R perspective, so it doesn't really matter. There's a lot of good theory in there. And once again, as with the Taming Text book, you don't necessarily need to learn the Python syntax if you don't want to. You can kind of ignore it. The idea is just to read the book and understand the concepts and the theory about why you do the things and what kind of benefit that you do. Okay. There you have it. If you go through this list of things that I just provided and study them in detail, you will be very, very far along in terms of text analytics. You will be able to do a lot of really awesome, cool things in your daily work. So there you have it. That's the end of the series. I hope you've enjoyed the series. I've had a lot of fun making it, and I hope that everyone finds it extremely useful. As always, if you like what we're doing here on the Data Science Dojo YouTube channel, please subscribe. That way you can keep abreast of all the latest tutorials that we post to the channel. Also, if you have any questions or concerns, feel free to use the comments section of this video. We at Data Science Dojo monitor our channel regularly and try to answer any and all questions promptly. Next up, if you like what we do at Data Science Dojo more generally, you can follow us on social media. We're on Twitter, we're on Facebook, we're on LinkedIn. And if you start following us, you'll be able to tap into a nice steady stream of data science goodness that you may find useful in your daily work. And lastly, I hope to see you in an upcoming Data Science Dojo Bootcamp. This is Dave Langer signing off, and I wish you very happy data sleuthing.
Give it a like if you found this useful, and subscribe to our channel for more crash courses and tutorials. Thanks for watching Data Science Dojo, data science for everyone.